Wait, I need to also do this. And is it on, or can you check if it's on? Wait. How is this working actually? Oh, and then like this. Hello, hello, hello. Okay. We should check for everyone. I think it's a bit weird. I think it doesn't look well somehow. Oh, I think that's. I figured it out for the speakers later.
Oh wait, you need to do the other way.
Oh, the other way around. Now, this was the problem. Yeah. I just thinking how this works. Okay, cool.
So then later, I think in the panel we can just put it.
Yeah, but it's not particularly good somehow. Hello, hello.
I muted it.
Yeah, but it's what is going on here? Okay, but that's I don't know. For me, it's fine. But I'm just thinking for the speakers later. Yeah, I mean, for the introduction is fine, but if you do it for the whole talk, it does not work so well.
And maybe between speakers, we can maybe switch the microphone on 1 and 2. So then
You can try.
It doesn't take.
Yeah. Hello, hello, hello.
You want to go?
Yeah, let's go. Hello, hello, hello. Yeah, I think this will be fine for the speakers as well. Okay, welcome everybody. I hope you had a great time in Munich so far and you enjoyed CoRL. So on this last day, we have a workshop on mastering robot manipulation in a world of abundant data. My name is Angela Schöllig, but I have been organizing this with a fantastic team of people. And maybe those who are here from the organizers can stand up briefly. So also if you are a poster presenter or a speaker later, you know whom to talk to. So Siki Su, Martin Schuck, and Ralph Römer from my team. But then we also had Animesh Garg and Karime Pereira and Oya Mees helping to organize the workshop. And you will see them around. So the motivation is we want to evolve robotics from static environments where they do simple tasks to tasks in our homes, hospitals, on our roads. So in dynamic, unstructured environment where the environments are not built for the robot. And we all know that machine learning will play a major role to get there. And we have seen a lot of evidence during this conference. And so that was part of the motivation to organize the workshop. And one trend I think we see is that we go from relatively little robot-specific data to large-scale internet data and see how the data the large-scale internet data can really help us in robotics and how, right? And it's still important, I think, to emphasize that these two sources of data are very complementary. We do not generally find robot data on the internet. And we, in the type of and quality of information that is on the internet, any human written text, videos, and images is not what we usually have when we talk about robot specific data. And so here in this workshop, we have two themes. One is what algorithms can we use and develop, and what is the state of the art for versatile and reliable manipulation algorithms? And the second theme is how do we collect data and what type of sensor modalities to use for general purpose skill acquisition. So one theme is around algorithms. One is about data in the broadest sense. And so in my group, we have also worked, I guess, at this intersection using little robot data to improve performance on real robots in a safe manner. And more recently have looked at how we can embed large internet scale data. And to give you some ideas, I mean, we can use crowd navigation data to enable robots to better navigate in crowds. For example, learning diffusion models for crowd navigation. We can use the semantic information of the environment and semantic models to enable robots to do mapping in semi-static environments where things can move over long horizons, such as this room where tomorrow all the chairs are gone and a different event is happening and the robots should still recognize the room again. And we have also used large language models to do creative tasks, such as designing choreographies for robots. And so if you want to learn a bit more, don't hesitate. So we have one survey paper on safe learning, and here you also see a little kind of demo where we now do manipulation for Lego building tasks, and as a benchmark and as a use case to show where we are in terms of robot manipulation. Yeah, just advertising for 1 minute, our lab, if you are interested in collaborations, PhD internships or postdocs in this area, you can always approach me today. And with that, I switch back to the workshop. So today we have an amazing list of speakers. We are really happy also about the distribution between academia and industry. So we have different people from industry, from like Google DeepMind and BMW to Robotics. So I think it's a really great mix, and hopefully we see different perspectives on the problem. And the workshop schedule is, we have a quick opening remarks, then we have a set of invited talks. During the coffee break at 10:30, there will be posters on the second floor, right? So the posters of this workshop are on the second floor, and we have some more, one more invited talk, and then a panel discussion that summarizes the morning. And the morning is dedicated to theme A, which is on the algorithmic side mostly. But you will see a mix, of course, because we are talking about learning algorithms. And then in the afternoon, we have another set of invited talks, but we start with a spotlight talks of all the submissions to the conference, to this workshop. And yeah, at the end, we have another panel session with the speakers of the afternoon. There is a lunch break, and if you haven't read the program, during the lunch break, there will be lunch served, and in the plenary room here in this building, there's an industry panel, which I think for everyone. So I think which is also quite interesting to attend. If people stay longer and are not leaving tonight, we are happy to guide you to a nice place to have dinner and do a bit of a post-workshop social. But maybe we need a rough idea who is still around in the evening and would be interested, such that we can kind of recommend a venue. So maybe just a quick hands, who is interested tonight to still go and have dinner before leaving Munich? So 2, 4. I'm just getting roughly 5, 6, 7. Yeah, so maybe 10-ish. Yeah, 10. Okay, great. Okay, we'll share some more details towards the end of the workshop. Great. So then the papers are all available. The ones submitted to this workshop, you can use the QR link. And the poster sessions are during the coffee breaks, and the spotlight talks for the submissions to the workshops are at the beginning of the afternoon session. Okay, great. Then final note, especially also for those who are joining us online, because we are streaming this event live on YouTube. there's a Slido where you can ask questions. So we will monitor the questions. I guess here in the room, you can ask them yourself, hopefully. And the idea of a workshop is that there's interaction, but especially for those people who are online. Okay, great. Then we can switch to the first invited talk. I'm not sure. Are we doing okay in time?
Yep.
Yeah. Okay, great. So Sergey Levine probably doesn't need an introduction. He's a professor at UC Berkeley, did his undergrad, graduate studies, and PhD at Stanford, and is well known for his work on deep reinforcement learning, end-to-end learning. Also has published various data sets for robotics learning. So I'm really looking forward to hearing a bit more what he is up to right now. Thanks.
Can we use HDMI? Yes. Use this. Yeah. Okay. Yeah.
Do I need to connect the computer, or do I just start working? Did I get permission to share on Zoom? I think I need permission.
Yeah, can you send me? Oh, you're sharing.
Seems to be great out.
You're still sharing.
And yeah, just be a bit patient because we also stream live, so you need to connect to it.
Do you need to give me permission soon?
I think so.
Hopefully that's working.
Yeah. Oh,
Great.
You want to have the mic?
Sure.
Yeah, it's this way around. Yeah.
Okay.
Wait 1 second. We have another.
Other mic. Okay. Yes.
Yeah, it's for online. They didn't give us audio permission for the room.
That's a lot of microphones. Okay.
Yeah.
So somehow put those somewhere. Okay, perfect. All right. Welcome everyone. Hopefully I've got all the electronic doodads and you can all hear me. My name is Sergey Levin. I'm a professor at UC Berkeley. I also spend a lot of my time at a company that I co-founded called Physical Intelligence. And today I'm going to talk about generalist robot policies. All right. So, 1 second. Too many devices and too much stuff. All right. So how did AI systems used to work? If we go back maybe 10, 15 years, if we had a particular problem we wanted to solve, like image segmentation or classification or visual question answering, whatever our problem domain was, we would set up a pretty significant data set for that problem. We would train a specialized model for that task, and then hopefully we get pretty good performance. And this was pretty onerous because we would need very significant amounts of data. And most importantly, we need to be very well labeled data that is labeled with expert human labels for that particular task. And of course, these days, the way that we tend to approach this problem is that we get large amounts of data from the web. The data is typically not strongly labeled. It might even just be raw text or image text associations. We run some kind of giant self-supervised algorithm like next token prediction, and we get back what is often referred to as a foundation model, a model that can solve a diversity of different real-world tasks and can then be fine-tuned to particular downstream problems or even prompted in zero shot to perform those tasks. And that's much, much better because now we don't need huge manually labeled data sets for each individual domain. We can share this one general foundation model across the board. Okay, so of course, where I'm going with this is that in the world of robotics, in some ways, we're seeing a similar kind of transformation where if we go back even a few years, the way that the dominant way of thinking about robotic learning is that for whatever task you have, whether it's making the pancake or picking up a box or whatever, you would train a separate model for that task and that robot and that application, typically that laboratory environment. You would need to collect a significant amount of data, and that was a pretty big barrier to deploying robotic learning systems. How robotic learning might work in the future is that we could pool data from many different robotic sources, which would give us that abundant data that is in the title of this workshop, which we would then use to train a big self-supervised or action supervised, something supervised robotic foundation model, which could then be either prompted or fine-tuned for downstream tasks. And of course, as a high-level picture, this is very appealing because now this would overcome one of the biggest barriers to the deployment of robotic learning systems. But there are a lot of pretty major questions that we have to answer before we make this possible, like how do we design these models? Where do we get this data? How do we combine whatever data sources we have? How do we make all this scalable? And also, how does the downstream stuff work? How do we adapt these models and specialize them to particular tasks? So one piece of the puzzle that I want to tell you about is how we can get data from many different robots to train robotic foundation models. This is really important because if we live in a world where, as Angela said in the beginning, that there isn't an internet of robot data, well, that means that for any given robot, there might not be huge data sets available. But in a sense, we can actually get something that looks like the robot internet by pooling data across many sources. And we explored this on a project called RTX from about a year back at this point, led by Quan Vuong and Carl Perch, where we didn't just scrape the data from the web, but we contacted academic research labs, the 33 other labs in total, in addition to Google DeepMind, and asked them to share their data for whatever manipulation tasks they were doing with us. And that gave us something that looks a little bit like the robot internet. Now, I could tell you lots of stats about these data sets, but it's maybe easiest if you just see some videos of these things in action to get a sense for the diversity of the data. All of it involves robotic manipulation, at least the data that we used for the models. The OXC data set itself also has many other sources like navigation, but for the experiments, we used only navigation data. It's all single arm with parallel jaw grippers, but there's a huge amount of variability in the task, in the robot, in the camera viewpoint, all these sorts of things. So the good thing is that this gives us much more abundant data. The downside is that this data is extremely heterogeneous. So we have to think about learning methods that are cross-embodiment, that can handle a variety of different robotic systems. Now, the good news is that if you actually do this, you can get very, very powerful models. One of the experiments that we did is we took all of the robotic manipulation data that we had in this data set, trained a model on this, and then sent that model back to a number of the labs that contributed the data and asked them to test this cross-embodiment model in comparison to whatever model they were developing for their own individual tasks. So each lab had a different application, and therefore they had a different model. These tasks were very diverse. Here are some videos of the kinds of tasks that showed up in the evaluation. And here are the comparisons. So the important things to look at here would be the colored bars here. They're all in different colors because every lab had a different method, versus the rainbow colored bar, which is the cross-embodiment model. And you can see that in most cases, the cross-embodiment model is better, and on average, it is 50% better in terms of success rate than the individual specialized models that each lab had. And that's really exciting because that's showing us the kind of benefits of generality that we saw previously for things like language models, where the general model trained across many different settings actually beats the specialist for the particular task that the specialist is actually specialized to. So that's really important. Now, that's not all of the solution, of course. That's just a piece of the puzzle. Another piece of the puzzle that we have to figure out is the type of model that we can use. And here, too, there's a way for us to leverage even more abundant data sources, namely image language data on the web. So we could, for example, take large language models, fine-tune them to process image observations. That's a standard procedure to turn them into vision language models. That's typically done using tasks that combine images and text for things like image captioning and question answering. And then further fine-tune these models to actually process essentially visual questions that are really robotic tasks. So if the question is like, what should the robot do to pick up the Coke can? The answer is actually an encoding of the action that the robot should take at that instant in time, depending on what it's seeing in the image. And if you do this, you can actually get a vision language model that performs robotic control. The early prototype of this used two models, one called PolyX and another one called PolyMe, and this was also done on Google DeepMind. And if you actually combine this type of vision language model architecture and then fine-tune it on diverse data from the cross-embodiment data set, you can get pretty interesting results. So you can get models that can follow, for example, spatial commands like move apple between can and orange. These are commands that don't occur in the training set for this particular robot. In fact, the exact command doesn't occur in the training set for any of the robots, but it puts together bits and pieces from the different examples that it saw to perform these tasks. And perhaps surprisingly, the cross-embodiment model, this is the one that ends with X for cross-embodiment, actually ended up performing about 3 times better in our experiments on this robot, even though this robot was probably the most overrepresented in the original baseline data set that had this, the RT2 paper that used only data from that robot. So that's pretty surprising that even though this is the robot we're testing on, and this is the model that had only data from that robot, and it was the largest data set in the group, it still gets a huge bump. the model can perform a variety of different tasks that involve, spatial reasoning, semantic identification of objects, all that kind of stuff. But the other thing you probably noticed from watching this is that the tasks so far are relatively simple. So they're kind of, academic style tasks. They're really meant more as tests of the model's semantic parsing ability, more so than its ability to actually perform intricate manipulation behaviors. So where have we gotten so far? Well, so far in the talk, we have a way to inherit internet scale knowledge from VLMs to improve robotic control. And we have a hint about how to bridge the data gap by aggregating data from many different robots. But there's still things lacking. For example, the tasks are still pretty simple. They're pretty rudimentary. The generalization and language following is limited. And the architecture is not really adapted to robots. The model architecture is literally just an off-the-shelf vision language model with a different set of training examples. So where can we go from here? Well, we need to understand how complex tasks can be learned via these vision language action models and actually design architectures that are specifically suited to controlling robots rather than just using off-the-shelf models designed for outputting language. We need to handle diverse robot types with different morphologies. So all the robots so far were single arm with parallel jaw gripper, all controlled in end effector space. So the action spaces are actually aligned. It's just that the identity of the robot is different. And we need to develop the right architecture for these very generalist policies. So these are some of the things that I'll talk about in the main technical portion of this talk. I'll have three sections. I'll talk about a recent model that we released at Physical Intelligence called Pi0, which is a generalist robot policy that can actually handle multiple different morphologies and is specialized to dexterous manipulation. I'll talk about how we can use the language generation properties of VLAs to provide for better reasoning. And then I'll, at the end, briefly discuss how we can get better performance by also leveraging reinforcement learning in a kind of post-training phase. But let's start with better generalist robot policies. So we recently released a paper on this model that we call Pi0 from Physical Intelligence, which is something that we've been working on for about the past 8 months. And this is a model that is trained on a diverse data set that we collected from a number of different robotic platforms. So they're shown here, as well as all of the RTX data and other data that is publicly available. Now, the robots here no longer consist of just single arms. Some of them are bimanual systems. Some of them have 7 degrees of freedom. Some of them have 6 degrees of freedom. Some of them are actually mobile, and they all have different action spaces. So the model has to handle variable action spaces. And the tasks are going to be much more dexterous. The control is going to be at a higher frequency at about 50 hertz. And the model needs to handle that kind of high frequency dexterous control. So the overall design of the system, and it really is much more of a system than it is a single model, consists of a pre-training phase where we pool data from all of the robots that we collected data from, as well as utilizing internet scale pre-training for vision language models and the entire OpenX embodiment, the RTX data set. That is used to train a specialized flow matching based vision language action model. From there, that model can be prompted for zero-shot control. So it accepts text commands, but it can also be fine-tuned. And this is how you can get the most power out of these models. If you can actually fine-tune them in the same way that we post-train language models to align them with human preferences, we can post-train these models to get them to perform very intricate tasks like folding laundry or new tasks that are not seen in the data set that I'll show in a second. And that can get you really good performance on very intricate tasks. So let's talk about the model first, but I do want to emphasize that this is really much more about the system and the training recipe rather than just the model architecture. So the whole thing actually matters. And if you're thinking about like what's important for getting robotic foundation models to work, probably all the data stuff, how you do pre-training, how you do post-training, how you structure that actually ends up being more important in practice than details of the model architecture. But I'll talk about the model architecture because I do think it's actually pretty neat. So the design of the model here utilizes flow matching, which is basically a variant of diffusion to generate actions. And that's really nice because that allows us to output continuous actions without discretization, without tokenizing the actions essentially, and handle very complex multimodal distributions, as well as action chunks. So for high frequency control, it turns out to be very important to output an action chunk, which is a group of actions, a little short trajectory of actions, in this case about 1 second's worth, and to actually be able to handle multimodal distributions. So here's how the model works. We have what is essentially an encoder, which is initialized from Polygenial, which is an open source VLM, that takes in between 1 and 3 images, depending on the embodiment. So some robots have only a single base camera, some have up to 3 cameras, 2 wrist cameras and a base camera. The model takes a language command, and that's just processed through regular tokenization. And then the actors are produced by what we call an action expert. So the way that you could think about this action expert is you could actually have the whole VLM extend all the way outward to the actions, and then just have a different loss on the tokens corresponding to the action dimensions. If we do that, Then you actually get a rudimentary version of a diffusion VLA. And then what we do is we actually use different weight parameters for the portion of the network that outputs the actions. And that's what we call the action expert. Now, it has different weight parameters, but it still has the same number of layers. So each layer in the action expert actually attends to all of the layers in the VLM. So it's not actually an encoder-decoder architecture. It's actually one decoder-only model with attention from here to here, but it just has different weights for the action expert. So you can roughly think of it as a mixture of experts model with one mixture element for the actions and one mixture element for the images and language. The join angles are actually fed into the action expert. Basically, you can think of the action expert as being specialized in everything continuous, and this part is being specialized to everything involving images and text. The action chunk is about 50 time steps. Each time step has a dimensionality of up to 24, depending on the robot. And the generation here is through flow matching, which roughly speaking, you can think of as a variant of diffusion. Okay, so that's the architecture. Now let's talk about the training recipe. So we start with a pre-training data set, which basically has everything. So it's about 10,000 hours of data in total. It's, to our knowledge, the largest robotic data set that anybody has trained a model on, outside of maybe autonomous driving. And then you can get a model out of this and you can prompt that model to perform tasks, but you can also specialize it to particular downstream tasks. And that usually is going to use somewhere between 1 and 20 hours of data. So the more complex the task, the more post-training data you need, but this is still the kind of data that you could collect in a day or two. So for very complex tasks like laundry folding, specialization might be about 20 hours. For box building, it's also going to be 20 hours, but there's some simpler tasks where it's going to be between 1 and 5 hours, and you can still get good performance. And I'll show results for different tasks. Some of those tasks are actually present in the pre-training data. So for laundry folding, there is actually plenty of data in pre-training. So it's not just 20 hours of laundry folding, it's 20 hours of high quality data and then lots of low quality pre-training laundry data. For other tasks like box building, that's actually not present in pre-training, and the only data for that is the data in post-training. So the post-training data is high quality but narrow data. The pre-training data is lower quality but broad. The post-training data needs to illustrate consistent strategies for how the robot can perform the task well. And by itself, if you just use the high-quality data, that doesn't actually work, because the high-quality data, because it's more narrow, doesn't actually teach the robot how to recover from all sorts of mistakes. So you really need both phases, and it's not just about initializing the model in a good place. In the same way that for language models, the pre-training phase is what actually bakes knowledge into the model. For this system, the pre-training phase is what teaches it how to handle all sorts of diverse situations. The post-training phase, the right way to think about it is it's really there to specialize the model to a particular task. So most of the knowledge, most of what the robot knows is actually going to come from here. And this is basically going to tell, like, okay, if you actually want to be good at folding t-shirts, this is how you do it. So if you just use this 20 hours of data, that's not really great. But if you combine it with pre-training, that's how you can get really good results. All right, so let's look at an example where we take the Pi0 model after pre-training and then specialize it to a new task that was not present in pre-training. The task is going to be to assemble a box. So you get this piece of cardboard, and you're supposed to make it into a complete box. This is very difficult because if you've ever done this yourself, you put one tab in, and of course the other tab immediately pops out because the whole thing is kind of wiggly and annoying to deal with, and the robot is really going to struggle. So it's pretty difficult to do, especially when you have only 2 parallel jaw grippers to do it with. So here's the execution of this task after post-training. So there's Suraj testing his robot and examining its performance very sternly. And you can see it's going to take a little while to do this right. So it's far from perfect. There are things like missed grasps and mistakes, but it generally does a pretty good job of recovering from those. And you can see that it actually uses kind of an interesting strategy where it braces the box against the table in order to perform the fold. This is difficult to do. It's actually difficult to do even under teleoperation. So you have to actually practice this task quite a bit before you can do it successfully yourself. So it's actually pretty neat that the robot can do it. And many of these steps themselves can also fail. So here it's actually inserting those little tabs. That's why it has to squish it like that. Here it happened to have worked on the first try, but oftentimes inserting that tab actually fails and has to try it many times. And of course, the great thing about the task is that once you get a policy for it, you can run it, in different conditions. You can put the box down in different orientations with limited variability in this case, and actually get something that works. So these are 5 different executions of the task, just to show you that that wasn't the only trial that worked. We can do a variety of other tasks. So here on the left, you can see a few examples of different tasks we did, scooping food from a plate, putting eggs in a carton, and so on. And these are the quantitative results. Now, the y-axis here is what we call a task score or task progress. Basically, the task consists of different steps. And if you get 1.0 on a trial, that means that you did all the steps. If you get 0.5, you kind of get partial credit if you, for example, folded just one half of the box and not the other half. The interesting comparison here is between the full Pi-0 model after pre-training and post-training, that's the solid bar, as opposed to the dashed bar, that one uses only the post-training data. And as I mentioned, using only the post-training data is not very good because it's a little too narrow. So for some tasks, it actually works, like for the egg packing tasks, but for other tasks, it's quite a lot better to use pre-training because then you inherit all those strategies for recovering from mistakes. Other complex tasks, sorry, something's wrong with the video. Let me just restart that. There we go. Okay, other tasks, bussing tables. So this is done with a different morphology. This is a single arm robot. And you can see here it's cleaning all sorts of trash from the table. It has to put the trash in the trash bin and put the dishes in the dish bin. So of course that requires some amount of semantic recognition. It requires generalizing to new objects too. So that works pretty well. Other tasks we can do, for example, laundry folding. So this is a pretty intricate task. This is really difficult because since the laundry is crumpled up in that bin, it can come out in all sorts of different configurations. And the robot has to handle the laundry in whatever configuration it comes out in, flatten it, and then fold it and stack all the laundry items in the stack in the top right corner of the table. There it goes. And this works with a variety of different laundry items, different initial configurations, and so on. It also works with a different robot. This is a mobile robot. And you can see sometimes it fails, but it just keeps trying until it gets it right. Here's another laundry task, taking laundry out of the dryer. So it has to approach the dryer, open the door, and then take all the items out. So for the laundry task, sort of truth in advertising, there is a lot of data in pre-training. So even though the fine-tuning is on 20 hours or less, the pre-training actually contains a lot more laundry trials that are of lower quality. And that's actually really important because in this task, the clothing items, as you might imagine, can enter all sorts of different configurations, especially if the robot makes a mistake. So that pre-training is necessary for it to know how to recover. Speaking of recoveries, we messed around with our robot to try to see what it would do. And it's actually pretty interesting, the kind of recovery behaviors it exhibits. So here, Michael throws a shirt onto the table to try to confuse it. And it is actually like somewhat confused by this and then decides, okay, that just goes right back. Now everything is back to normal and it can proceed happily with folding the shorts. And if Michael intervenes again, it can put it back again. So here are a few more perturbations. So Michael can go in, mess with it. And because it has so much pre-training data, it actually can handle all these unexpected situations, usually in a sensible way. Occasionally it'll get confused and it'll decide to like push the stack of clothes off the table or something like that. But most of the time it actually responds in a very sensible way. Here's the full laundry task. So this is actually done by taking the model and training it on multiple different tasks together. But because it gets to see the image, right, it can figure out from each situation which task it's supposed to be doing. So here it actually unloads the dryer and then it goes and folds the laundry. So it's a single policy doing all of this. This is sped up mostly so that we wouldn't be sitting here all day. But in terms of the folding itself, it ends up being about 2 to 3 minutes per clothing item, mostly because sometimes it makes mistakes like this and takes a little while to get out of it. But it does eventually fold the entire stack from the dryer. And we want to put it in the dryer so that the dryer would naturally randomize the shape of the laundry. There we go. Okay, so takeaways. What we have so far is a prototype of a generalist model trained on many robots. We have good performance across a range of what I think are extremely complex tasks. These are quite a bit more complex than the put the orange between the Coke can kind of tasks that we had before. But there are still things that are lacking. So fine-tuning is still crucial for most of the complex tasks, especially if you put the robot in a weird new domain and a weird new environment. What we would really like is for it to figure out maybe in zero shot through some complex prompt that says like, oh, you fold the laundry like this and that. But for now, it actually requires fine-tuning. It would be good to get around that in the future. The high-level strategy is sometimes lacking. So those of you that were looking close at some of the laundry folding notice that sometimes the robot would do silly things like almost completely fold it and then decide, oh, it's not good enough. Let me unfold it and try it all over again. So it is very, very much a reactive policy at this stage. And it's trained via imitation learning, which means that it's not actually optimized for task success. It's not optimized for robustness, and it's not optimized for speed. So these are all things that could be addressed in the future. So where do we go from here? Well, I think we've only scratched the surface of VLM capabilities, and we can push performance also much more if we can optimize for that directly with RL. And I'll very briefly touch on those topics next. So one of the things we've worked on at UC Berkeley, this is work led by William Chen and Michal, is better VLAs via reasoning. So what Michal Zawalski and William Chen and collaborators developed is a way to use VLAs with additional sequential reasoning steps where you can actually get the model to think iteratively through a problem to generalize better. So instead of directly outputting an action in response to a command like clean the sink, the model instead performs intermediate steps like detecting objects through bounding boxes, breaking down the task into substeps, and then outputs the action. Now, it's important to distinguish this from a modular approach. In some ways, this is modular in that the model actually performs those intermediate steps, but it's also an end-to-end approach because the supervision is for the entire chain of thought generation, including the final action. So the model really is still trained end-to-end to output the right action, but is trained to also output intermediate steps and then utilize the outputs of those steps for the final result. The training data for this model is generated synthetically by using other large foundation models to perform a variety of operations on the training data, like localizing objects and breaking down complex instructions. And that's all baked into synthetic training examples in the same way that we generate synthetic training examples for post-training of LLMs. In the end, the actual VLA model is still the same type of VLA model as before. This one still uses the older discretization style approach, and it just autoregressively generates the full chain of thought reasoning process and the final action. So if you want to see this in practice, here you can see 4 different tasks. On the left is what the robot is seeing. On the right is the chain of thought generation. There are bounding boxes that are visualized on the images. Those bounding boxes are just for your interpretation. So that the model doesn't actually get the bounding box. It's just parsed from the chain of thought generation for visualization. And it actually works quite well. So this model uses something called OpenVLA as the base vision language action model. So OpenVLA is just trained end-to-end to go from image and text to action. Embodied chain of thought augments that with these chain of thought generations, and you can see that it gets a very significant bump in the success rate. Also better than the RT2X model from before. The last portion that I want to talk about, and I'll keep this pretty brief, is how we can also improve these robotic policies through real-world training with RL. This stage doesn't currently actually use VLAs. It's actually just trained with smaller models, but in the future we combine that, and I think that is where we'll see the most promise for the most high-performing and fast policies. So these are some results that I'll show that were primarily developed by Jianlan Luo and Charles Xu at UC Berkeley. We started on this maybe about a year ago with tasks like electronics assembly and developed RL algorithms that could start from demonstrations, in this case, a much more limited number of demonstrations, about on the order of 15 to 30 demonstrations, and then run an extremely sample-efficient RL algorithm that's optimized for real-world training. And this RL algorithm can learn tasks like electronics assembly in between 30 minutes and 2 hours. So this task is maybe on the faster side. You can get a very successful policy in about 30 minutes. Actually, even within 15 minutes, it starts inserting the chip consistently. And you can see that it doesn't damage the pins on the chip while doing that. So this is actually the entire training process that you're seeing. Because the time in this talk is limited, I'll fast forward it a little bit. But here is the, sorry about that. Here's the performance at, well, anyway, PowerPoint issues. I do have some final videos here, which of course I'm going to play. All right. Go. Okay, well, it happens. New computer. The results are really cool, so you're really missing out. But I will tell you the quantitative results. So there were a number of tasks that we evaluated, inserting the microchip, routing cables, and relocating objects. And we actually provided our imitation learning baseline with the same amount of data as RL. So RL received between 30 and 2 hours of data, depending on the task. We actually gave more demonstrations to the imitation learning method to match up to that level. And we still obtained significantly better results with RL because these tasks require that degree of precision. And perhaps even more important, the cycle time was quite a bit lower, so that the policy from RL ended up being 2 to 3 times faster. So you can imagine, of course, that if we combine these kinds of methods with the large robotic foundation models, that would lead to some significantly more effective results once we can figure that out. For other more interesting tasks, this is some recent work where we extended this to things like bimanual manipulation. This is assembling a car dashboard. Again, this is the training process. The training process sped up 20x. It takes, for this task, I believe it takes about 2 hours to get to 100% success rate. And here's the final policy. So it has to pick up the dashboard and it has to actually line it up with multiple different pins and insert it with the plastic pins. Here are more tasks using, and students have interesting sense of humor, using a whip to remove a Jenga block. That's maybe not the most industrially relevant task, but some of these are actually pretty intricate. So this timing belt assembly requires the robot to handle deformable objects and things like that. Flipping an egg, assembling IKEA furniture. The robot can't handle the screwdriver yet, so Charles has to go in there and put in the screws, but the robot can line up all the pins and all the pieces. The model is also pretty robust to external perturbation. So here's the timing belt assembly, and here Charles goes in and messes with the timing belt, and the robot actually recovers. Now, in this case, the recoveries don't come from pre-training. The recoveries actually come from the RL policy itself, experiencing a variety of situations. So of course, you can imagine that if those parts were combined, we might get an even more robust policy in the future. Here's the complete motherboard assembly task. This is kind of a neat one. This actually shows multiple different policies, one for every electronic component. So the different components are trained separately, but then they can be combined together into one execution. And I asked the students in this case to prove to me that the RL process didn't actually damage the computer. So after they assemble it, after they put in the SATA drive and the RAM stick, I want them to actually turn on the computer to show to me that it works. So here's the RAM stick. If you've ever built a computer, you know how annoying this thing is because you have to apply force to actually slot it in. Next, we have to plug in the USB keyboard so that we can type the password into the login screen. There's the USB plug. And then once we've plugged in the USB plug, we have to be very neat with our cable routing, and we have to make sure that the cable goes into the little cable clip. So that's an interesting task because it's a wiggly, deformable object. The reward here comes from an image classifier that just looks at the image and predicts whether it's successful completion. And then we push the button to prove that the computer has in fact been assembled correctly, and it does in fact boot up. All right, so to conclude, something that I want to leave you with is this, that in the world of large language models, we have a particular training recipe that pretty much any large company working on language models converge on. There's a pre-training phase with large amounts of very diverse data. There's some kind of architecture that can utilize that diverse data. And there's a post-training phase that either uses high-quality supervised fine-tuning or reinforceable learning to get the model to actually follow human instructions in an effective way. And what we're converging on in the world of robotic foundation models is actually an analogous architecture where we have a pre-training phase with diverse data. We have an architecture that is designed to handle that diverse data effectively and actually distill out all the knowledge in it. And then we have post-training, which currently is often done with supervised fine-tuning, but it can utilize things like instruction fine-tuning with chain of thought. And maybe in the future, it could also utilize reinforcement learning. And I think it's very interesting that we're converging on a very analogous recipe, but with different choices for all the individual components. So I think I'll leave it at that, and I'd be happy to take questions. There's a question over here.
Thank you so much for the talk. So I think you have maybe two or three questions we can ask now, and then there will be a panel later. But I would like to ask the next speaker to already set up if that's fine. So, your question.
You had your hand up first?
Yes. Thanks for the talk. I had a question about the post-training data. And you mentioned briefly the partial credit and how important or how insensitive is the partial credit scheme to the actual data, and is it robust if you change it after the fact somehow? You might have to.
Well, so that's just for evaluation, right? So that's just how the plot is generated. For example, for I'm trying to remember from memory what the scoring system is. I might say it wrong, but my recollection is for laundry folding, I believe it's 1 point for flattening the object, 1 point for folding it, 1 point for putting it on the stack, things like that. So this is very important for these tasks because these are very long horizon tasks. And for a lot of baselines, like you'll just end up with a result of 0 across the board. So we found that scoring system for our own internal evals to be more effective. And that's why we used it in the paper. But it's not, this doesn't actually affect the policies themselves. It's just how the bar graphs are generated.
Yeah, so you use a lot of cross-embodiment data in terms of having different robots. What about having sim?
Yeah, that's a great question. So for everything that I showed, use only real data. Now, I do think that you could incorporate simulation data into these things exactly the same way they do it for any other kind of sim to real system. I think a really interesting question here is whether cross-embodiment training might actually make it easier to use sim, because you could imagine that if you have just one robot and one simulation, now you have a transfer learning problem. If you have many robots and maybe many simulations, now they might encompass essentially a single, much broader distribution. I think that would be a really interesting thing to explore in future work. It's not something we've worked on because we're not simulation experts, but I think it's a really interesting possibility.
So have you encountered any hallucination
Yeah.
language models and so that it goes to EU regulation?
Yeah, that's a really interesting question. It's a little hard to answer because you know, the way this shows up in the policy is like the robot makes a mistake. So the robot definitely makes mistakes. The degree to which those mistakes are hallucinations or not is a little hard for me to tell. But you know, you even saw in the videos the kind of mistakes it makes, right? So a lot of those grasps, especially on cloth when it's lying on the table, they're pretty difficult because you have to go to a particular height. The interesting thing about these policies is that when they're trained on very diverse data and lots of that data, they actually exhibit a lot of corrective behaviors, which you don't get if you have very small data sets. So that's maybe like the one saving grace there is if you have a task where retrying eventually allows you to succeed, then you will eventually get a success rate slower. Now that won't work every time. So if you're, you know, picking up a fragile glass and like putting it on the shelf, if you accidentally drop it, you don't get to try that again. So there's still open problems. And that's where I think some of these other post-training methods like RL could be very effective in the long run.
Okay, one final question, and then I think we are ready to go with the next talk, but there will be a panel discussion for lunch. We'll make sure that everything is on.
Yeah. Oh yeah, you can put it in. Yeah. Oh, the original.
Yeah. I think it's a good question. So for LLMs, it is used in the sense that you can think of RLHF as a model-based offline RL procedure. There are a lot of challenges with training very large models with RL that are basically the same as the usual RL challenges scaled up. So RL methods are harder to stabilize. It's harder to hide parameters when you're training on, say, weeks instead of hours. All those problems become more severe. So this is very much an active area of research. So if you're keeping that on RL algorithms, developing better algorithms for large and small models is a good thing to do. I think there's a lot more progress to do.
Okay, great. Thanks, David, again.
How do I use this like that? Okay. Can you guys? This is not on.
Okay, so our next speaker is Jens Handa. He's a postdoc researcher in robotics at KTH in Stockholm, and he's working with Danica Krajic on robotics, perception, and learning. His research focuses particularly on data-driven approaches to robotic manipulation and grasping, and he has put a particular emphasis on in-hand manipulation with deformable objects. Jens completed his PhD in robotics at the Aalto University, where he addressed probabilistic multi-finger grasping in colored environments. And he also did his master's and bachelor's degree at that university in space science and technology. So one round of applause for Jens.
Hello. So I'm gonna unmute you. Yeah. Yeah, hello. Thank you for being here. So I'm presenting today on behalf of Danica Krajic, who couldn't be here. And in comparison to the previous talk, I want to use less data. And but why we want to do this? Because we all seen the scaling laws, that everything seems to work much better just with compute, data set size and parameters, at least for LLMs. I think the previous talk also confirmed that the same thing exist in robotics. We can really see that the test score error rate decreases with the size of the model and with the number of demonstrations. So am I just pursuing a goal that is ill-posed? is there any reason to be like Scrooge McDuck? Initially, he was portrayed as this greedy person who had all the money in the world, but he didn't want to share it with anyone. And I don't think we should be like that, to use as little data as possible. But my thoughts are that we should be, at least we could be more careful with the data. We could use it more efficiently. And why would we like to do that? Well, this is a demonstration from our lab. So this is a AR teleop. The task was to stack blocks, right? Really small blocks. So you had to be really precise. And we use these MetaQuest controllers to do it. And this was very taxing. So after 10, 15 minutes, you just couldn't do this much more longer. And we also did the same for rice scooping. So getting 20 hours of data of this is kind of impractical. Although we have seen a lot of innovations in this as well, using these type of robotic manipulators, but not the embodiment of the robot to gather data. But still, I think we could do more with less data. And how can we do it? Well, in the lab I am in, we have used two things. One is equivariance, and I will talk about this today. So how can we use symmetry in data to do robotic tasks? We have specifically done it for grasping, which I will talk about. And another one is how can we use inductive biases? So how can we use physics-based information to learn better networks with less data? So let's start with equivariance. So what is it? I think a few of you maybe have seen it, but the mathematical definition is really this. It's a single line that contains a lot of information. So what it says is that if you apply some transformation to your data, g times x, so g is your transformation, you put that through a function, f. It should be the same as you first put your data through a function, and then you transform the data, so the output. It is more often showed in this diagram, so it just says the same thing. You can take any of these paths, going from x, applying the transformation, and then through a function, should equal that putting x to a function and then applying the transformation to the output. More practically, it's, let's say we have this cat and we want to segment it. It would look something like this. But then we could reflect it and it will look something like this. The thing is that we shouldn't have had to learn the segmentation again if we reflect it. We should just be able to reflect the output of it. And this is really what equivariance does. And it means that we don't have to see all transformations of the data. If we know some symmetry in it, we can just embed that into the network, or we could transform the data into a canonical space to learn these efficient models. And we took the same approach in one of our grasping work. So the idea here was, given an object point cloud, we wanted to constrain the approach direction here of it to be inside a cone. It's really that simple. And why did we want to do this? Well, one of our challenges was we wanted to grasp from a confined space, so from a shelf. And we didn't want to waste data on why do we want to generate grasps from behind the object when we can't reach that with motion planning. So the problem is really like this. So we have the object, the grasp, and then we have the cone parameterized by an approach direction VA and then an opening angle alpha. And we wanted the approach direction of the grasp VG to be inside of that cone. Mathematically, it looks like this. So we just wanted to learn the probability distribution of grasps and success condition on objects and the cone. This we can split into the following. So what this means is that we can want to learn the probability of success given a grasp, and then want to learn the probability of grasp given an object and the cone. Simply stated, we wanted to learn an evaluator and a sampler. And the neat thing here is that the evaluator don't have to care about the cone constraint, because the cone constraint is only useful for sampling grasps. This we learn with two different neural networks. And I will only talk about the sampler here. So what we first tried was just this simple variational autoencoder. where the input is the object grasp and the cone constraint. Then we condition on the object and the cone constraint in latent space, and we wanted to reconstruct the grasp. This should have worked, but it really didn't. Maybe we had too little data. So, but the nice thing here is that we have some symmetries in the data because of how we have the cones constraint. So this is the object in the camera space. So you can see the X, Y, and Z is the camera coordinate system. And what we can find here is that we can always transform or rotate this object to align with some of the axes of the camera coordinate system. So here we can find a unique rotation matrix that always rotate the blue object to be the approach constraint to be parallel to the negative y-axis. And why do we want to do this? Because then we can always generate grasp from only top down. And then because of the unique rotation matrix, we can transform it back into the original space. So in this way, we ensure SL2 equivariance. So our new sampler just looks like this. The thing here is also that because now we have all transformed the space into another space, is that we don't have to condition on the approach direction anymore, because the network knows that always have to learn grasp from top down. And this works very well. This is how it looks, the whole process. So we take the object and the cone, then we find the rotation matrix. We apply the rotation transformation to the approach space. We sample grasp there, and we do some evaluation and refinement of the grasp. We find the best one. Then we rotate back into the original space, and we can execute the grasp. The main thing that was that failed in this thing was not the grasping, it was actually the motion planning. So planning to these small confined spaces is not that easy. If you ever played with motion planning, you should know that. These are some other example of the same thing. So for instance, in the bottom right, we can see this blue picture, which we don't have a lot of wiggle room to grasp it. So this worked well. Compared to other networks, we get 10 to 20% higher grasp success rate. It's still far from great, but the thing is that the grasp kept is really like the number of sampled grasps is how many of those are within the cone constraint. And with our network, we are essentially up to 100%. So we really see that the network learned to adhere to this sort of soft constraint. Okay, so this was our work on. Yeah, and at CoRL, there are many works doing equivariance. So it's still a hot topic, and I think there's a lot of more work we can do there to be more data efficient. Okay, so that really concludes my part on equivariance. Let's move on to inductive biases. And what is inductive biases? Well, for one thing, equivariance is an inductive bias. It is something we know about the data that we can then use to learn better, and which could be good, for instance, for grasping. Another thing that we used an inductive bias is physics-based priors. So how can we use knowledge from physics to embed it into the network structure to really be able to, for instance, learn the dynamics model that could be used for predicting high-dimensional objects? So physics-based priors, one of them that we have used is the Lagrangian. So this odd equation really describes a lot of dynamical systems. It's made up of kinetic energy, the difference between kinetic energy and potential energy. And most of us knows that kinetic energy can be written as 1/2 times the mass times the velocity squared. This is just the same thing in matrix form. And where Q here, when Q dot means the joint positions and velocities. Another thing that nature has given us is the principle of least action. What this really means is that if I have 2 points in space, A and B, the nature will naturally have us to do the actions that leads to least. The trajectory from A to B should be the trajectory of least actions. It can be formalized in this differential equation. And then if we use this Lagrangian, we can solve for it. and we will get out this differential equation. Most of you have seen this. It's the manipulator equation. It's more commonly written like this. So it's an equation, the mass inertia matrix of your dynamical system times the joint acceleration plus the Coriolis and centrifugal force plus some gravity term. And we can actually use this to make networks, to embed them in the network learning. So let's say we have the same manipulation equation here, but we don't know the mass inertia matrix, which is very seldom known, and it requires a lot of engineering effort to learn it. And also, let's say we don't know the gravity term. What we can do is that we can learn these two with separate networks from data. So now let's say we only have a few samples of the joint position, velocity, acceleration, and the torques. What we can do then, we have this sort of network structure. So we put in the joint position into two separate networks, one to learn the gravity term, and another one to learn the mass inertia matrix to the Cholesky decomposition. What you can also do is that you can analytically derive the gradients of the partial derivatives of m with respect to q. And you can then use those analytical derivation inside your network, such that this would obey the manipulator equation. So with this, we can learn with just this simple loss function. So we learn to predict the torques. We also have to do a regularizer on the parameters because a Lagrangian is not unique. It's any Lagrangian that obeys this manipulate equation is a valid one. So that's why you need a regularizer. But one thing that Delan overlooks is the geometry of the data. So it means that if you have two joint positions close to each other, it should mean that the predicted mass inertia matrix is the same or very similar. This is not true. And what we then propose is that we want to enforce this geometric consistency while learning. So we want to have the mass inertia matrix to belong to the space of symmetric positive definite matrices. And we do this by a composition of three different networks. One is a Euclidean network, so just a regular MLP. Then we use the exponential map to get it to the space of symmetric positive definite matrices. And then we apply some SPD layers there. So graphically, it looks like this. We have a Q in some space. Then we apply some MLP layers, which we then map to the cone. So this is the cone of symmetric positive definite matrices. And then inside of there, we apply a few more layers to get it to another feature space on that cone. So in this way, we ensure that the geometry holds. We also use Riemannian optimization to do all of this. And what we get out is that we can really see, like, just from a 2-3 data points, we are 10 times better than the Delans. So this is really small data to learn a double pendulum, which is a very simple system. And this is also the drawback of this method. We can learn to predict how this 2-DOF pendulum works, but this is not really practical. We might want to learn the mass inertia matrix for humanoids or by manual settings. What we then did is that we introduced this reduced order Lagrangian neural network. So it looks rather simple. It's just an autoencoder that reduces the high dimensional space down to a low dimensional. And inside in the latent space, we learn a Lagrangian. Different from the previous work is that we use an ODE solver in the latent space to predict the next joint velocity and position. But the network is otherwise very similar to the previous one. We have 3 losses to enforce the Lagrangian dynamics and the reconstruction loss. And we again have to have the regularizing on the parameters. But it's a very simple system. And but one thing we also have to do, make sure, is that to learn these reduced models, we have to make sure that the pairwise layers of the encoder decoder are their inverses. So they should be multiplied together. They should be the identity matrix. And this is something we enforce while learning. And this is how the output looks like. So this is on a 16 DOF pendulum. And you can see that it works much better. We can actually predict. On the left, it's our best model, and we can really see how it follows the pendulum. And this is really what we see also. If we don't do the reduced order, we have 10,000 times higher prediction error. So this looks nice. Can we scale it to more than 16 DOF? So that we did. We have more results in the paper, but this is our highest DOF example. This is 600 DOF plot, which we predict initially from the start. We predict the whole trajectory until the end using our learn model. You can see that it's a bit crumbled, but it's still, I'm surprised how well this actually worked. And yeah, this is where we are now. We would like to put this on a real system to learn from very few data points, the whole Lagrangian dynamics for that. And there are been at CoRL a lot of inductive biases papers. So it's still a hot topic, and maybe it's worth pursuing to do more with less. So these, before I wrap up, I want to thank my co-authors, Hao Fei and Zhang for CapGrasp, and Katarina and Noemi did the reduced order Lagrangian neural network. So I started off by showing the scaling laws, and it really seemed like that they do. It's just enough to scale. But I think it still pays off to be a little bit like Scrooge McDuck. I hope I showed a few examples that we can do more with less. Maybe we don't have to gather data for 20 hours. Maybe just 1 hour is enough, as long as we maybe have some equivariance, some sort of inductive biases that we can embed. And yeah, this was it. I'm happy to take questions.
All right. Can you hear me? So, do we have any questions in the audience?
It's such a good
It's
work.
I have one. So
Yeah.
we've seen many different approaches that have brought something to robotics. For example, diffusion policies have brought diffusion into the mix, and now we're seeing flow matching models, etc. But all of them, in the end, sort of get merged into this transformer-like architecture for large-scale data learning. Do you see a way that you can include something like this also in these scalable architectures?
Yeah, so transformers are by nature permutation invariant, but the position embeddings actually breaks the equivariance. So it would be nice to see that. But one thing we see in CoRL was actually some work on how we can mask out the attention in the transformer to show like embed some inductive biases by that way. So if you have a kinematic structure, maybe your joints should just attend to your neighboring joints and all that. So that was a work on CoRL here doing that.
Yeah, there's one question.
One question about compute. Maybe you can give the audience an idea what kind of compute was necessary for the board.
Oh yeah. So the dynamical model was really just trained on a Mac. So this is she didn't have any graphics card, so we trained it on a Mac in an hour. So it's actually can do pretty damn cool stuff without much money. A Mac is expensive though, but you can use any other hardware.
All right. There's another question.
Just wondering, so you like shift the data efficiency with structure, prefix, and the variables.
Yeah.
I'm wondering if you have any comments on how to achieve this example, how to quantify information on the data and select so like, for example, everything. So there's any format.
Yeah, that's a good question. No, we haven't explored that yet. So it would be nice to see more work on that. I think it's a lot of theoretical groundwork that needs to be done to figure that thing out. One thing that you could do, like with the equivariance, is that you have to embed the symmetries. It would be nice if you can actually learn the symmetries from the data. If you know that the data might have some symmetries, could the network just learn it from itself? So instead of having to embed it. Okay.
All right, then one last round of applause.
Thank you.
Where's the next? Yes. Oh, it's virtual. So our next speaker is joining virtually. I hope everything works out there. But he's online, and that was a thumbs up. So yeah. Yeah, so the next speaker is Handa. He's a research scientist at NVIDIA Robotics, where his work focuses on the intersection of perception control and machine learning for robotics. And prior to joining NVIDIA, Ankur completed his PhD at Imperial College, and he was a research scientist at OpenAI as well. His interests span a range of topics, including computer graphics for benchmark tracking and SLAM systems, as well as applying deep learning for scene understanding. And his more recent works explore leveraging GPU-accelerated physics and reinforcement learning to bridge the sim-to-real gap and vision-based teleoperation for performing complex robotic tasks. And with that, I hope you can share your screen.
Let's see.
Perfect. And can we maybe put this?
All okay?
Yeah.
Let me know when I should begin.
Can we put this sound on the room speakers?
Can you hear me all okay?
Is that fine for you guys? Okay. Yeah. Go ahead.
Okay, so my talk's going to be about exploring the frontiers of dexterous robot manipulation, but with simulation. So I think you can do a lot with simulations. I know there's been a lot of interest lately on collecting data with teleop systems. And I hope I can show you that you can do a lot with simulation also. So what is our mission here? Mission is to build a superhuman dexterity. So the superhuman part is extremely important here because we can't be limited by the human performance. And our focus is on high-value dexterity as characterized by the breadth of human utilization in manufacturing. So dexterity is working with your fingers to perform intricate, high-value manipulation as opposed to just grasping. And it requires arm and body coordination along with leg work if you're looking at humanoids for force transfer and navigation. But the key here is to really move the hands to the specific location with your legs and stuff, and then do the manipulation. And that's through leveraging the fingers to do that. I think I want to also highlight this talk that I saw a few months ago from David Silver, which was showing all the great things we have been able to do over the past few years by doing RL and self-play. And the key thing that is they're all superhuman. So while we can do a lot with supervised learning, but the recipe we have converged on as a community for more complex things happens to be RL and self-play, which is how we get superhuman performance. If you want to beat a human, you have to have some form of RL into it. So before I begin, I want to highlight some of the previous work we've done over the past 5 years. It started off with the Dex pilot work, which was when I was thinking about building teleop systems with hand and arm. At the time, it seemed like, well, we are going to have to do something beyond RL. And I started off building that with purely vision-based system, so you can move your hands around in a workspace with 4 cameras looking at it. You can track the hand and you can relay the motions over to the robot and it will do the teleop. and sort of figured out that it turned out to be far more complex than I thought. Both the teleoperation system development and the teleoping, and then learning from those demonstrations. So I gave up on that and moved towards going back to doing sim to real. So started off with Dextreme, which is basically a system that does in-hand cube manipulation inspired by the OpenAI work, and the DexPBT work that followed afterwards, which was looking at hand and arm systems to do the reorientation. So the PBT stands for population-based training. And then we had follow-ups on Dextreme FGP, fabrics guided policies, which impart smoothness and collision avoidance implicitly into the system. And just recently, we had this system that does hand-arm coordination to do the grasping of objects lying on the table. So that's basically the summary of all the, at least my past 5 years of work. So I'm going to start with Dextreme, which we developed in 2022. So I'm just going to play the video to show you what it does, and then walk you through different steps on how we built that system, and then move towards others. So the task of this is cube manipulation. Job is to coordinate and orchestrate the fingers so that you can rotate the cube such that the orientation matches with the on the bottom right. So the whole idea is to just keep doing that in the loop until it drops the cube. This was, again, done using the combination of CoRL and you can see there are a lot of places where it feels like it needs to do some deliberate movement of the cube to achieve the orientation. And it does that very gingerly and very nicely to get to the target. This one's also pulling the thumb through to rotate the cube. And no real data was used here, no teleop, just to emphasize that a bit. And we had a cube pose that was tracked by a vision-based system. So this is also an interesting bit where it gets stuck and then figures out that it has to move the cube in a different direction. Yeah, the thing recovery from where it gets stuck.
Ankur? Oh, can you We can't really hear you while the video is playing.
Oh, okay. Well, I'll
maybe
be
you
a
mute
bit...
the sound.
Okay. So just to give you the history and motivation behind it, so that was the OpenAI system back in 2018, and it had all sorts of sensors on it and shadow hand, and to do the in-hand manipulation, and they were using phase space markers on the cube to track the orientation. They also had a vision-based system, which wasn't that great. So our motivation for this work was to simplify the hardware. We believe that you could do a better, build a better vision-based system and track it using a combination of deep learning and geometric computer vision. While this system that they developed with vision was just end-to-end, where they would regress from image to the corresponding pose directly. So we avoided that. And we also use GPU-based simulation as opposed to what they do in that work, which was MuJoku-based. And we brought the time down from many months to just a few days. And I think one of the things I want to emphasize is that both examples of how scaling up simulations for context-rich manipulation can allow sim-to-real transfer. So that was basically the message. This was done with MuJoku, and we did that with Isaac Jim. But the underlying theme is very much the same. Can you use high-throughput simulation with the combination of domain randomization to do sim-to-real transfer for this context-rich manipulation task? And the answer is yes. So I think just to give you flavor of what it had, we had all sorts of state vectors that we used within the simulation, and we used RL with the combination of automatic domain randomization to scale up the system. So on the left, you see is the state vectors that go into the actor and the critic. So we had the asymmetric actor critic, so meaning that the actor would get the observations that it's going to get in the real world, and critic would also have far more than the actor and some privileged information that you cannot get in the real world. The neural network controller would take object pose, which we developed through computer vision and deep learning and geometric computer vision. It would take the history of joint angles and the target orientation, and it would provide you the joint targets. The key difference between the stuff OpenAI did and us is also the hand. If you have 4-finger hands, they're much more difficult to control or learn from, as opposed to the 5 ones. There's a lot more movement and redundancy you have. So Allegro hand learns cube rotation slower compared to the shadow hand. But the input and the output is something that's displayed here, which is the object pose, joint angles, target orientation, and you get joint targets. Pretty simple. So what is automatic domain randomization? So the key thing about here, the automatic part here is that every time you train with domain randomization, you can evaluate slightly outside the ranges of which it was trained on. And based on the performance, you can shift the ranges and retrain. So you do that for all the parameters you have, and it gives you automatic curriculum, and it's also giving you infinite data, all the data you can mine from simulations. With a classic domain randomization, your ranges are fixed. So you only get so much data, but if you adapt it based on the performance, meaning that if you're performing really well, you keep expanding. If you are not performing well in a certain range, you shrink that range a little bit, optimize for another parameter, and come back to it. So simulations also give you a way to sort of evaluate in the loop. And the evaluation is extremely, extremely fast because you're doing that in simulation, as opposed to running experiments on the real robot, which happens to be much slower. So the transfer to the real, I think it's the highlight of that result was we reduced the training time from multiple months to 2.5 days. So this was what they had with OpenAI, and this is what we had with automatic domain randomization. We beat their vision-based and state-based Excel results by a lot. They also had some results with XXL, which they ran it for multiple months. I think we could have done that as well, but at the end of the day, we saw that there's a significant gain we get by running a vision-based system alone. And the number of consecutive successes were capped to 50. Therefore, we provide these stats for 50. In our case, the max number of consecutive successes would go to about 100 or 150 at times. So that's the difference. So I'd like to show some of the other bits of the results here. This was another attempt.
Can you maybe try to mute the video?
Can you see that now? I think the deliberate movements that you see here are actually very interesting.
We still can't really hear you.
Can you hear me all okay now? Can you hear me all okay now? Okay. I guess you will miss the sound, which I like. I think I'll stop it here. I also have the high frame rate video, which I think is very interesting. It does the which are really fun to watch. I love the thumb flicking through to rotate the cube. It drops it as well. just to let you know that it's not perfect. The other one that I quite like is this one where you see the smoke coming out of it. And that happens all the time when you're running experiments on the robot. You're going to break the hardware at some point. I guess the message here is that no matter how many layers of robust software you add, you will always feel the hardware. So Allegro is still not as robust as many other robots, especially with Shadow Hand as well. So we did break it after working for it for a while, but in the subsequent work, I'll show how we can learn policies that are more gentle to the robot, and we can get much more smooth trajectories out of it, because RL by the very nature learns bang bang control, and it's not very smooth. So the next work, I think, which I want to highlight, is the work where we add fabrics to the system. So geometric fabrics is the work that Nathan Ratliff and Carl Van Wyk developed. So we added that on the Dextreme system to provide gentle and smooth behaviors that transferred really well to the real world also. And the difference is pretty obvious when you see there's the motion of the fingers, and there's also, when you do the FFT, you see the smoothness on that, which I'll show a bit later on that as well. So you see that trained policies can be pretty hard on the physical hardware, and that's mostly because it's flopping the fingers and randomly moving, and you do exponential moving average to smooth out, but still the noise is still there in the behavior. So fabrics guided policies are supposed to be more gentle, and you can see the behavior as you in the video. It's far more robust and smooth, and this work was basically all about how we can develop systems that are gentle to the hardware, and they have baked in smoothness and collision avoidance. So your standard dynamics equation with a joint PD controller gives you the torque, and you can do that. So fabrics learns another additional layer of QF and QF dot, and basically the policy is omitting F by A, and A uses the fabrics layers that provides a smoothness, second order smoothness on the velocities and on the joint angles. And that's basically what this work is about. And we show that the fabrics guided policies are just as good as the Dextreme based policies, but they tend to be really smooth. So I guess I can skip that here to show you the smoothness. So you can see that Dextreme policies tend to have a lot more noise in them, as opposed to the Dextreme FGP policies, where if you do the FFT, the behaviors, the frequencies and the amplitudes, they're pretty obvious here that the ones you learn by vanilla RL tend to be far more noisy. There's another experiment that I did on this where I was being very adversarial to the hand, and yet it did pretty well on that. So I think one other thing I would say is these kind of behaviors are very difficult to learn by standard supervised learning, but with RL and in simulation you can scale that up quite a bit, and this sort of robustness emerges out of it. So I'm being very adversarial to the hand here, and yet it's not losing the cube and not dropping it. Guess I should hurry up because I only have 12 minutes to go. I also want now, getting to the last part of the talk, is the pixels to action dexterous arm hand grasping with geometric fabric. So just to give you the flavor of what it does. The input is the depth image, and the action is basically the hold and the PCA space of the hand. For grasping, and it's able to pick up the object, quite reactive. A very funny grasp, but it did it. The other one I want to show is this, where it's following the key, box, picking it up, and that's the other one that I highlight. Like a toy airplane. Again, everything is from pixels to actions. Sorry. So what is so unique about this work? It's the first time RL for manipulation on a 23 DOF system, 7 for the KUKA arm and 16 for the Allegro hand. So jaw grippers-based robots often have the 7 DOF for arm and 1 DOF for the gripper. So this is 3x the complexity. Geometric fabrics is also fused in for inherent smoothness and collision avoidance. The other highlight is basically the end-to-end grasping via student-teacher distillation on depth images. We don't want to operate on point clouds. It's very reactive and fast and works on arbitrary set of objects. So the geometric fabrics has these design requirements which allow us to develop systems which avoid collisions. If you have different objects that you want to avoid in colliding with, you can turn them into boxes and bubble wrap the object with spheres so that you do sphere and box intersection. Self-collision avoidance, joint limiting, and the action space, inductive biases as well. So I want to highlight that. We basically have palm pose for the full arms, so sort of an end effector in that sense. And then for hand, we actually learn from the data sets some PCA space for grasping. So it's tailor-made for grasping. Often you would find that if you do RL on high-def manipulation systems, it would just have fingers going around and just to pick up the object, but you don't want that. So you want something that is power grasp or precision grasp. So we can learn that from some of the data sets that are out there in computer vision. Redundancy resolution as well. And it's all vectorized. So the first step is basically learning from the teacher information. You have all the privileged information you can get in the simulation, and we have different objects per robot. So you get object ID, which is one hot vector, and then you learn with the classic asymmetric actor critic. You turn the handle, and eventually you will learn a policy that's able to pick up an object from the table. Now the second part is basically distilling that onto directly from depth image. So you have a student-teacher online dagger-based system, which is fairly standard at this point. And we also regress to the object position here so we can visualize. So you have an auxiliary head that's giving you the object position, and then an action space basically giving you the action trained all on using an online dagger system. And then comes the real world deployment. You have a state machine. Every time you pick up an object and drop it in the bin, you reinitialize it and go to the home position and redo that process. And on the bottom right, you see that we are able to also visualize and ROS the object position. So that helps in debugging as well. So, and you have picked up when you can read the depth or the height of the object position. Say you raise the object beyond a certain height. Now it's time to drop. This was the object set we trained on. About 140 BizDex objects. We have a lot of variety in them. We also had some scaling of the object masses and everything done to add more diversity. And this is now different behaviors that we show. And you can see that having an auxiliary head that gives you the object position is actually very useful for debugging. We don't really use it for anything else other than debugging to make sure the network has learned something that we can visualize. Again, this exogenous disturbance handling is something we also did by network external four-stalk perturbations. So the speed control, you can also change the speed at which it's able to move and grasp an object by changing some parameters in the fabrics. So that's inherent, which is often very difficult to do with the standard RL policies. If you train and with an EMA of 0.9, it's not always possible that it would work with 0.5 if that's your way of slowing down by averaging. Here it's much slower, so you can see how slow it moves here, but without changing the performance significantly. Again, you're getting depth as an input. I didn't mention it here, but we also simulate noise, depth noise in the simulator when we do the student training. But that's pretty standard at this point, so I'm going to skip it. Generalization to soft objects. He wasn't trained on this, but yet because the behavior is all about power grasping, it's able to do reasonably well on soft objects as well. And this is the full video of sped up by 8x. You can see it has these retry behaviors as well. And it's just one run, not many runs stitched together. Okay. So some parting thoughts here. Simulations are a path towards building high dexterous systems. Majority of the grasping systems today use simulators to train, especially the geographers ones as well. And personal experience has been that getting teleoperation data from more complicated manipulators is extremely non-trivial. The system I developed 5 years ago with the Handa teleoperation, it was a lot harder to collect data, and perhaps there's a better way today, but I sort of was one of the reasons why I moved back to doing RL. So RL is a recipe for superhuman performance. Most superhuman systems today use RL in some form or the other, including the ChatGPT-based system. And BC is a special case of RL. Other thing we learned from the last system is that direct end-to-end dexterous systems that map pixels to actions are really robust. And I think it's basically the future, given the nature of diversity we're going to encounter in the real world. So with that, I will end my talk.
All right. Do we have questions in the room? Yeah, there's one.
I think I can't hear the question.
Oh yeah, I will repeat it. So the question was, what strategies are you going to use in the future to push this even further?
I think I mentioned about self-play and RL. I think one of the things that has been underexplored in robotics is self-play. There was an interesting paper from OpenAI in 2019, Alice Bob doing self-play to do the grasping and or goal reaching as well. So I think that's one thing that we would like to explore. As you may have seen with Alpha 0 and Mu 0, self-play was crucial. And I think that area is still underexplored in robotics, and that I think will require interesting work in simulation development and training as well. So that's one thing we'd like to explore. I think it's also possible that you're going to have to do, if you want to do some functional grasping, you're going to have to do deep mimic style stuff as well. And that's something we are also exploring, but not by collecting zillions of demos, because for anything to do with hand and arm, demo collection becomes very difficult. So these are the two areas I would highly recommend spending time on as well. I think we should learn a lot from the rise of alphas from DeepMind. Those things have been underexplored in robotics, and perhaps it's time to revisit them and apply those ideas here.
Okay, so then I also have one more question. We've seen a trend at CoRL that people are first pre-training on data and then using highly curated data sets to fine-tune. And with simulations, it feels like, especially with context, we're having a rough approximation of what contexts are in the physical world, but people oftentimes complain that they are not really accurate. So the question is kind of, is there value in having a high precision simulator, or do you think that just having enough randomization kind of deals with the problem without having to be too realistic?
I think there's certainly value for real world data. Oops, sorry, just gonna switch off. I think there's a value in real world data for pre-trained backbones, but I think if you want to do evaluation and scaling up, that will only come from simulation, even if the simulators are not super accurate. But I think we are going to be developing over time more accurate simulators. GPUs are going to get better and better over time, so you can simulate a lot better as well. But I think overall, the kind of robustness you get by training in simulation is very hard to get in the real world. And I could see basically BC and RL coming together, where possibly for distillation, you can use a pre-trained backbone, but you have a lot of these skills that you're trained in simulation, and you're trying to do multi-teacher student compression. I think there's interesting work called ManipGen, if you haven't seen it, which is doing something along those lines and putting together VLMs as well on top. So I would also say LLMs are also looking at now synthetic data. So there's another axis to be explored. But I think there's a belief that you cannot scale simulation because somebody has to create the environments, and you have to make sure that things are very stable, etc. But we can learn a lot from all the content creators who've done amazing work in graphics for about 30 years or so. And there's a huge amount of data we can explore from there. You know that today graphics is also learning from games and super sampling and stuff. So I suspect we will use some real world data, but I think a lot of data will come from simulation as well.
All right, then one last round of applause.
Thank you.
And thank you, Ankur. And with that, we are heading into the coffee break, I believe. All right, so it's half an hour, and then we'll be back. Oh yeah, and the poster sessions are happening on the second floor.
Test. 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 It's a bit. Is it loud enough? Yeah, you can tune it. So now I should be louder. Even louder. So test. Is it better? Hello. Slow.
So hi everyone. Just turned on. Oh shit. So hi everyone. Welcome back. We now have our fourth speaker for today. His name is Carlo Sferrazza. Carlo is a postdoctoral researcher at UC Berkeley, working with Professor Peter Abil. His research focuses on advancing humanoid intelligence by incorporating priors, inductive biases, and multisensory feedback. Carlo obtained his PhD from ETH Zurich in 2022 under the supervision of Professor Raffaello D'Andrea. During his doctoral research, he worked on the design of vision-based, data-driven tactile sensors and the applications of such sensors to robot control and dexterous manipulation. His PhD thesis was awarded the ETH medal, and in 2022, he was selected as an RSS pioneer. He's also the recipient of an SNSF postdoctoral fellowship, the best paper award at the 2020 International Conference on Soft Robotics, and the 2017 ETEL award. I think his research is very related to the topic of this workshop, and I'm very much looking forward to your talk.
Thank you for the kind introduction, and thanks to all organizers for inviting me. Actually, very much like the topic of the workshop, and I also like the title, which acknowledges the fact that we really have a world with an abundance of data, and I took the liberty to make an addition. This data is not only abundant; it's actually heterogeneous and very diverse. So what I mean is that we all know that interacting with the world is a multisensory experience. I think we all agree that touch, audio, smells, all senses are kind of complementary to vision. But this is not only true for humans or for animals, but it's true in robotics too. It's been shown repeatedly. And if we go back to ICRA 2019, there is this very seminal work in the group of Jeanette, actually animation was on the paper too, where that name was making sense of vision and touch. It was really about understanding what is the advantage of using the sense of touch in addition to that of vision. And there have been like a lot of papers kind of building on top of that. Most recently, Manuel Vieira CoRL from Shuran's group, where they show like how audio data can integrate in the rich information that we get from vision about the environment. So there is a repeating pattern in these papers, and it is that of showing that we have a full model of a lot of sensors that achieve a certain performance. And in the moment you start removing some of the sensory information, the performance starts to drop. So there's kind of an agreement in the community, I would say, that more sensors help and less sensors lead to reduced performance. However, if we look at the general scheme of modern robot learning, where we try to achieve this kind of generalist robot policies that can be reused across tasks, we very rarely see the use of other observation in addition to vision. So as you all know, usually these tasks are described by language instructions. We might have even multiple views of images, and we're trying to get some actions out of it. But again, like touch, sound, other senses are never part of this scheme. So the question that I'm trying to answer with this part of the talk is really why aren't we using other sensors? I put down two reasons, and I think actually they are the most important here. One is obviously these generalist policies usually rely on large robotics datasets. And these datasets are usually containing vision, observation, language instructions, and actions. It's very hard to go beyond that because it's kind of a chicken and egg problem, right? Because we don't have adoption of other sensors in the community. It's hard to have people put these sensors on the robots when collecting data. But I have to say, like, even in the few attempts at collecting these larger multimodal datasets, there is an issue, and the fact is that vision tends to be a much denser signal than audio or touch. For example, touch is only kind of active when there is some contact, but often we have no contact in the scenes. So what happens is that when you collect these data sets, there is a huge imbalance in the data distribution, where you have a lot of signal from vision, but very little from audio or touch. So what happens is that when you train models from these data sets, what happens is that these models over-rely on vision and tend to neglect important information from the other sensors. So we're trying to address these challenges in the work I'm presenting today. It will be on-site as a collaboration with other people at Berkeley. Actually, Oyer is on the paper too, and among the organizers of this workshop. The paper is not an archive yet. It's going to be very soon as we're finishing up some stuff, but there is a QR code if you want to look at the website, and there is a link to the current version of the PDF too. We call this work Fuse. The idea is really to fuse heterogeneous sensor and generalist robot policies. I'm going to explain you the context in which we do it. We have a pre-trained generalist policy. I'm going to touch a bit more on what that is. That can be Octo, for example, for people in the field, but also other larger VLAs. The idea is that we want to fine-tune this generalist policy by using a much smaller data set of observations, including vision, touch, and audio, and described by language instructions. The idea is that maybe we can solve some tasks that are harder to solve with vision alone in a better way, with higher performance, but we also want to enable additional capabilities compared to those that can be achieved with vision alone. For example, we could prompt the policy with tactile attributes, for example, grab the object that feels coordinate. Or we could use a multimodal prompting, so prompts spanning multiple modalities with different attributes from touch, sound, and vision. If we have some generative capabilities in our model, we could also ask the policy to generate some tactile attributes corresponding to the objects that it is feeling at the current time. I'm going to go more in details in all these tasks, but the two main points here is we want to improve performance on some tasks, but we also want to unlock new tasks that weren't possible otherwise. So one step back, the core of our work is a pre-trained generalist robot policy. So was that, again, we have usually a transformer policy that takes in usually multiple tokens, could be, in the classical case, it's vision and language tokens. We usually have some readout tokens that attend to all the other modalities and are used in an action head that is usually trained by minimizing imitation loss. The idea of this setting is that you train a very large data set and we can generalize maybe zero shot to other tasks or with some little amount of fine tuning. So the point of this work, though, is that can we actually leverage new sensor modalities in this setting while retaining the generality that we achieved during pre-training? Pre-training usually is achieved in the order of hundreds of thousands of robot trajectories. So when I look at this kind of multimodal data sets, so that's how I pictured them. Yeah, there's this different modalities, clusters of modalities in our data set, for example, vision, audio, and touch. What we want to do is our model needs to connect all of these. So the way we approach this is by doing something that we're very good at doing in the Bay Area, which is building bridges. And in this case, the bridge is made of language. So the idea is really have language instructions act as a glue across modalities to have our model reasoning across all of them. This is our recipe that we call Fuse. We have a multimodal transformer. This is a transformer that can be pre-trained on a subset of modalities, but then we augment with additional modalities at fine-tuning time. It's similar to what I showed before with these reader tokens that go through an action head. That's actually the main loss of our approach that minimizes, again, imitation discrepancy. But we have also two auxiliary losses, and this is actually very important in our approach. We have a contrastive loss, a generation loss. The point of these losses is really to tackle the issue I was mentioning before, the fact that often vision dominates during training. And I'm going to go more in detail into both of them, but the idea in general is that the contrastive loss makes sure that we align our observation embeddings with all possible instructions that could possibly describe them, while the language generation loss aims to make sure that the observation embeddings that we get at the output of the transformer are sufficient to reconstruct the instruction that could be related to this. So more in detail. So I think this part probably needs a bit more time to digest, but basically the contrastive loss is computed the following way. We have a readout embeddings that we obtain by attending to all modalities except language, and that are fed through this transformer. And then we use these embeddings and language embeddings to compute a clip loss for all possible combination of instructions that match this combination of modality. So in this case, like all the ones here, for example, pick the object that feels corded or pick the object that looks blue. This is, by the way, for example, for a blue rope. These are going to be positives, and all the other instructions in the batch are going to be negatives. So we pull together the positives, and we kind of maximize this alignment with the negatives in the batch. So that's the contrastive loss. The language generation loss requires an additional component, which is a language generation head that we add on top of our model, just used for this auxiliary loss in this case. We have, again, readout embeddings that are fed through the transformer. Here we do it for all possible subsets of modalities that we have in our datasets. For example, we could have wrist images and touch. And now we get some readout embeddings, and then we have our corresponding language instructions. So what we try to do is make sure that we can generate that instruction from the readout embeddings. So this way, again, we make sure that at the output of the transformer, we have all information that we need to describe the task. So we don't ignore any of the modalities. So how do we evaluate this? The first thing, we need a data set, and we actually collect a pretty considerable sized data sets, about 30,000 trajectories. It's much smaller compared to what you have in vision language data sets. For example, the OpenX mixture that we used for training Octo in this work is about 800,000 trajectories. So this one is much smaller, but still pretty decent sized. It's about 800,000 data points in comparison, and they contain third-person wrist cameras, views. We have 2 tactile sensors. These are digit vision-based tactile sensors. We have a microphone attached close to the gripper. And we have also IMU data that we don't use for these applications, but we provide them to the community for future usage. So all of this is going to be open source together and released together with the models, the code, and the results next week, most probably. So the tasks that will contain this dataset are mostly 3, all language labeled. We have like grasping and a tabletop scenario. We have a much more difficult task of grasping inside a shopping bag. You see these are all the diversity of objects that we have. And we also have like a task where we kind of press some sound buttons. So these are buttons that have different colors and play different sound. So first thing we do is compare with the obvious baselines. So we want to compare our approach, which is fine-tuning using iRise recipe Octo-based model. We compare with fine-tuning Octo just using vision, so neglecting information from the other sensors. We also compare with training Octo with all modalities, but from scratch. This is a pretty weak baseline because Octo is a pretty large model and we have a very small data set. So to be a bit more fair, we also trained a resonant model from scratch where we use film fine-tuning for injecting the language conditioning into the policy. We see on the bottom the results, especially the last picture here is the average result. You can see that our approach performs much better than the other baselines, but this is especially true in the shopping bag task, where we have a lot of partial observable scenarios when you use vision alone. Well, the bag becomes very dark and the objects are not very visible. You can see our model in action actually at the top, where we ask the policy to grab the yellow block and you can go inside the shopping bag and take it out. And the importance of the 2 auxiliary losses that I was telling you before is actually very true for the shopping bag. We are actually twice as better in terms of success rate. By the way, the shaded color is about finding the objects, while the darker colors are about actually grasping them. And you see that in a partially observable scenario as the shopping bag, both of the auxiliary losses help. If you remove any of them, the performance drops. So these are things that somehow the vision policy could have done, but it does them in a worse way. Now, what are things that the vision policy couldn't do at all? So one thing is a zero-shot touch description, and we are using here our generative head that we actually implemented for the auxiliary loss, but it can be used also at inference time. For example, we can have the robot go inside the shopping bag, pick an object or different objects. We have some tactile readings, and then we're going to ask our generative head to generate the possible instructions for this kind of readings, and they will detect that in the first image, the object actually feels fibrous, in the second image, it feels slick. More interesting, a multimodal disambiguation. You can ask the policy to grab an object that looks yellow, but there are more yellow objects on the scene. So you can also add a tactile attributes, for example, feels squishy or feels crinkly. And the policy now has a feeling of what the tactile attributes feels like, and then it goes to the right object and pick them up. We had some other experiments that we called cross-modal compositional reasoning. The idea is really to reason across the whole range of modalities. For example, this setting here, these buttons are all present in the training set. So the policy kind of knows what color is associated with what sound. So for example, the green button would play metal. And so if you ask the policy to grab the object that is the same color as the button that plays metal, then the policy right away goes and pick up the green object. So this is kind of easy because you could say like, okay, if these are only training buttons, maybe during fine tuning, the policy just remembering that it should associate green with metal. So we took this a step further and did a more complicated cross-modal compositional task in multiple steps. I'm going to play this multiple times. So if you don't get it the first time, it comes again. It's a bit subtle, but I think it's pretty important. So we're gonna try to introduce some test buttons in the scene. The blue and the red buttons were not in the training set. So what we're gonna do is first ask the policy to push the blue button. So it's gonna go there. And I hope the sound plays. So it's gonna listen to the audio. And now we're gonna ask the policy to generate the corresponding audio description using the generative head, and that tells it like push the button that plays piano. So again, it has some understanding of audio. By listening to the audio, it can reconstruct language extraction. Now we're going to take the language extraction and we're going to feed it again to the policy. And this time, the policy will interpret it as go and push the button that was seen during training that played piano. So we'll remember that's the pink button. And you can listen to the piano played by the pink button. So the model really successfully correlates audio and vision, and repeating this, effectively, this is equivalent to asking the policy in multiple steps, push the training button that plays the same sound as the blue button. And we do, again, this in multiple steps. First, we go in the blue button, we listen to the audio, and then we generate the corresponding extractions, and then we look at the training buttons, and we find the one that was playing the piano. By the way, these are different pieces of the same song, right? So it really has an understanding of what piano means, although it's the same song. So takeaways of this project is really that generalist robot policies can actually be fine-tuned with much smaller datasets made of multisensory data. This results in better performance across some complex tasks, but also enables other tasks or capabilities like multimodal prompting. Something I haven't shown, Fuse is actually applicable to a variety of VLA backbones. These are some preliminary results. We have a much larger VLA based on polygemma models that can basically do the same things with the same recipe. And this is just some showcasing results, but in the final version of the paper, you see all of this in greater detail. Yeah, again, here's the QR code. So switching gears a little bit, we've been talking about a case where we have many sensors on a robot and what are the nice things we can do with them. But looking a bit broader and looking at more like mobile by manual manipulation, often we have many more sensors because we have vision, we have touch, but we also have joint angles, and these are often distributed across the entire body. But we also have a numerous number of actuators. We have joint commands, but we also have a lot of hand commands if you think about dexterous manipulation. Again, there is kind of a specific placement of the sensor over the entire body. So what we're asking ourselves, can we use this notion of locality to actually make the problem a bit more tractable given this high number of both sensors and actuators? So can we actually leverage locality in a transformer setting for policy learning? And if you look at transformers, they are built on this self-attention mechanism, which was designed to deal with a global relations across sequences. And these sequences are often structured like language, where the first word can be very related to the last word in a sentence and so on. While animals are a little bit different, there is this notion of spatial connectivity of the way our neural system is routed. And that allows us to have things like shorter loops, or what we call reflex arcs, where we have some very fast reactions at the level of our spinal cord to really react very fast to interactions with the environment. So what to ask ourselves is this just an evolution artifact, or can we actually use locality as a powerful inductive bias for policy learning? That's the motivation of this work, Body Transformer, that we presented at this conference. And the idea of Body Transformer is to have an architecture that just biases the vanilla transformer to take into account the structure of the robot body. So in practice, what we do is we treat the robot body as a graph of sensors and actuators. So we split our observation and our actions across the nodes of this graph. Then we make sure, using masked attention, that at every node, at every layer of the encoder, every node only attends to itself and the direct neighbors. And then the next layer, we're going to do the same thing. And then our receptive field, or our information, grows across the graph, and the information again gets pulled to all the nodes. And finally, we decode actually the actions also locally at all of the nodes. We have two versions of this architecture. One is called BOT hard, which only uses its masked attention layers. And we have another version that would be more clear why we have it. BOT mix actually interleaves masked attention with the regular self-attention layers. The way we build these masks is the following. Here we have an embodiment graph, let's say a humanoid. We've just built an adjacency matrix out of the graph. We add ones at the diagonal because we also want to do self-attention at the nodes, not only look at the neighbors. We evaluate this in different settings. First, imitation learning. This is a pretty large imitation learning benchmark, which contains humanoid tracking motions, all action labeled. It's about 800 different motions or tasks, and they're split in a training and test set. What we've shown is that Body Transformer can actually outperform the baselines, specifically Transformer and NLP baselines. And the interesting thing is that this gap actually becomes larger when you look at the validation set. This benchmark, people thought it was kind of saturated because it's pretty large, and so it's quite easy or stable to train. And the best results before were obtained using this multi-clip policy, which is pretty fancy structure with a recurrent neural network that estimates a latent variable describing intent, and that's fed usually to a BC pipeline. Well, what we did is just using classical BC end-to-end just with the right architecture. Another exciting thing here is that if we look at scaling this model up in terms of the number of model parameters, we can see that the transformer in red actually overfits pretty quickly, while our architecture keeps scaling nicely as long as we scale up the model. So we see a similar trend in a low data regime where usually people tend to use NLPs in imitation learning because transformers would easily overfit when you have a small number of demonstrations. And what we see instead is that our approach is either competitive or better than the NLP and consistently better than vanilla transformers. We see similar improvements also in reinforcement learning. Here things are a bit more tricky because our kind of hard constraints on the bottlenecks of our architectures are a contrasting objective compared to just achieving exploration as fast as possible. So for hard exploration problems, we noticed that it's actually beneficial to add some self-attention layers interleaved with our mask attention. So this way, the global information is pulled through the graph a bit earlier during the pipeline. And that helps in achieving the top performance on these harder exploration tasks. To demonstrate real-time applicability, we also deployed this on a real system. This is nothing fancy. It's really like a blind policy transferred from sim to real, trained simulation using reinforcement learning. Another interesting fact is actually the Body Transformer can achieve much better computational complexity compared to vanilla transformers, because you can imagine like there is a very big sparsity in the attention metrics, and that usually brings at least like a 2 times reduction in the computational cost compared to the vanilla attention. So some takeaways. First one, and probably the most important, is that inductive biases matter for policy learning. And that's also very true for a single embodiment. People have been trying to use graph across multiple embodiments, but actually what we're showing here is that the graph bias is actually also important when you have one single embodiment. That doesn't mean that it cannot be applied for cross embodiment, but that's the message of the paper. The way that our inductive bias works is by leveraging physical agents as graphs of sensors and actuators. And this way, body transformer can outperform the baselines, showing a scaling trend, which is promising, and has potential for faster computation. If you're interested in this kind of problems with a lot of sensors, a lot of actuators, actually we developed the benchmark. It's called the humanoid bench. The idea of this benchmark is to have like a lot of different tasks tackling different challenges. So we really put a lot of thought in what tasks enable dealing with different challenges. We put a lot very flexible observations. We have egocentric vision, all body tactile sensing, higher resolution of the fingers and the feet, lower resolution everywhere else with proprioception, 61 actuators, so very high degrees of freedom. It's open source, feel free to try it out, contribute to it. There is a lively community already built around it. Yeah, we're very excited about it. With this, I'd like to thank all my colleagues and collaborators on the projects I presented, and happy to take any questions.
Your audio signal, is it just audio or all the direction you can recognize where the audio signal comes from?
Yeah, no, it's a mono microphone, actually. It's just a single channel microphone, and we just build a spectrogram out of it of the last second of data. And yeah, we don't have information about direction yet.
But it's what modality in sense of which does something, especially if you stay up at night to get some water, you do not have to put on the light. You just hear of your own actions and echoes where to go. So you have a kind of audio 3D reconstruction, and you have to know where the sound comes from. So
it's a great point.
You use mono.
It's a great point, but we use an action sequence as well. And so we don't use just a single step in our policies. Our policy is conditioned to previous steps and actions. So you can kind of get a sense, depending on how your robot is moving or where the sound is coming from, looking at the sequence. We don't see it instantaneously, I agree, and you could use a stereo microphone. We just took the cheapest on Amazon. That's actually the real choice.
Any more questions from the audience? Actually, I also have a question, also regarding the multimodality that you use. So I would assume that for your tactile sensor, the signal you get is very specific to that sensor that you use. I mean, for cameras, you can have different types of cameras in your data and still use them for training, even if your camera is different. How is that for tactile sensors? Can you really only use that data if you have the same sensor?
Yeah, that's a great question. I would say, like, in tactile sensing, there is the issue of heterogeneity even within the sensing modality. So if you have a completely different tactile sensors, it might be tricky, and you probably need to project things in a shared embedding space. And there are works that have tried that successfully. So there is promise there. For what regards this work, we don't use only 1-digit sensor or 2-digit sensors for data collection because sensors break during like such large data collection effort. So just the simplest way you can do this is performing background subtraction on the images so that you are in a more similar space across sensors. So that if there are some differences during fabrication, those are evened out. And then what turned out is, I think in our datasets, we have like about 6 sensors for data collection. And it turns out that then it generalizes to all other digits that we've been trying.
Maybe one other question.
Just one short. How does it correlate the tactile sensor with squeaking property with language? I didn't get that part.
Yeah, because during training, we have labels that are like made their way. We have a very large degree of labels. We do use like in language model rephrasing as well, so that we add some synonyms and so on to get like really grounded in language. And that turns out to actually help, yes.
Then thanks again to our speaker. Now we have the first panel discussion.
Yeah.
So we have 2. So one for Zoom or audio in the screen. So maybe you can. Yeah. Yes, I think we can give them one.
Both of them like this?
Yeah.
All right, this is going to be a bit complex, but maybe you can just share these two and pass it around the table.
Oh, and we have to talk into both of them, of course.
Keep them together. 24.
Maybe then.
Yep. Yep.
I guess we can probably just put this on the ground and just pass this.
Okay. All right. So welcome to the panel. Maybe a quick check. Ankur, can you hear us from Zoom?
Yeah, I can hear you all okay.
Okay, nice. Very nice. So yeah, welcome all to the panel. Yeah, I think we have seen different visions for training dexterous manipulation today. And so I would like to start the panel with the question, if the answer is imitation learning with scaling data, then what's the role of RL in training robot policies for human-like skills? And I would like to start this discussion with Sergey and Ankur, because I think your approaches differ significantly here. So yeah, maybe Sergey, have at it.
Okay, I feel like I've been put on the spot. Okay, I think it's a good question. And you know, the way that I would provide, oh, is it not on? Going to do something?
No, yeah.
Oh, okay. Oh, okay, there we go. All right, so there is like kind of a simple answer and then a more complex explanation to explain why we're in the situation that we're in. So the simple answer is that a good RL algorithm should be able to do everything that an imitation learning algorithm can do and more, meaning that if you have a good offline algorithm that can also be used for online fine-tuning, then you would just plug in all the same data, all the same architectures, and get back a better solution, and one that you can then fine-tune with online RL. The reason that these days you see a lot of really great results with imitation learning is a confluence of a few different factors. One is that the RL algorithms problem is a harder problem, which means that especially when we start going to larger data sets, more complex tasks, we need to work harder at developing algorithms that are stable in those regimes, and things like hyperparameter tuning, it becomes more difficult. But the other side of the equation is that in some ways, when we're doing the kind of robotic manipulation that we're doing today, the RL methods also are a little bit less necessary. Like if you're in a setup where it's very easy to teleoperate a successful execution of your task, then maybe just there's like kind of less pressure to figure out those tough algorithmic problems. But it's not the case everywhere. Like you could imagine that maybe you have a problem where it's not a robotic arm under teleoperation, but it's like a swarm of 100 quadcopters constructing a building, right? Like for that, it's much harder to imagine a purely imitation-based approach. So that's kind of the explanation for where we're at now. And I think maybe the way to contextualize is that for the kind of the development curve for RL, it's still at the stage where there's like a lot of algorithmic ideas that need to be invented to make it like truly practical. There's some good foundations and good ideas, but more work to be done. For imitation learning, it's a much more mature technology, which means that if we're looking at applications, especially complex dexterous tasks, it makes more sense to go with a more algorithmically mature area.
Okay, so maybe Ankur, what's your perspective on that?
I think it's a very good answer that Sergey gave. I have very similar opinions, except that obviously I'm working on slightly different set of problems. I think at the end of the day, I mean, Sergey gave an example of the building construction and stuff, and I was going to give example of car manufacturing, building airplanes, going to Mars. You can't get teleop data for those things. So if you're working on completely different set of problems where teleop is very costly and sometimes impossible, you're left with just an RL-based approach as long as you can simulate. So I think BC has certainly become very powerful, but if you think hard about it, most of the systems are going to have to use RL at some point or the other for robustness. If you're looking for superhuman performance, I highlighted that by citing David Silver's, that slide, The Rise of Alphas. I think that's where self-play and RL can play a huge role. Obviously, it depends on the fact that you can simulate it. But I think there's still so much to be done with what we have in simulation, what we can simulate today. So BC will still be a powerful, or I should say, lower bound that RL has to achieve. But of course, RL comes with all sorts of knobs that are very hard to tune. And there is still a lot of algorithmic stuff to be done on that, as Sergey said as well. But yeah, but BC has got to a point that you cannot ignore the results. I mean, you have to have your head deeply buried in the sand to say that BC is not going to be any useful. But I think BC needs RL as much as RL needs BC. So that loop will remain. So that's my answer.
All right, thanks a lot. Then
sure, yeah. Maybe I can just be loud enough. One of the interesting things that we saw in the development of foundation models is that despite having a lot of data in other domains, whether it was vision or language, we saw very good performance, but that was not always translated to what you would call large-scale viability as a product. And the amount of work needed on top of that was non-trivial in different fields. Now, given that we have already seen that in other domains, what evidence do we have that, first of all, building a foundation model is already tricky in terms of how to get the data and how to build something like that? But even if we were able to get there in a year or so, what tells us that it would not be, let's say, it would not plateau at 70 or 80% at some data point, and then we'll have the last mile problem yet again. And maybe this time around, let's start with Carlo and others. Please feel free to jump in. Yeah.
So yeah, I think like along the lines of what Sergey was saying, RL is good at certain things. It's less good at others. I think if I think about that, like if RL is not good to get to the 80%, it might be good to get to from the 80 to the 100, because it's been shown to be very good in the local regime, right, where you already have some kind of primitive behavior or like local behavior, and then refine there around that to get maybe to superhuman performance, or at least to match human performance. So I think it's going to be quite important to do something like that. I think RL has also been shown to be pretty good at robustness, for example, in the locomotion setting. And I think a lot of the failure cases as we see today is also because of this missing robustness in the failure cases. So I do see like a potential for online exploration, online fine-tuning to actually cover the long tail of things that we don't experience in our data.
But there seems to be a catch-22 here. The catch-22 is RL is only applicable if you have access to a simulator. If you have access to a simulator, then why do you need the data? Because data from humans is very expensive. You can just do RL to begin with. And in places where you cannot get data, what evidence do you have that the simulator is actually good enough?
Yeah, actually, I should have clarified. I didn't mean like RL with a simulator, because I think that's actually what we need to get from 0 to 80% of RL. But if you want to get from 80 to 100%, it might be sufficient to do it in the real world. Okay. Then the question is, how do you get the reward? But there are many ways to do it. You can use the foundational models for vision and language that you've mentioned. Maybe those will give you some help in that direction.
That's wonderful. Anyone else has a comment on that?
I think to kind of address your question at a higher level, I think that, so the topic of this workshop has to do with massive data, right? So perhaps one way I could interpret your question is, if we get to like 80%, and it seems like we're stuck at 80%, what do we do? Do we go for even more massive data, or do we go for something else? And I think it's a really difficult conundrum. This is not the first field to face that conundrum. And there are some very bad decisions that could be made. So if you imagine that you go back in time to when like GPT-2 first came out, and you are, maybe building some like natural language tools or something, and you look at this saying, okay, this is pretty cool. Like it can generate like good stories about like unicorns in South America or whatever their demo was, but like it's not going to like answer queries or help with search. So what will I do? Well, maybe I'll build some kind of fairly complex logical and symbolic system around it to like hook into this thing in the right way so that it can do like search or something. Well, that would have been probably a mistake at that point, because if you had just waited a number of years, then instead of GPT-2, you'd have GPT-4, which would have much greater capabilities. and perhaps a lot of the work you would have done in the meantime would have been obviated. So there's a very and that's not to say that that's always the wrong answer. Like sometimes it is the right answer, but there's a very difficult call to be made as to when you kind of double down on the data-driven stuff versus try to like put in place some kind of like training wheels and crutches to get it to work. And an example of a place where maybe the opposite decision has proven to be at least so far very good is autonomous driving. So in autonomous driving, you can take a Waymo for a taxi ride in San Francisco. I don't know exactly what the Waymo is running. I know some things about it, but it's certainly not running a fully end-to-end stack, right? So that's not to say the right answer is always one thing or the other thing, but we have to be very, very thoughtful about it. And we shouldn't just jump to the conclusion that because a particular system has a limitation, we need to build crutches to get around that limitation, as opposed to developing new ideas to better use data. We also shouldn't jump to the conclusion that we should always just use more data.
It's a very measured answer, doesn't it?
Maybe something along the lines, in many fields of ML, people are talking about emergence and emergent behavior. And I guess this is also what has driven the success of GPT and was the step from 2 to 4, where we have seen all these emerging capabilities by just scaling the models. But we have also heard talks today in robotics that we know a lot about our systems and that we can introduce these biases. So my next question would be, do we just scale the data and wait for emergent behaviors in robotics, or does it make a lot of sense to include these physical priors that we have into our models? And maybe, Jens, you can start with that, because I guess you are the expert on that.
Well, well, I think what we have seen already is that scaling seems to do a lot of the work. So I don't know if we need to embed the physics-based priors right now. Well, Carlos already showed one way to do it, and it seemed to work fairly well. But maybe when we hit the sort of limitation of scaling and all that, it might make a sense to look into how we can embed this physics priors. But one thing that we could do already is to look into equivariance, which I talked about. Like many of the works so far has not really thought about equivariance, like symmetries, and we have a lot of that in robotic data. So I think we could use that.
Ankur, you're online. Do you have any thoughts?
I think I'd like to go back to Aloha Unleashed paper. That's a good case of study where they scale up things by collecting 26,000 demonstrations, and the success rates are still somewhere hovering around 70%, 75%. So it's not, I mean, you can scale up more by making it 26 million demonstrations of stuff if you want to do. But going back to LLMs as well, we're seeing a fundamental limit to what we can do by just scaling. And sort of, there are things that look like there's an emergence, but they also fail really, really badly. I mean, there's still examples of 9.11 and 9.8 comparison, and LLMs still seem to be bad at comparing them. What I don't know is what sort of priors you might need. I think if it's like going back to physics and adding priors, that doesn't sound like a bad idea. And exploring simulation in that context seems like also a pretty good idea. But I think I would be careful about emergence here right now.
Yeah, I can comment on it. And actually, I can give you my experience when we were working at the body transformer. People from computer vision would always say, like, inductive biases are going to bat you back. And I think there is a subtle difference between different types of inductive biases, because sometimes we think of end-to-end systems as convolution neural nets or transformers. These are also strong inductive biases. The difference with the type of inductive bias that are going to bat you back is that these ones don't limit the representation power of your architecture. So they leave you complete freedom, and they're still universal approximators. So if the inductive bias is there to guide the learning, then go for it. If it's going to constrain your learning landscape, then it might be not a very good idea to use that. Same thing goes for priors. I think like physics priors can be used, for example, in simulation to generate new data. They can be used, for example, through videos to get some initialization and be in a better initialization region for your training. So I think there is definitely no harm in using any of these. Of course, there are better inductive biases and worse inductive biases. but those that don't limit your learning, I think have almost no harm.
Ilya Sutskever has had an interesting saying, which is that inductive bias is training data in disguise. It's a statement that when you think about it, has a lot of depth to it. In research, especially academic research, we have an inductive bias of sorts, which is a bias towards coming up with new methods, right? If you come up with a new method, you publish a paper, that's a good thing. And when you have something like methods that add structure that reflects physical properties, there are many, many different ways to do it. So there are many ways to create new methods that way. And what Ilya's saying kind of gets at is that very often when we take methods like that and we increase the amount of data, the benefits become smaller and smaller. And that's what it means to say that inductive bias is trained data in disguise. Now, we should be very careful with that statement because, of course, that doesn't mean that we shouldn't change architectures, for example, in various ways. But if you look at the kind of architecture and model changes that have been most effective in the past, many of them, they're all inductive bias because that's literally what a neural net architecture is, but it's not inductive bias towards putting direct kind of world knowledge into the system. It's inductive bias towards kind of properties of effective learning processes. So it's a very kind of meta level thing. If you look at things like batch normalization, even just the structure of transformers, like all these things, they're not really building in world knowledge so much as that they're making things more learnable. And I think there's a lesson to be gained from that. The lesson is that we should think about inductive biases insofar as they make it easier for us to use data rather than supplant data, so that we don't end up essentially providing training data in disguise.
Want to add to that before we move on?
Okay.
We have some questions from online.
Yeah, let's get to that.
Yeah, we also have some questions from online that I want to ask. So one question is, what is the significance of memory or context length in robot foundation models? Currently, the VLA models typically have extremely short or no memory.
Who is working on VLA models?
Yes, and I think that is very sad. So there's like a good reason and a bad reason for it. So one might think that the good reason is that long context is hard, and if you have lots of images, then you need even longer context. So there's like some systems challenges, and big companies with lots of GPUs and TPUs will surely figure out a solution. But there's actually a more subtle issue, which is if you start adding history to a policy trained with imitation learning, you can make your policy a lot worse. Why? Well, because in the physical world where things tend to be mostly smooth, the current action is strongly correlated with the previous action, and the previous action is strongly correlated with the current observation plus the previous observation. So you will easily get policies that simply copy what they were doing before and not actually perform the task properly. This is something that folks like Drew Bagnell and his students have studied extensively. It's also something that my students studied in a paper called Causal Confusion. You can interpret this in lots of different ways, but roughly speaking, what it means is if you add history, the model has more ways to cheat and get a high likelihood without actually solving the task. This is really an algorithmic problem. Like there's surely a solution that we can come up with. There's probably some clever technique, and certainly there's papers proposing various techniques that can get around this. But that's actually the real reason why we don't see more policies with histories, because it usually makes them worse. And by the way, that's a BC problem with RL. You can make it work. So one way to solve it is to use RL.
Very short comment. I second what Sergey said, and it's actually a big issue when learning from tactile sensing or sparser data. What you saw today is that the policy, when you give it tactile attributes, just goes directly to the object. So it uses the knowledge of the tactile attributes, but it doesn't go and poke the object before actually understanding whether it's the right attributes or not. And that's actually a side effect of using a short history. It's very, very important for sparse sensory data, and it would be nice to figure out a way to do it. As Sergey said, we haven't yet, I guess.
Okay. In the spirit of massive data, and all of you have worked on different sizes and different types of problems, generally, scaling up data itself is non-trivial. Often you have to do trade-offs between quality, diversity, diversity and scale. Could you comment on, based on your experience, especially because data collection in robotics is much more expensive per unit of data point compared to language or vision, how can we chart a path forward in that sort of trade-off space? We can start with maybe Ankur. Ankur.
Yeah, so I haven't really worked on BC. So my experience is mostly through RL, which automatically creates curriculum of data generation if you set the knobs properly, and if there's an evaluation in the loop, as we saw with what OpenAI and what we did with automatic domain randomization. I think this sort of approach can also be adapted for manipulation tasks and stuff, but obviously it requires more careful thoughts about how to design systems and scenes and stuff in simulations. While it's much easier to do sort of diversity in real, but I think you also hit an asymptote which you don't necessarily do if you figure that out in RL, because you can always do different ways to improve the performance through self-play. But in real, there's a fundamental limit you hit, and an asymptote with the data collection after that. It's very difficult to build systems that have superhuman performance by adding more and more and more data, because the amount of effort needed to collect data to improve the performance becomes significant that it might not be feasible in the real world. So my experience is mostly through simulations, and I feel like that's one way where that's one place where we can still leverage scaling really effectively by a combination of automatic scene design through LLMs these days and self-play. Yeah.
The one thing that we have done is instead of collecting data from the start, is if we have some behavior cloning or something like that, to recognize where the model veered off and did something wrong, and just collect some corrective actions and data in that space. In that sense, we can put less tax on it's less taxing on the demonstrator, and we can just get high quality data in the regions where the model seems to struggle a lot, and that has worked quite well.
One thing that we found when we were working on the Pi Zero system is that you can actually get around that trade-off challenge, which by the way is very spot on. Like that is definitely the trade-off, by using a pre-training and post-training recipe. And we didn't actually model this off how LLMs are done, although it was like convergent evolution that we end up with something. Then we look at it like, hey, that's actually what worked for LLMs too, is to basically pre-train the model on diverse data. And the diverse data will necessarily be of lower quality because that's how it gets to be diverse. And then have a post-training phase where we use a much smaller amount of very carefully curated high quality data. And that actually works better than either of the two by themselves, because just the low quality data will lead to low quality strategies. And just the high quality data will be too narrow, such that when the robot makes a mistake, it'll be an unfamiliar situation. But if you have both, it basically teaches the policy to do what the high quality data does. But if it ever gets out of the distribution that the high quality data covered, then it still has some fallback from the pre-training. And that's much more analogous to how LLM post-training works too. So I think that is one way to get around that trade-off, and it seemed to be very effective so far, actually.
Just a short comment. Okay. Yeah, a short comment that sometimes reasoning in the in a better representation space actually can help there. I think there was a very nice demo here, CoRL, showing that having touch signal, for example, when picking a grape, it actually makes retrying behaviors emerge. Because imagine if you go inside a shopping bag, pick up a grape, and then you take it out, you don't see it by vision, so you'll never know whether you actually grasped it or not. Well, if you have a touch sensor or something that gives you information about contact, then it will immediately notice that that the behavior is a failure behavior and will immediately reattend. So sometimes it's also a matter of representation space.
So maybe we can take some questions from the audience here in the room as well, and I'll just repeat them so that Ankur can hear them as well. So we have one over there.
So I guess maybe a little bit of a trick question, primarily a target. So there's this hypothesis that large-scale imitation learning is a very promising path to like robot maintenance. However, that obviously requires large-scale teleop data to even embark on. So my question to you is, if let's say you're in an academic lab or something like that, and you can't go and collect like hours and hours of teleop data, and you had like a tenth of the data that you have or 100th of the data, what would you work?
Getting more data. So I guess the more serious answer is like, we are not the first community to face this challenge. Like, you know, if you go back to the early 2000s, like the largest computer vision data sets were much smaller than the kind of robotic data sets that we can collect in a single lab now. And the computer vision community worked really hard on it. And you know, their equations obviously is different from ours. Like, you know, if you can scrape data from the web, maybe it's easier. But at some level, like, it takes work. And perhaps more importantly, it is work that a research community should amortize over many researchers. And we've seen examples of this. Like RTX is a big collaborative effort that involved lots and lots of labs getting together and saying like, yeah, if we like pool all of our stuff, then we're gonna have a data set and it can get us some distance further ahead. And I think we should keep doing those kinds of things. And I think that we can develop good kind of standards in our community for sharing data sets, reusing the same data set. Like, I think there needs to be like a little bit of pressure to, like, all else being equal, try to reuse a data set that already exists, just to kind of incentivize that kind of work. And I think we can get there. And I think that if many research labs pool their efforts, we can do a really good job of that. Like, you know, shortly after my lab released a second version of the bridge data set a few years back, and just a few months after that, we found there were like 2 or 3 other data sets that came out around the same time that were the same size or bigger. And that was, you know, arguably in the very, very infancy of this kind of robotic foundation model work. Now this stuff is much more mainstream. So I think if everybody pitches in a little bit, we'll all be fine.
I think we had a question in the back. Yes. Can you make slightly louder, please? Yeah.
Yes. Okay, let me try to repeat that question, and you can tell me if I got it right. So how do we initialize RL algorithm with BC? It seems like many ways of doing it kind of either don't make sense in the case of action chunking, or don't work well in the case of the negative results that you cited. So like, what's up with that, and how do we make it work? Is that okay? All right, so there's like some technical stuff about RL and some technical stuff about imitation learning. So for RL, one of the most important things to make practical RL algorithms work is to have a value function. And unfortunately, value functions don't get initialized with BC because BC trains policies and not value functions. So figuring out how to initialize value functions from data is really, really important. That's what offline RL does. And there are offline RL methods that work very well in kind of more limited settings, but they're harder to scale up than imitation learning methods. So that's the algorithm research frontier. And I think that there's some tough problems, but we can make progress along that frontier. And as we make progress there, we'll basically get better methods to initialize value functions from offline data. So that's like a fairly well-scoped problem. Now, if we go to the imitation learning side of the equation, there are a bunch of things that imitation learning methods do that are like a little peculiar. Action chunking is one of them. And those peculiar things are typically there to deal with one or both of the problems, the causal confusion problem or the distributional shift problem. And they're really actually the same problem at some level. The reason that these things are imitation learning specific is because you actually don't need them for RL, because RL gets around those problems in other ways. And in fact, there have been experiments with using action chunking for RL, and the results are extremely mixed, mostly negative, perhaps because it's solving a problem that exists with imitation learning but doesn't exist with RL. I'm not sure what to make of that. Like, you can interpret that statement as either saying like, oh, something is wrong with RL because it doesn't benefit from this awesome thing, or you can interpret it as saying RL is better because it doesn't need this thing. Take your pick as to which of those interpretations you like. But I think that there's like an algorithmic frontier, and we need to develop better algorithms.
we are limiting on time. One question that is not for surgery.
That to me, it looks like things are getting much bigger all the time. At the moment, we are at sort of a boundary where academia cannot really work well because they need these large foundation models. And with these transformers, which originally were being built for language, and then we add vision, and then we add touch, and then we might add smell, or we might add whatever. So they are really getting big, and you need some from a commercial company at least as a basis, and then you can train additional things. And I don't think that this really scales well. And also, I don't think that you need 10 times as much data to get 10% improvement. That won't scale well. So aren't you also worried that we would need some other kind of architecture which is more compact and more efficient? Because we cannot use nuclear power plants in the future to train our models, which is actually being considered.
Someone else?
Well, I guess we always have had the problem with scaling, like when deep learning was out, like getting your hands on many GPUs and all that. So yeah, maybe we could look into more data efficient learning and all that. But the models that are out now literally can run on your local GPU and doesn't need a nuclear power plant, at least the robotic foundation models. I've been playing around with the cross-former for a few weeks now, and it doesn't need that much. I think we are obscured by the large language models, but the robotic foundation models are actually very neat and small size.
Maybe a different perspective is that it's true we are moving towards a world of abundant data in robotics too. And it's not just about making architecture more efficient, but what you've seen in history, like in robotics in the last 10 to 20 years, maybe especially also in other fields like computer vision and NLPs, is not about making the architecture more efficient, but make them such that they can absorb this increasing amount of data. And I think there is a lot academia can do. You can also prove it at small scale and show the potential for scaling. And I think it's something that's going to be very important in the future.
That's a great answer. And one thing I would add is also, there's challenges that come with this stuff, but there's also opportunities. So really good pre-trained models, once you have them, they can be fine-tuned with less data than if you were training from scratch. So in some ways, it can actually alleviate parts of that problem. And there have also been like really good ideas put forward to make fine-tuning of foundation models more practical on a budget, like low-rank adaptation, for example. This combined with good open source models, they can help a lot. Now, the challenge is still there. So if you talk to, NLP students that are working on language models, like, yep, they can grab like Llama. Llama is a great resource, open source, has weights available, low rank adaptation, smaller data set, run some experiments, but there's still challenges. Like they still need a big enough GPU to hold this thing. So I would say the challenges are not insurmountable, and there are a lot of ideas being put forward to address them. And also there's new opportunities like being able to get away with smaller data sets than you would from training from scratch. So it's changing the landscape, but I wouldn't say it's changing in a way that kind of puts academics out of business, so to speak.
All right, so maybe in the interest of time, and because we all also want to get to lunch, I would once again thank the panel for the discussion. Yeah, and I hope you join us as well in the afternoon session where we will continue on this topic.
Thank you, Ankur, as well.
And thank you to the organizers.
Yeah.
So should I use this one?
Yeah, I think it doesn't. You can.
Okay. So, yeah, all set. Okay, welcome back to the afternoon session. So we are starting with spotlight talk. So this should be really interesting because it's very recent work that people have submitted to the workshop. People, this is also where you can dive deeper later in the afternoon coffee break, because you can discuss the work further with them at their poster. And then we have three more talks, or 4 more talks really. Anyway, 5 more talks. I'm sorry, I'm just checking the coffee break in between, but really we have a number of more talks, really exciting ones. I think they will broaden our perspective in addition to what we already heard today in the morning. And at the end, we will have a panel session again. And I think this should also be really interesting for you to interact with the speakers. So let's get started with the spotlight talks. So we'll just make sure we are staying on time for everything because, yeah, such that we have half time during the coffee break for the posters again. So are the spotlight speakers here already? I guess we have a few more minutes. Maybe we'll make sure we stick to the schedule because I saw people switching between different workshops. And so we should be reliable on ours, reliably keeping those times such that people can switch if they need to. So, yeah. Maybe for the spotlight speakers, can you raise your hand if you are here? Okay, perfect. Okay, great. Then I think we'll just get ready with your slides and we'll start at 1:55. And maybe the first one can come here because with the microphones, we have 1 microphone for Zoom and live streaming and 1 here for the room. So sorry for the...
No worries.
Spotlight talk. The first one is robot cross-scaling robot data collection through crowdsourcing.
Hi, everyone. I'm Suvir from Stanford. This is joint work with David Yuan, Kelly Burns, Sajid Islam, Tony Xiao, Chelsea Finn, and Dorsa Sadiq. So we're presenting RoboCrowd, a framework for crowdsourcing robot demonstration data. So the motivation for this, as we've seen, end-to-end data-driven methods are really promising and powerful, in narrow settings, as long as we have the data, as long as we have abundant data, but we don't quite have abundant data yet. And one of the reasons why is that the human effort required for collecting data for imitation learning is burdensome to collect. Right. And one of the sort of underlying reasons for this is we don't have mechanisms to sort of distribute data collection between, researchers and dedicated robot operators and non-experts, more broad set of users. So in this work, we look at sort of ways that we can transform the process of robot data collection into something that's a bit more distributed over many different users through crowdsourcing and incentive design. So to do this, we developed RoboCrowd, a framework for incentivizing crowdsourced demonstration collection in the real world. And so we center five key properties, being publicly accessible to non-experts, capable hardware, intuitive operation to non-experts, safety, and gamification. And so I'll give a quick overview of the system. So we build the system upon Aloha, a low-cost system for bimanual teleoperation, and we do a variety of hardware and software enhancements to make the system intuitive and safe for non-experts. And we also develop a interface to onboard non-expert users to how to operate the system, including tutorials and sort of a gamified interface where people can select different tasks they can do in various scenes. And so our key idea is with this system to sort of align incentives to shape the crowdsourced interactions that people might have with the robot into useful data for imitation learning. So for example, here, a user might grab a candy out of a bin, right? So some sort of semi-precise picking task from a bin, and they're not really intending to provide data. They're just trying to get a candy out of a bin. But in the process, they're adding to this sort of crowdsourced data set for bin picking that we would create. So this is a simple example, but we look at other incentives as well. For example, intrinsic motivation for people just having fun interacting with the robot, and an idea of social comparison where people kind of compete to try to do better on different tasks. So we actually deployed this for a couple of weeks in a cafe at Stanford, where people could just kind of organically come up to the system and play with it. And we collected around 800 interaction episodes from over 200 users in this sort of self-organized gamified experience. And we set up some different scenes to sort of experimentally test some various incentive mechanisms in shaping the types of data that people could give with the system. So I'll give a quick overview of our results. So here's a scene where we collect data for users sort of attempting different bin picking tasks, one with a high chew candy and one with a Tootsie Roll candy. And it turns out people prefer high chew, so more of their data was focused on that task. So this is kind of like a crisp example to show that how these different material incentives can shape user interaction. But something interesting we see is that users actually focus a lot on play data. So they try to construct their own tasks that are harder than the ones we put out. And this is something consistently we see when we construct other tasks as well, like this kind of complex bimanual task of ejecting jelly beans from a dispenser that people try to attempt. And we also sort of see this as well, where when we control for different material incentives and see, we put candies inside of a Ziploc, and people tend to go for the candies inside the Ziploc that require unzipping the Ziploc instead of just like grabbing the candy out of a bin, which points to this idea of like intrinsic motivation as a useful incentive for shaping these interactions. We also add this like leaderboard page for social comparison, and find that people who tend to be more competitive and look at the leaderboard actually give slightly more data and slightly higher quality data as well. And we also have some preliminary results on using the crowdsourced data for pre-training robot policies. So we see some signs of life here, but I will point out that like some of the crowdsourced data is pretty, low quality and noisy. So this presents like definitely a research challenge in figuring out how to leverage the most from this data. And here's an example of fine-tuning our like candy Ziploc task on expert data for unzipping a Ziploc full of tools. So in summary, we are proposing this paradigm for crowdsourced data collection in a public space with non-expert users, and sort of focus on this aspect of incentive design to shape the interactions into useful data. Thanks.
If you have questions, we have the poster session.
Yeah, thanks so much. Hey guys, my name's Ted. I'm here today to present our recent work Steer. The first author, Laura Smith, couldn't make it, but this is with a collaboration with our big team at Google DeepMind. Broadly, we've over the past few months, we've been very inspired by a lot of the successes in large-scale imitation learning that we can see being deployed in static manipulation settings and mobile manipulation or even self-driving. But in a lot of these settings, right, we're roughly operating off of expert demonstration data sets, such as those on the left, of very coarse, skills of the form, place A near B, knock object, pick object, etc., where a lot of these skills are relatively simple and they're collected at the episodic level. But when you compare that with very realistic deployment scenarios, such as pouring something out of a cup and placing it back upright on a table, it's not exactly obvious that everything we want to do in the real world will correspond exactly one-to-one with the definitions that we set a priori in our offline imitation learning teleoperation data set. So if we really think about how humans kind of then operate, yes, for one, humans don't really have such homogeneous training data, but in addition, humans also are able to have a lot of contextual world understanding of what it means to pour or drawing upon past experiences to stitch together previous kind of knowledge into a new test time task. We really like Kahneman's thinking fast and slow, breaking up roughly into a model of how this might work is having like a high level system 2 analytic thinking and then system 1 low level more reactive motor commands. And when we think about what it would take to bring robotics into such a framework, maybe the limitation is that a lot of our system 1 low-level policies don't really have the flexibility that it takes to really allow a system 2 kind of level reasoning to successfully operate over these low-level system 1 skills. Towards this, we present our method steer, which, maybe you've seen a very similar diagram before. We take an offline data set of very low level primitives. We relabel with skills that are more easily can be utilized by a high level reasoning policy. We train that multitask policy. And then at test time, we can then synthesize these skills at test time in a very much more natural way. For example, you can use a vision language model to take a test time new scenario to turn that into kind of the skills that your system 1 policy on the left has now learned. And then from that, you can get much more reactive and generalizable behavior. How then do we do this? That's the whole crux of the problem. One kind of thing we identified is that we've seen a lot of progress in like hindsight relabeling, taking existing, very coarse, homogeneous data, relabeling that with denser language annotations so that your language condition policies now have more steerable instruction following skills. What we found is that a particular way to do this is to kind of densely annotate our data set with very dense language captions at much lower temporal horizons, focusing on what actually is important for steerable robot manipulation, such as focusing on aspects such as rotation, grasp approaches, object-centric arm motions. And then for the experiments, what we find is that we do find that qualitatively, we get very good vibes, so to speak, that the low-level policy can now be steered, responding to different ways of basically breaking up behavior modes into specific aspects of like showing exactly how you should do a task, in addition, not just what describing what you should be doing. Quantitatively, we find that this outperforms methods which kind of build off of the same underlying data set, but that do not do this like dense language labeling. We find that, for example, even VLAs, which are trained on internet scale data, don't get this steerability for free. Looking a bit what these rollouts look like, you can see our method on top, being able to utilize the low-level steerable low-level policy to approach the plotted plant in a much more natural way, as opposed to, let's say, OpenVLA or RT1, which really don't respond to the affordance of the scene at all. We find that this enables generalizing to new tasks altogether, such as pouring, much better than other kind of hindsight labeling methods, such as goal condition behavior cloning or RT hierarchy, which predicts extremely low-level language motions that aren't necessarily able to be like semantically guided by a VLM. The policy by itself, even without this VLM guiding, can still perform well at individual low-level tasks. Here we show zero-shot generalization to a lot of new objects and configurations. Here's showing an example of a failure mode of why VLAs out of the box may not be enough. In theory, even if they have seen pouring and they've seen understand the semantics of what it means to do these things, those semantics have not been bridged to low-level skills. And finally, the result we wanted to showcase that inspired our project to begin with is to see whether or not VLMs can actually control and orchestrate this more steerable low-level policy. And indeed, we find that both zero-shot and few-shot VLMs like Gemini can control this low-level policy to achieve very complex new tasks. Thanks so much. Our paper and website are there, and hope to see you at the poster.
The next paper is SplatSim, zero-shot sim-to-real transfer of RGB manipulation policies using Gaussian splat.
Hi, everyone. How do we build photorealistic? How do we build photorealistic simulators that can serve as a data generation pipeline for robotics? Here is an example of our photorealistic rendering video. And here the flying objects are specifically here to convey that these are generated instead of real world. I'm Yishu. I'm here to present SplatSim, zero-shot sim-to-real transfer of RGB manipulation policies using Gaussian splatting on behalf of the authors. So our motivation is policy learning from manipulation from human demonstrations has shown a lot of progress. However, these teleoperation systems, these teleoperation systems are hard to scale because they are quite costly to set up and they require physical robots for each teleoperator. And also, RGB renderings from current simulators look nothing like real world, making RGB-based sim-to-real and out of distribution generalization problem. So our key idea here is to combine the explicit representation of the Gaussian splatting with existing simulator to convert the simulated data into photorealistic data. We rely on the insight that if each rigid body in the scene can be segmented and associated with its body in simulator, we can use the transformation given by the simulator to get a photorealistic trajectory of the simulated trajectory. Here are some examples. We generate photorealistic data for 4 manipulation tasks and transfer the policy zero-shot to real world without any data collection in the real world. Now we expand more about our method. The first step is to create a Gaussian splat of the scene with the robot. This is the scan of the thing, and this is the Gaussian splat of the scene. And then we segment the Gaussians belonging to the robot, and we take the means of the Gaussians as a point cloud. And then we find out the transformation between the splat robot frame and the simulated robot frame using ICP. And we find out the segmented means for each link of the robot and then we can apply the transformation. This is how the spatial alignment looks in practice using a cloud compare software. It takes around 15 minutes if you're untrained in the process to find out all the transformation. Have to crop some of the points out. We also show how to segment objects with non-axis aligned links using a KN-based approach. We can also use directly control the splat with a teleoperation tool like Gallo. So our overall pipeline is we first collect expert demonstration in a physical simulator pipe bullet. And in our case, these demonstrations come either from human experts, teleoperation, or through a privileged information-based motion planner. The trajectories from the simulator are then fed to the simulator-aligned splat model of the scene and the object. And then we transform the 3D Gaussians to manipulate the static Gaussian splat models to extract photorealistic renderings of the scene at novel joint and object poses, which serves as the RGB state observations for the diffusion policy. Along with these RGB observations, diffusions also take the end effector position and the orientations as the input. And then we train our policy and transfer to real-world zero shot. Here are some examples of our zero shot ability. This is the push T task. This is the pick up an apple task. This is put an orange on the plate task. This is a stack block task. And this is a table of our overall success rate. We can see that even based only on synthetic data set, we can achieve 86% of success rate, very comparable with those trained on real world data to show the effectiveness of our method. These are more demonstrations. For more videos and details, please visit our paper and our website. Thank you.
Our fourth spotlight talk will be on latent action pre-training from videos.
Hi, my name is Joel, and today I will be presenting latent action pre-training from videos. This was joint work with people from KAIST, University of Washington, Microsoft, NVIDIA, and AI2. So where do we get the abundant data? I think that's what everyone is curious about. A lot of people throughout the last few days have hinted towards internet data, video data in the internet being a potential solution. But data in the internet with humans doing a lot of different stuff are widely available, but there's no robot actions, and there exists a human to robotic body gap. We propose LAPA, which aims to mitigate these two problems and train robotic foundation models. Through LAPA, we can take videos such as these with diverse environments and humans manipulating different objects with differing camera viewpoints and learn skills directly to transfer directly to the downstream robotic tasks. So how do we do this? We tackled the problem of having no robot actions by obtaining latent actions from the visual deltas in the videos. We tackled the embodiment gap problem by initializing from a VLM. So LAPA consists of 3 different stages. In the first stage, we train a VQVA where it takes 2 consecutive image frames from video as input and outputs only the second image frame. And we train this with vector quantization, so we get discrete representations. And we only use the tokens or the indexes of the discrete representations for stage 2, where we do supervised fine-tuning. And instead of actually predicting ground truth actions, we predict the latent actions represented via action tokens. And stage 3, we assume that we have some trajectories with ground truth action labels collected via tellout, and we fine-tune the VLM. So diving more into a little bit of the detail, first we get the embedding of the 2 image frames from the encoder. And to the decoder, we feed in only the first image and the tokens. So the decoder is forces the latent representations to capture the delta between x1 and x2. And yeah, since it's discretized with the vector quantization, we can have them just as latent tokens, which makes it easier to train LLMs. So yeah, in stage 2, it's the same as other VLA training. We do it, but we just use the latent tokens. In stage 3, we initialize from the VLA, But the VLA cannot do anything in the real world because the action it predicts are latent. So we do the same thing. We have some observation and action pairs, and we fine-tune the VLA, which and in this phase, it learns the mapping from the latent to real actions. And we have diverse pre-training and fine-tuning mixtures, but in this talk, because of the time, we want to highlight two main experimental setups, the multi-embodiment and human-to-robot transfer. So in the multi-embodiment, we've pre-trained on OpenX. We use the exact same subset used to pre-train OpenVLA. And on fine-tuning, we collect 150 characters per task, where there's 3 objects, 1 target, 2 distractors. So it has to do language conditioning, and we test unseen object combinations and unseen instructions. So the first result that I want to highlight is that pre-training helps. So compared to Scratch, LAPA pre-trained on Bridge outperforms, and LAPA pre-trained on OpenX leads to better performance. So this is a good thing because then scaling pre-training data leads to better downstream performance. Second is that LAPA pre-trained OpenX outperforms OpenVLA pre-trained on OpenX, but OpenVLA was pre-trained with actual ground truth actions. So how is this possible? In previous other setups in the work in simulation, actually using the ground truth actions is the upper bound, but in this case, we beat the upper bound. This is the reason why this is possible. The latent actions you can see when we use the decoder of the VQVA to get to the next frame, we can see that the same token combinations, despite the different embodiment environment, equates to the same robot action. So the first thing you can see that it goes, the Google robot and the WidowX both goes down and left with the same token representations. This is very different from current VLA training where they discretize based on each data set, which is can't really result in a huge positive transfer. This is analogous to bipair encoding in LLM. So we get the atomic tokens in LLMs by going through all the corpus in text. Similarly, we go through all the frames in the videos and try to find the atomic action granularity. So now about the abundant data, now we need to train on human data. So we show results on something, which consists of 220K human videos. And the highlight result here is that LAPA pre-trained only on human videos outperforms OpenVLA pre-trained on Bridge. And Bridge is one of the biggest open source data sets. So I think this really highlights the true potential of LAPA. This is just for future work. Because I told you that it captures the atomic action granularity. So it captures any actions between 2 image frames. And something there, the camera moves a little bit. So we see that it also captures the camera movements despite the different environments. So we want to, for future work, we want to extend this to capture more diverse actions, not only embodiment-centric actions, but as well as environment-centric actions to do dynamic tasks. Yeah, thank you for listening. I'm glad to talk more about this in the poster.
So our fifth talk will be diffusion policy optimization.
All right. Hi, everyone. My name is Lars, and I'm very excited to be presenting our work on diffusion policy optimization on behalf of my awesome collaborators, and especially a big shout out to Alan Wren, who led this project. So recently, there's been a lot of excitement about learning policies with imitation learning from data. And there's been a lot of very, very impressive results, like this shirt hanging task from Aloha Unleashed. This table from the paper, however, caught my attention because as you scale the data, you would expect your policy to improve in performance as well. But here we see we plateau at around 70 to 75%. We think that RL might be a very good way to overcome this limitation of learning from human demonstrations, because you, instead of optimizing for or maximizing the likelihood of the data, you rather optimize the policy pi to directly maximize the task performance. To do this, you need, and we want to do this with policy gradients. To do this, we need access to the log likelihood of the actions with respect to the policy pi. For a standard Gaussian policy, this is straightforward, as we have access to the likelihood of the action directly. With a diffusion policy, however, this is more complicated because what we have access to is only the intermediate denoising steps and only the likelihood of each intermediate steps, but not the final action at the very end. So to solve this, we formulate this diffusion MDP, where we model the denoising process itself as a Markov decision process. And then for every time step of the environment, we have such a MDP. And then we can model a whole rollout as a chain of these MDPs. And we get a effectively now a two-stage, very long MDP, where at every stage, we have access to the log likelihoods. And as such, and this is how we kind of parameterize the problem for this. And since we now have access to the likelihood at every single step, we can solve this MDP with standard policy gradient methods. And this is how the PPO works. So we start out by testing DPPO against other standard policy parameterizations, a Gaussian MLP and Gaussian mixture models. And we find that the final performance is greater, much better for the DPPO, and it converges faster at a better sample complexity. And this difference is much bigger when we use learn from pixels directly in RL. And we want to highlight this task in particular because this is a very long horizon challenging task from the RoboMimic task suite, where the DPPO can achieve over 90% success rate, and to our knowledge, previous methods only achieved roughly 50%. And considering that this is like here we have an effective action space of 112 dimensional actions. We use sparse rewards and only get the reward at the very end for task completion. And we use no regularization like BC loss. We still can achieve these results, and it shows that DPPO is a very powerful method to solve long horizon manipulation tasks. We also tested out on this multi-stage manipulation task requiring high precision from Furniture Bench. And again, find very, very strong improvements over the pre-trained policy, and especially here on the roundtable task, we go from 1% pre-training performance up to 86% success rates. And maybe more importantly, the qualitative behavior we get is much smoother and more natural with DPPO compared to the standard Gaussian MLP parameterization. And this property also provides for much stronger sim-to-real transfer, because on the left here you see the DPPO policy is very smooth and nice, and we have very consistent performance between sim and real. On the right side, we see the Gaussian MLP, though working pretty well in sim, has very erratic behavior in real and causes robot errors, and as such doesn't transfer at all. So then we do some deeper exploration and find the two properties that we think causes DPPO to work so well. So here we consider this very simple avoid environment, and we have these three settings with different modes depending on what expert data we pre-train the models on. And then, as we pre-train the same models, the DPPO, the Gaussian MLP, and the Gaussian mixture model. And in the beginning of the fine-tuning phase, we add exploration noise, and the resulting policies we plot here. And then we consider what they look like. And we see for the DPPO, the resulting exploration trajectories cover the expert data well and stays close despite having noise added to them. And compared to the Gaussian NLP, the exploration is much less structured and ending up being all over the space. And this this property of staying close to the expert data, but still covering it, is what we call the on-manifold exploration. And yeah, and this is what we think might speed up the training and also regularize the behavior to make sure we're staying close to the expert data. Yeah, providing more natural and smooth fine-tuned behavior. We also find that the DPPO is more robust to OOD initializations and more robust to action perturbations throughout the episode. And yeah, and this obviously helps with deployment, but also allows for more domain randomization at training time, which also helps with sim-to-real transfer. So yeah, in conclusion, we present DPPO, a method to fine-tune a pre-trained diffusion model with policy gradients directly. And the takeaways are pre-trained diffusion models can be brittle, but it provides a very good base for fine-tuning. We find that DPPO can effectively leverage the wide coverage that the diffusion policy provides for efficient online exploration. And the structured exploration leads to more natural behavior after fine-tuning. And now we're very excited to take this even further to by, for example, training on bigger data sets of multitask data, and then yeah, doing fine-tuning in, of course, the simulator, but also in the real world, or using generative simulations and similar. So yeah, thank you so much.
Our final spotlight talk will be many WAV, learning robot manipulation from in the wild audio video.
Do you need your speaker now? Yeah. Okay.
Thank you so much. Yeah, sorry about the mess. Okay, so this is Yi from Stanford, and today I'm happy to introduce you ManyWave, learning robot manipulation from in-the-wild audiovisual data. So audio signals reveals a lot of rich information about the interaction and object properties. This is a video of me holding this handheld gripper interacting with a lot of objects. And we can hear that the audio signal contains a lot of information about the interactions. So we asked the question, how can we leverage audio feedback for context-rich manipulation skills? So we built on top of the UMI gripper by Chi et al. And embed a contact microphone inside the gripper finger. And for each demonstration, the audio data is recorded synchronously with the vision data through the external mic port of the GoPro camera. And here are some advantages of contact microphone. First of all, it's cheap. It's only $10 off the shelf from Amazon. It's robust. I can only use one microphone to conduct my entire experiments. And it's insensitive to background noises due to the nature of the piezoelectric material that only pick up signals transmitted through solid objects. And it's easy to record and store with vision data into MP4 files. However, here's the challenge. So let's hear a recording of the human-collected demonstration. And this is a recording of the robot deployment. So we can hear that the robot motor noises and other robot interaction noises generated during test time is causing an audio domain gap. To address this, we propose an audio data augmentation technique. We randomly sample noises from a recorded dataset of robot noises and the ESC50 audio dataset and overlay it to the original audio signal. And the final sensory motor learning model taking fisheye images and the log mouse spectrogram converted from the augmented audio. And the visual features and audio features are fused through a transformer encoder and finally passed through a diffusion policy to generate the robot actions. And we systematically evaluate our method on 4 context-rich manipulation tasks. And today I'll dive into 3 of the tasks. So the first one, the robot is supposed to wipe the shape off from the whiteboard. Now the challenge of the task is to infer the contact between the eraser of the board while following the shape. And we can see that by leveraging audio signals, our method is able to correctly infer the contact between the eraser and the whiteboard. And the policy is also able to generalize to unseen table heights, unseen shapes, such as a star that's not in the training data set, and also to a different eraser with a slightly different wiping material. And here are some results from the baselines. I think I don't have time to delve deeper, but it's worth noting that for the vision-only baseline, the policy will tend to float above the whiteboard as the contact between the eraser and the whiteboard is hard to be inferred from only the image coming from the wrist mount camera. And here's a bagel flipping task. We can find that our method is able to correctly insert the spatula between the bagel and the pen and then flip when the bagel is in contact with the edge of the pen. And the method is also able to generalize to unseen table height, and it's also robust against background noises due to the nature of the contact microphone. So our key findings, one of our key findings is that by incorporating contact audio as an additional source of information improves the robustness and generalizability of the policy. To delve deeper into this finding, we actually visualized the attention map of the VIT encoder used in our method and found that a policy trained with both vision and audio attend more to the task relevant regions, comparing to a policy trained with only vision data attends more to the background features, such as the edges of the whiteboard or the room background. And another finding we have is that noise augmentation is an effective strategy to bridge the audio domain gap between human collected data and robot deployment data, as it improved performance by 50% on the wiping task comparing to a baseline with no noise augmentation. And here's one of the interesting experiments that I would like to show is that we found that the contact audio is sensitive enough to different surface materials. So the task here is that there are Velcro tapes that are with different materials that can either be loop or hook, and the tapes are randomly placed on the right, and then on the left there is a loop material underneath the wires. So the task is basically to find the correct tape that can attach to the loop tape underneath the wires. So we can clearly see that there's a difference in terms of surface materials that could guide the policy to choose the correct tape. And finally, we conduct in-the-wild experiment where we will use the handheld gripper to collect diverse in-the-wild demonstrations of the bagel flipping task. And we find that our policy trained on diverse in-the-wild demonstrations can zero-shot generalize to this unseen environment, whereas a policy trained with data collected only in the lab tends to drift away from the object. And so here are the quantitative results and show that the in-the-wild demonstrations enable generalization to unseen in-the-wild environments. Yeah, if you're interested, feel free to check out the project website. And yeah, thank you all.
Okay, now I guess we'll have the first invited speaker for the afternoon session. It's my pleasure to introduce Xiao. Xiao is a senior research scientist at Google DeepMind working on robot learning. His research focused on scaling robot learning in the real world with a particular focus on approaches that look at internet models and practice to improve with more experience.
Great. Okay. Cool. Yeah, thanks for the warm introduction. Really happy to be here today. Today, I think I'd like to kind of talk a bit about a lot of what's been on my mind the last few months with regards to where we are in terms of the progress of science and figuring out what's missing for robotics foundation models. I think there's so much energy and excitement in seeing how much progress we've made. And I think a lot of us are still wondering, though, you know, what's next. Today I'll showcase a few different works from a really large team at Google DeepMind. And this is definitely not just me, it's presenting on behalf of a really large team. So roughly then at a high level, in today's talk, I'll cover a few different areas. I'll first start with what exactly I mean by robot foundation models. This is very much an overloaded term maybe, and exactly figuring out what that means will be a good start of the talk. I'll then dive into 3 explicit components that I think are very important for next steps of understanding robot foundation models. And finally, we'll wrap it up with a bit of forward-looking philosophizing. So to really think about what a robot foundation model is or should be, I think it's helpful to take a look at how we got to where we are today. This is the classic sense, plan, act loop, where a lot of robotics progress, even learning-based systems, have seen a lot of progress by using off-the-shelf perception systems, some kind of planning module, and then some kind of low-level actuation. And recently, right, what this looks like in practice is we take a vision language model, that's the perception stack. We take some language model for some kind of planning and reasoning, and then finally we have some learned low-level control policy. But here, there's 2 things here which I think kind of give me some hope for where we can go, and something that looks wrong with this picture to me.
One is that the modules that we're using off the shelf weren't necessarily optimized with robotics in mind, right? We are taking very performant VLMs and LLMs from NeurIPS and CVPR and what our friends in foundation modeling are doing, and we are finding that we can use them for robotics very well, but they weren't necessarily designed with robotics and decision making in mind. And the second thing is that the way that we're stitching together these modules is oftentimes right now quite engineered in heuristics, right? Which is working quite well in a lot of settings we're thinking about, but I would still argue that the communication bandwidth of these bottlenecks is still quite narrow and will become limiting at the limit. And what I argue then is that because we are now at the point, I would say that we are starting to really feel the pain of these bottlenecks, these limitations, is that the trends we've seen elsewhere in language and vision, we're going to start to see in robotics, right? The foundation modification of robotics, where the barriers between vision and language and control, we're going to start exploring how we can break these down and try to take more of the destiny of robotics, so to speak, into our own hands, and actually creating foundation models which are optimized for robotics, which are designed with low-level control in mind. But that's not the only reason I would say, right? When we really take a step back and say, okay, great, okay, so that's what a robot foundation model might look like. We're going to break down the barriers. Why do we even need to do this in the first place, right? And the first reason that I just alluded to is that, well, it's the clear next step, right? We're going to go from taking off the shelf foundation models that we download and take from our colleagues in other fields, and we're going to try to, maybe create one ourselves, or we're going to make them better with kind of the priors and structures that we've discussed so much, for example, in the conference this week. But the next reason I would say is that actually this is not just nice to do, it's actually necessary to do. If you think about a lot of the robotics progress that we've seen, going from bin picking, picking a lot of objects, doing that very well, going to understanding how robotics mobile manipulation works in one room or one building. But the gap from that academic level research to the chaos of the real world, right? The unstructured, in the wild nature of where we now today want to deploy our robots with all of these hyped up startups and humanoids, right? It's like clearly there's a lot of complexity in the situations where we want to deploy our robots with the elderly, with our pets, with our children, and so many novel scenarios. I think the only sign of life, right? The only existence proof we have of a technology that can operate in the complexity and the generality of the real world so far seems to be foundation models, right? I think they're clearly deployed, not perfectly, but they're able to operate at the generality of the in the wild distributions, data distributions, and I hope we can leverage those properties in robotics as well. So we can see then, why have these non-robotics foundation models worked in the wild and these very difficult and unstructured scenarios? And I think there's three main properties that I really think are very important, right? One is, I think in foundation modeling, folks have understood the scaling laws of how to really get benefits when you add more resources into data, into model size, into compute. Seeing that generalist learning, generalist models are often beating specialized models. Another thing is, I think these non-robotics foundation models are trained with very large bandwidths. They have high bandwidths. They're trained on very heterogeneous data distributions. And I think then at inference time, you can see emergent prompt engineering, few-shot learning, et cetera. And finally, I think one thing I really like from the foundation modeling community is they've made progress towards more scalable evaluations, predictive benchmarks, and shared kind of evals, which kind of accurately reflect how these foundation models need to perform at deployment time. And in robotics, right, I would argue that we don't necessarily know what these three pieces look like. The topic of the workshop, I guess I was originally in the morning workshop where the theme was learning methods for versatile and reliable manipulation. I would argue map quite well to these three pieces of foundation models that work, right? For scaling laws, when we say learning data-driven systems, I think we'd also like to have some confidence that we know the dynamics of how our learning is going to go. We want versatile manipulation, right? In that it's very robust in all sorts of situations that can generalize. I'd argue that high bandwidth context is what's working in foundation models. And finally, if we want reliability, well, we need evaluations, benchmarks, and to really understand that we're testing and measuring in a very kind of robust manner.
And the first hot take, and I'll drop a few today, is that I think today our state-of-the-art 2024 technology is not yet ready to solve general purpose robotics. I think we're if you just kind of snapshot algorithmically where we are today and all you did was apply, maybe money or data, I don't think we're necessarily ready to solve robotics. I think there's still a lot of science and a lot of research and paradigm shifts that we need to unlock. So then let's dive a bit deeper then. The high level areas that I mentioned, I think one of the first one that comes to mind is scaling laws. In foundation modeling, once again, I'll just draw upon what we know kind of works, or at least seems to have a bit more understanding than where we are in robotics. In language modeling, right, starting from, GPT-2, from chinchilla optimality, I think there was some work done on the physics and the learning dynamics of how you can scale up these language modeling systems. They found these nice power law distributions of how capabilities and loss could scale as a function of compute, dataset size, model parameters. And I think this is very interesting, right? Because like when the language modeling community convinced themselves and others that they kind of understood the dynamics of like, hey, when we add XYZ, we're going to get performance gains, and this is how what we should expect. You see plots then like the bottom. This is from the GPT-4 paper where they did their experiments and iterations in hyperparameter search at smaller scales, with the confidence that their lessons would still project into the future, right? These are not just retrospective scaling laws, they are predictive scaling laws. And I think in robotics, we would like to be there, right? We would like to have the confidence that the work that we do today, the research and the engineering and the investment, is going to translate into predictable gains in the future. I think maybe we've convinced a lot of venture capitalists that we understand this, but as scientists and researchers, I would not say that we have confidence that this is true right now. I do think, though, this year has been a year of a lot of, sparks of life, signs and signals that, that are vaguely positive. And I'd like to highlight a few ones that have changed my mind over the past 2 years. And the specific question I'd like to ground this in is like, when do we know that scaling will help us? And I think the hardest test you can possibly pass is imagine that you only care about your specific robot in your specific deployment scenario, be that your lab, a task, an environment, a scene, whatever. But if you can pass that test and you can show that scaling helps you in your scenario, I think that's a very good bar to hit. One of the first results I saw this was work from our team from 2 years ago called RT1. We collected a large off-scale, teleoperated expert data set. And then we kind of studied when we trained, large-scale imitation learning, behavior cloning transformers, what would happen, as you kind of ablated model performance as a function of dataset scale and dataset diversity. And I thought was very interesting is we found that both dataset size and data diversity mattered, but you kind of needed both in conjunction. It seemed that a minimum threshold of data diversity was very important. And then in the next work that we kind of followed up with last year with RT2, vision language action models, we started treating robotics data a bit more apples to apples with internet data, like VQA data. And there we found that when we kind of co-trained robotics data alongside internet data with a high capacity model backbone, we actually saw some positive transfer of these internet concepts, these internet semantics sort of leaking through into control, which is very great to see, because in our robotics data, we never saw things such as celebrities or country flags or healthy fruits or company logos. And yet we were kind of seeing some of these percolate through, and now our low-level control could showcase some understanding of these high-level concepts. And finally, and also recent work from earlier this year, the open cross-embodiment effort and the RTX line of models, we showed that by training on additional robot data that wasn't your robot could still get you gains in your robot setting. And in this plot here, what it's showing, the rainbow bars show the performance of a single cross-embodiment model checkpoint compared against specialist baselines, which were only trained for the robot that they were evaluated on. And this is a clear sign, I think, that on average, our generalist model, by making the problem harder, training on more robots, you even got gains in your specialist setting.
And I would say, like, for example, a few years ago with single to multitask learning in the RL literature, this wasn't always the case, right? Like if you cared only about your specialist setting, oftentimes adding multitask auxiliary objectives would decrease performance on your specialist. Maybe to give you sample efficiency or generality, but it would decrease specialist performance. And I think whenever we see signs that you can get gains in specialist performance, that's really exciting to me. I think though, at the end of the day, these are still in my mind kind of unpredictable when we see these gains, right? We see that, like, yes, there's signs of life. We're very optimistic. It's very exciting, but we don't really know. We can't really expect the kind of transfer I just showcased to always happen all the time at very high performance. I'll just highlight some dirty laundry here, right? One is that I think vision language action model training is still kind of more of an art than it is a science. It requires good intuitions, good engineering, but at the end of the day, a lot of the positive transfer we see is kind of what we find ad hoc. We haven't planned for that kind of transfer a priori. And I think here's some examples of when that transfer did not happen, right? For example, we find that VLAs can fit VQA distributions and robot distributions, but when you mix the two, it's not obvious when this transfer will happen. Another example is reasoning, right? I think in RT2, we kind of showcased some positive examples of chain of thought reasoning, first asking some kind of task, and then, an intermediate chain of thought here. For example, what do I need to hammer the nails? The chain of thought says rocks, but then we find that sometimes a low level action won't obey the chain of thought. And I think this is very interesting because now that the physical chain of thought reasoning has generalized to our robotics visual distribution, but then kind of the consistency of reasoning to action didn't necessarily transfer right out of the gate. But I think there's a ton more research, right? Especially in the world of vision language action models. I think action representations, how we tokenize, how we weight our data mixtures. These are all big unknown problems that, as I said, are more of an art. They're kind of a black magic, just kind of, some researchers just staring at spreadsheets of data distributions and data sets and just kind of coming up with arbitrary heuristics. No large scale ablations, not a lot of principled fundamental science. The screenshot here is one of the works I've seen from a few months ago that I really like, from Alex Toshev's group at Apple, where they're looking at different tokenization choices, where in, for example, in RT2, we kind of just chose the most naive parameterizations. And, another major aspect, in addition to how you train VLAs, the architectural design decisions, I think understanding the scaling trends for robotics is also important. I think, one might ask that, okay, great, you just mentioned, Ted, chinchilla optimality, you mentioned language model scaling laws. Did the exact same laws just apply, copy and paste to robotics? And I would argue probably not, right? I think in robotics, it's easy to convince yourself that not all data is created equal, right? You can have 1 billion hours of just free form robot motion, just waving your arm around, and that's probably not very useful data, right? Even though it's a lot of tokens. And so I'd argue the axes of what it means for robot data to scale might be very different from what we expect from language, where you expect everything is just the same, right? So I think what this means, here's 2 interesting papers I like recently that are showcasing this direction, but I think they're just an initial kind of data points on this research field. But I think the hot take here is that because we don't yet know what the scaling laws of robotics looks like, if you look historically, a lot of medium scale data collection in the past has not survived past 1 paper, right? We collect a lot of data, it gets us really great results. Then you look 2 years down the line, the data has almost 0 marginal utility. And I just, we would just hate to be in a point today where we've harnessed a lot of excitement, a lot of resources, a lot of investment. We collect big, large scale data, in product deployments in the world. And then 5 years down the line, we found out a lot of it was not needed or not useful at all. That would not be great. So moving on then, past scaling laws, high bandwidth context. This is what I mentioned earlier on, which I think in language models, we've seen a lot of great success where, they operate under very unconstrained interfaces. But when you look into robotics with how a lot of popular language conditioned policy learning works operate, it's at an episodic structured template language, right? Like pick A, place in B, right? Move A near B, almost like a fancy one hot. We're not really leveraging language for the reason that language is good in language models. And maybe the reasoning is that we've been starting by, from these like very fancy language model demonstrations where high level semantic knowledge is very robust, and we're kind of trying to just pattern match and fit what works in language models into robotics. But maybe by doing that, at least the ways we do that today with very high level abstract language, we're giving up so much. We're giving up what makes robotics interesting and hard. We're giving up the low level, rich contact, the physics, all the knowledge we know that is important from the motion planning and classical control literature. It's sometimes hard to, maybe if you just squint at this, hard to understand how you might even begin to express a lot of these very nuanced concepts in language. And so today I'd like to highlight kind of two works that recent works that tried to present one possibility towards that. One is, called RT affordance, where we kind of started by looking at vision language action training distributions, right? This is what I just mentioned with co-training the robotics data, the green bottom left data alongside blue internet data with maybe some more spatially grounded vision data on the upper right. If you really think about, if you like zoomed out and like thought about like the data manifold, right, of like where these data distributions lie relative to each other, I think they're actually quite different, right? And like what we need is to bridge these very different distributions with some kind of shared, intermediate representation. And what we propose in this work is to use affordances as that. Affordances, what we mean by that is thinking about what makes robotics hard, the contact, the grasping, the rotations, and really expressing that as, kind of as poses, as some kind of representation, which can convey this information, which might otherwise be leaked through if you just rely on high level language. So towards this, affordances, they're expressive, I think, because they fully represent what's hard about robotics. They're lightweight, and they maybe kind of offload the cognitive burden from the high-level policy from having to learn all of this affordance-based reasoning just via low-level control. It just provides like an intermediate kind of planning hierarchy where it can try to learn these concepts. Looking at the method broadly, it's a quite a simple adjustment from our standard vision language action model training. We basically just break up a hierarchy into a high level planning and then low level planning. For the high level planning, we're taking in the current image and the original text instruction, and then we're predicting an intermediate affordance plan expressed as text, which we can then overlay into the current image as a goal image. And then for the low level policy, now it's conditioned on this, visualized affordance goal image alongside the text instruction to produce the original low level control outputs. And the idea here then is that now that we have this kind of hierarchy of reasoning over affordances, we can get great generalization at test time to out of distribution shifts, as well as on in distribution behaviors. This was originally motivated by the fact that a lot of our prior works on exploring different representations and different languages was that like there were certain categories of objects where we noticed we were consistently seeing generalization failures. These are objects that have to be approached or grasped in a specific way, such as objects with handles or which are asymmetric or which have very unique affordances. And this model, is clearly a way to kind of showcase why that was a blind spot before, and by filling in that blind spot, we get much more robustness on these scenarios. And that was kind of one way then to look at an end-to-end training method by introducing hierarchy to improve end-to-end control, both on the reasoning over affordances, but also low-level control. Stepping back a bit, though, in general, I think it's interesting to think about how you might connect the broader problem of connecting foundation models, which are used to internet data, and now you have to bridge them to low-level control, which is, again, as I mentioned, maybe this super different thing from what you expect from the web scale pre-training data. One way is end-to-end, right? Better vision language action models, skill discovery, something like that, where you're optimizing both the high-level reasoning as well as the low-level control. Another way is maybe you can just abstract away robotics as black box. It's just tool use, right? You assume that the low-level policy can handle the difficult bits of interacting with the world. You assume it's a frozen policy, and then you can just do better foundation modeling, better reasoning in order to orchestrate that low-level policy. You can see this with works like that we did in the past, such as SEICAN, a recent work that I really like, embodied chain of thought, inner monologue, etc. But in contrast, I feel like one area that we haven't really studied as much is what if you freeze the reasoning, right? What if you view the foundation modeling high-level reasoning as the black box, and then you actually improve and optimize your low-level control policy in order to be more flexibly controlled by some reasoning system? And to do this, right, maybe one natural interface is maybe it is still language, right? So I think even though I was mentioning language has all these limitations, maybe this is the most natural way if you freeze the foundation model that you can expect it to control your policy. And if you do this language-based reasoning, maybe the issue wasn't language itself, but the way we were using language. I think a lot of the ways that I showcased the limitations of was more on the right of the spectrum. If you think about this roughly, this is like left is more granular and right is more coarse. So right is like episode level templated language instructions, pick A, place near B, move apple near Coke can. Very coarse, very high level. We can move it slightly left by rephrasing with hindsight labeling, right? And other works such as I see like Nils from Moritz and Rudy, or works such as a language table from our team at GDM of like a hindsight relabeling. Or you can go all the way to the left with like very granular, like one second horizon language motions of describing how the gripper should move itself. But I would argue that both ends of the spectrum are not very friendly for foundation models. Foundation models maybe don't understand these task level, episode level instructions. They also don't yet understand maybe the groundedness of having to reason about like 1 second horizon motion-centric strings. So maybe what we want is something in between. And our recent work Steer, which I just presented briefly as a spotlight 30 minutes ago, but I'll just like maybe so I won't go too deep here, is thinking about how we can really design a method that can be steered in that nice Goldilocks zone in the middle between being too coarse and too granular. What we did here was dense language labeling. And the way we did that was by focusing on like, what does it mean for a low-level control policy to be steerable, to be controllable in a way that like a VLM can compose it at test time. What we did at a high level is we focused on the grasps, on what matters, the contact, the rotations, the orientations, how you actually interact with objects as maybe the correct semantic abstraction level. That's where it's low level enough closer to actions, but also high level enough where it can be semantically understood by a VLM, where if a VLM has to operate over this kind of state space, maybe it's the correct level of hierarchy. What we see then is that training then is on the left here. We've kind of learned these more granular skills with dense language labeling. And then on the right here is how you might use this at test time. You see a new, everyday object on an unseen task. Then the foundation model can natively already kind of reason using the skills that we learned densely to deploy at test time. I'll zoom over this a little bit, but we see better steerability compared to pre-trained models such as OpenVLA and RT1. We can see this quantitatively by seeing how steer can adapt to new situations, generalize new objects which need to be interacted with in very unique ways. As kind of visualize what this rollout means is that steers on top. How this is working is that the VLM is controlling the low level policy and basically choosing which kind of grasp approaches to use. In theory, right, a vision language action model has seen potted plants. It's seen these kinds of motions. So in theory, it should be able to do this implicitly, but you see that isn't always the case. It overfits the training data distribution of the low level actions quite often. In RT1, right, it's never even seen any of the semantic data. It has no chance of interacting with objects in predetermined behavior modes. And our original motivation is seeing whether or not VLMs can control it completely autonomously. In the sake of time now, I'll just maybe skip scalable evals. I think it's very important. I'm sad I have to skip it, but I think it's also the part that I think we know the least about. I think the main point here is that I think world models can help us, but real world evals are always going to be the most important thing. But this is kind of going to become the bottleneck as we train more and more generalist policies. I'll just end on this slide here, which is just being a very intellectually honest grading of where we are today. The three topics I think are missing pieces, right? Scaling laws, more steerable robot policies, and scalable eval. I think there's been a lot of excitement, a lot of hype, but I don't think we're very close to solving the science behind it. I think there's a lot of work that we still need to do as a community, this year, next year, and beyond. And with that, I'll just end it here and open for questions. Yeah. Thanks, Dan.
If you have time for maybe one or two questions. Do we have any questions from the audience? Yeah.
Yeah, absolutely. So I guess the question was, we need to do more science, true, but a lot, maybe the medium over which we're doing experiments is still maybe architectures and models that are coming from other communities, right? Are we going deep enough? And I think that's a great question. I would say I don't think we are going deep enough, right? And I think next year, we're already seeing with this conference that robotics first foundation models designed with robotics in mind, with control and decision making, a lot of the structure and priors that we're seeing with tactile, with depth, with 3D, with all of these nice properties, these priors are beginning to be baked into the base core model itself. And I think we should absolutely be doing science on top of these in robotics.
One more.
Yeah, great question. Yeah, SIM to real gap. I think SIM is a great tool. Again, a lot of the work, almost all the works that I showed today did not use any SIM for training, right? But I think one initial step that SIM can help us is evaluation, right? What I also flashed by was, in general, scalable eval is an unsolved problem, right? Offline metrics are not that great. Online evals in the real world are expensive. We ran 15,000 trials over hundreds of hours for the works I presented today. It's clearly that does not scale beyond as we expand the scope of our tasks and embodiments 10 or 100x. SIM is one step, world models are one step, but I think these are far from perfect and are still kind of academic, toys right now. I would say they're nowhere near the production level we need. So that's an open call to, help us bridge these gaps and figure out scalable eval. Yeah.
Thanks.
Yeah.
Hermé, are you introducing?
Yes. Our next speaker is Christian Gehring. He is a senior director of robotics at Robotics, a Swiss robotics company building autonomous legged robots for industrial applications with a focus on high availability and reliability. He obtained his MSc and PhD from ETH Zurich in 2011 and 2016, respectively. During his PhD, he worked at the Autonomous Systems Lab supervised by Roland Sigwart. Thanks for joining us for our workshop.
Thanks for the invite. I hope you hear me. Maybe you can give me a sign if this is fine. All right, good. Well, yeah, it's a pity that I cannot be there in person. Really great conference and also workshop. I participated this morning as well. And so, yeah, let me introduce us, Robotics, right? We're creating a workforce of autonomous robots and believe that the plant operators in the future will not only hire people, but hire robots to get the job done. So you showed this slide this morning, right, that most robots today are using model-based control because they're working in very static structured environments, etc. And I hope my goal of today, of this presentation, is to provide you some insights about the real world problems that we are facing and sharing some use cases. I will also highlight some other aspects that are important to consider to achieve a successful adoption, right, of the technology that we have been discussing so far, especially for mobile manipulation use cases. So you will see our robots already run with learning-based methods in a second. In this video, I'll just show you quickly our robot and which type of environment it's working. So the robot is fully autonomous. It runs in various sites and does industrial inspection. So it has a number of sensors for navigation, but also for inspection. The environments are industrial settings, semi-structured And the robot is built in a rugged way, so it can work outdoors and indoors environments. Pretty robust in these setups. There's always stuff moving around, so it's not really static environments. There can be people on site. The terrain is very challenging. There's stairs and steps. That's why you need a legged robot, right? And the robot can really work fully autonomously. It does navigation and path planning all on board. The robot also works in darkness, in areas where there's limited connectivity, and so on. So what we are working on is you've seen robots, right? They are massively deployed in for manufacturing applications in industrial sites where it's more of a controlled environment, they're fenced and so on. And then we saw a couple of years ago, right? And the next revolution, so to say, in warehousing. So you have all these autonomous robots that are moving from A to B, moving stuff around. And we are going to revolutionize the next industry, the autonomous industry that are enabled by this AI-enabled robots in these more difficult areas and so on. So in this industry, people are working with a digital twin at the core. So they use sensors, for instance, the first level of autonomy, they use connected IoT sensors to get data to feed that digital twin in order that they can digest the data and understand the health of their plants and so on. And they also have some limited motorized equipment, and the next level already started. So you have robots that are still, you need a human on site that operates and remote controls the robot, so it extends the human performance, so you can reach up higher areas, etc. But what our customers are looking for is ultimately autonomous inspection machines that instead of sending human people into dangerous environments, you can send robots that have all the sensing equipment to provide that information. But that's not just enough, right? Often something happens in these sites and you want to do maintenance work as well, not just inspection. So at the moment, we have all the technologies to enable this autonomous end-to-end robotic inspection. But what we are working on and building on is this closing the loop, right, with the real world from the digital side through manipulation. The industries where these mobile manipulators are interested in for is for instance, metals. So you have steel manufacturing, aluminum recycling. Those are typically also indoors in the halls, but pretty tough, narrow environments made for humans. Then in mining, where it's sometimes outdoors, it's pretty dirty around. Things are changing all the time. Oil and gas, you have offshore platforms where you don't want to have humans. Also in chemical plants, often you have explosive gases in the air. That means the robot is not allowed to ignite these. So you need to certify the robot equipment in order to prevent these explosions. And then you have power generation, where you have various fields, areas like wind offshore energy or nuclear power or gas power plants, etc. That's where we are deploying today our robots and looking into it. So the industrial environments are pretty, as I mentioned, quite narrow is one thing. There are steps, gaps, and so on. There's always stuff around. That's why you need legs. There are different ground properties, right? There's gravel, there are water puddles, etc. You have a lot of varying environmental conditions. So indoor, outdoor, there's lighting conditions changing, but not only that, right? Every equipment looks a little bit different, etc. And it's often areas where you really don't want to go, also for a short amount of time. So legged locomotion is basically manipulating ground reaction forces, right? So you have to deal with irregular terrain, and our robots are able to do that. You will see in a minute, thanks to AI, slippery ground. So you can look at the robot, right? It's basically a robotic hand with 4 fingers upside down, and you manipulate the ground, etc. And this capabilities, super robust, were enabled by deep reinforcement learning techniques. So today and even 2019, we delivered the first RL-based controller to our customers that has been trained in simulation. So we have a neural network that basically coordinates all the legs and the actuators to achieve these high mobility capabilities of the robot. So they outperformed all the model-based controllers so far. What I think Locomotion is a much easier task, and what you see with Grippus, etc., because I think we can achieve satisfactory performance by only using geometric information, right? It's sufficient for navigation. I think even the use cases that we are looking at is where you really want to incorporate semantics as well for obstacle avoidance, etc. But for the fundamental manipulation skills or locomotion skills, RL does the job, so we can replicate the geometric space in simulation and train on that, and then do a sim to real transfer directly, and it works. What I believe is that there is a lack of abundant data for real-world applications for mobile manipulation. So current AI models trained on online and mostly lab data, they don't generalize well to our industries, to our world. So it's not just robot data that is missing, but also understanding industrial environments. I can show you 2 examples. So as you know, our robots climb stairs, and this is very important, and you need to make this really reliable, right? If the robot makes a mistake, it falls down, it will most probably be damaged, like us, we're getting hurt when we fall down the stairs. And so to achieve this, this capability, the robot needs to understand the environment, where to place these feet. So you need to capture with the perception system these stairs. But however, in these environments, in industrial environments, you have actually a lot of graded floors, metallic and reflective structures, see-through stairs, etc. Typically in our households and so on, we don't have these types of stairs. And if you look at how we get this information, how we make these mappings, is we use stereo depth estimation. So we have stereo cameras with actually active ones with IR projectors, right? You get 2 sets of images, and then you run like classical semi-global matching algorithms, etc., to create the depth match image. And unfortunately, these methods, right, they have their problems with this kind of environments. So you see a lot of outliers, you see reflections, and you end up with missing data. So if you look at these stairs, the robot does not know how to get down, where to place, because it has just missing information. So in the past years, there has been quite some progress on AI-based models for stereo depth estimation. So let's use deep learning, right? And if you look at those models, they don't work out of the box. So we compared the few at the Cray stereo that was trained on real and mostly synthetic data, and the NVIDIA model that is open source or that you can download and test that was trained on real data and also synthetic data. So if you look at these environments just in our lab, right, you clearly see in the middle of the ramp, there's Grea has a hole in there, and there's missing data on the ramp for the lower model, etc. So they and also if you look at another situation, we have these reflections, right? Again, you have a hole in the floor, you have missing data, you don't see the rails, so you fully, etc. So they don't work out of the box. So you need to fine tune them and optimize them for these environments. And these are just nicely trained models for a very specific task. Our robots, they do gauge reading, right? So they read pressure or temperature. And the way we do it is we use specialized deep neural networks with a classical pipeline, object detection, interpretation, and then use the train deep neural networks on synthetic and real data, and that works very well. Let's look at it if you use these large general purpose foundation models. Basically, it's a VQA problem, right? So here, just an example, we tested other models, right? If you ask what is the value of this gauge, well, it definitely says a wrong number. that doesn't work. If you look at other pictures, it's a bit harder to see, but again, it's a wrong estimation. And so we thought about what about reading a watch, right? So can it predict the time? And if you ask that, it's quite funny. Most of the models and most answers are 10:10 is the answer, 10 o'clock, which is definitely wrong in this picture. And if you look at, again, if you ask, like, what would you expect the price of this watch? It's fairly accurate. If you ask what is the name of the watch or the manufacturer, it's pretty good. And this is because it's trained on online data. And there, typically, you see a lot of watches that show you the 10 past 10 and so on. Just a little example. So which data is best suited for which purpose, right? That was one of the themes questions. And as you all know, we are working along the data pyramid from simulated data that is basically defined rules, right? So the physics that we use for locomotion training, and then the synthetic data that basically resembles the real world, and then eventually use real data. And the trend is to flip the pyramid, right? All the foundation models, imitation learning use real data, whereas reinforcement learning is happening mostly in simulation, and then you do transform that. So I don't have an answer for this, right? What is best suited? I think depends on the methods and so on. Ideally, collecting real data is difficult, but one thing that I think people don't talk about is about what about data for verification, right? And I'm not talking about checking the algorithm, but it's about checking the final system, the final product. And there's more like, AI regulations coming up, such as the European AI Act, that will require data for verification and transparency to prove that your system works. And how do you test and verify manipulation, right? Because real world testing is also very expensive. We do that a lot just for the locomotion. And so we run thousands of tests with a specific set of stairs and obstacles. We run 1 week reliability tests. We run 24/7 tests outdoor on a facility to ensure that the system works properly. And there you eventually want to test also on a variety of environments. And you need to make sure that it actually works in the environment where you deploy it, right? How do you ensure that? So you also need data for this. And what we're at the moment focusing on, especially for locomotion, is that we are investing in simulators. We're using Isaac Sim to train the controllers, but also test. We're extending that to more, realistic and photorealistic environments, so to say. Let me show you some examples for manipulation. What are we looking for in these environments? There are typically doors everywhere, not everywhere, but often you find a door, and eventually the robot should pass the doors to increase the site accessibility, right? So we did a research project with ETH Zurich together. There's also a paper now at CoRL presented. But if you look at the real world examples, right? So we can build this door, and this door is actually a dynamic object. So there's a locking mechanism that you often have with fire doors, etc. Then you find this funny, doors, a door in the door, and you need to also ensure that it works in these edge cases, or you need to press the button to open elevator doors and so on. And then in nuclear settings, you have even super heavy doors that you need to change the behavior to open these doors eventually. Another application or use case is to open doors for cabinets or panels to do inspections of electrical cabinets. And there are, again, right, people are opening kitchen doors often, but then if you look into the real world, you have this kind of doors that are also at different heights, with different handles. And some are really, really difficult, right? But this one, you need very fine, precise manipulation to push it and to open it. So you want to go through heavy doors, but also open very delicate doors. Another use case is taking samples. So humans go into the facility, take a bottle with them, and then they basically push some buttons, open some valves, and then attach the bottle, and then they get the liquid out of it, and then bring it back to the lab for further analysis. That's a job that is done routinely, daily, etc. And this is something where our customers are looking for automation with a robot, right? So there's the IRA challenge that happened this year, and it will happen, I think, every 2 years. It's quite interesting. So it's the chemical industry that proposes some challenges, some tests where you can participate. One of them was this taking samples, but again, it's quite a simplified environment. So here you have one type of thing, and if you look at the real world, right, they look all a bit different. You have different location things. You have different types of valves and bottles. Often, sometimes very complex. Also, here it's another version offshore where you have to deal with some things. What you have seen in the past, right, at the DARPA Robotics Challenge, they put together this opening valve. At that time, people have been working on solving this problem, and the solutions were all that you had a human operator in the loop, and they did some template matching, so having a CAD model, putting it together so that the robot knows where the valve is, and then running some open loop control actions. I think today we have better methods available, but still it's a challenging problem because there are different types of valves. Some valves you just need to turn halfway until it's open, so you need to double check that. In different situations with different handles, when there's also this type of lever valves, etc. Where sometimes the robot needs to really adapt its full body in order to reach that valve. So it can be in very tedious locations. We talked about, and I think I heard this number, I'm pretty happy with it. So it overlaps with my observation, right? If you look at all the academic work, is about the average success rate is around 80% of the deep learned solutions from manipulation, but that's not enough for industrial applications. So the problem is not solved through real world adoption. So deployment requires typically 99.99% reliability, or in manufacturing even more. And this is about the quality of performing consistently well. And this includes various aspects. On one hand, you want to have the hardware that it's durable over the whole lifetime of the system, right? You've seen in the morning they talked about smoking hands. And then another aspect is robustness. So again, it can deal with adverse conditions, variabilities and uncertainties, etc. I think there the focus is clearly, I see that. And then also resilience, right? Some people say like, yes, okay, this technique comes out with some emergent behaviors that the robot can recover from failures, right? It cannot pick something, so it tries again and so on. But you also need to ensure that this works fully, right? That you can guarantee that works if something goes wrong. So if you open a valve and you want to take samples, but then you fail to close the valve again, then you will drain oil onto the floor forever. So you need to have a high success rate. So you need to detect it, that it went wrong, and then you can close the valve again, try again. So in academia, right, people mostly focus on repeatability. So that's the success rate, but then there's also, if you have different users and different environmental setups, this is another effort to do. So how can we collect informative data in the real world to work on these topics? I think one challenge that we face is that critical infrastructure has very strict regulations. So in nuclear, for instance, so there we need governmental initiatives. Often also our customers, they have very confidential sites, so you don't want to share, so you cannot even bring your mobile phone to take pictures because they don't want competition to copy their processes, etc. So that's also difficult. But what is also difficult is actually to capture all the negative events when things go wrong, right? Failures are super hard to capture. And what we're trying to do is well, we deploy robots for simpler tasks, that is inspection, etc. Then we can collect environmental data automatically. But it's a slow and tedious process to get the permission to do these kind of things. So it remains challenging. There's also a question about which sensor modalities, right? If you look at how human maintenance staff do their job, they often use a combination of visual, audible, and tactile sensing. So they check typically which pump to inspect by just listening to the sound, the one that runs makes noise, so they can check that one. Closing the valve, they look at the field of force resistance, and then they typically confirm the success rate by reading gauges. So it's definitely important to go beyond visual feedback for technology adoption. Another question is about how to solve the problem. Should we do it in hardware or software, right? And my suggestion is really go, and it's also our approach, go with realistic high-performance hardware, because that will provide enough sufficient challenges for the algorithms. And we did that in the past as well, right? We built this high-performance series elastic actuators for accurate and precise torque estimation and control that enabled us a paradigm shift in manipulating in leg locomotion by running force control, enabled whole body control, model-based methods, right? And then we worked on other algorithms, so we came up with learning-based control methods. And that one, they don't need any more this torque control. So there's a paradigm shift again to the position control, and you can eventually build low-cost hardware. So that's an end effect. I think I would still go this way, right? Use good performing hardware, solve it for real, and then we will see from there how we can get down with costs and work with shitty hardware. Another problem that I would like to raise is in these environments is restricted connectivity. We have computational constraints, so there's really a barrier, I think, to adopt large models today for mobile manipulation, because we have a lot of trade-offs. So the robot needs to have all the compute on board, and that means you trade off, right, between compute and memory and latency. So offshore, it's really difficult to run stuff in a cloud to make the ad hoc decisions, etc. Often what people don't understand is, yeah, you can increase the battery capacity and then you have more power available. However, the problem is actually the heat, right? So if you deploy robots in 55 degrees, to get rid of that heat is pretty difficult. So you need water cooling, etc. And that increases space and weight constraints, or needs even more. So adding a beefy GPU doesn't work for our use cases. And in fact, actually, as you should know, cellular telecommunication is pretty unreliable and does not scale well. I mean, there are so many sites available today that are not connected at all. Improvements in energy efficient hardware serration are not that incremental, or are incremental, and are so running really these big models is not feasible yet. And I think also the model distillation that comes with additional performance loss needs to improve massively in order that we can deploy these models, these big models. But at least it's nice to see what's the performance limit of this model, what works and what not. So coming towards the end, so one last thought that I'd like to share is that functionality is actually only half the story, right? So when you're working on algorithms in research, it's about solving the functionality. This is still a hard problem in mobile manipulation. We try to make it as a community to run to create general purpose algorithms, right? For that, you're looking for data in the wild, right? How can we collect that? But again, it's, as I mentioned, it's tricky in terms of gathering sufficient amounts of and sharing it also with third parties. It's not so easy, even though I would love to push that further. I think that helps a lot, and it's a great start to share lab data. The question is if this is really enough. But then when it comes to building applications, right, make it work in real life, you should also consider not just the operation lifetime of the product or the system, but also the deployment and development side. So we talked about reliability, but also safety is important. You cannot damage equipment or harming people. That's not acceptable. So you need also to prevent that. And then what is often forgotten is the usability. So how do you deploy it, right? So when we select algorithms, we always need to consider the usability and the deployment phase. So you need to wear a lot of equipment. It's very loud environments, hot. You don't want to spend time in there. And so and typically it's domain experts that will deploy the robots because they know what needs to be done, right? Not roboticists. So eventually our customers, our use cases are about no site adaptation, really spend only a few hours, not 20 hours, and tele manipulation and collecting data for imitation learning. And then for the development, it's the fourth priority is kind of cost. So yes, we can build up some mock-ups in the lab, etc. But again, it's also costly to post-train, fine-tune, and the question is whether we can actually bridge that reality gap. With this, I'm at the end of my presentation. I hope I could provide you some new insights on the problem from real-world perspective. There's not only pick and place and assembly or household task in the real world, but these are exciting times, and I'm looking forward to the next generation of learning-based algorithms to solve mobile manipulation in the wild. Thank you.
We're running into the coffee break. Maybe we'll take one question. Yeah. Yeah. Okay, I guess I will repeat the question. The question is, could you go through the process for deployment or the challenges that customer would like to tackle? Or
yeah, I mean, through the deployment, right? At the moment, the way it works with our robots is you go there, and first of all, you need to some basic training how to run the robot, but then you need to steer it through the environment. It creates a map, and then you set up the waypoints for navigation, and then you need to program the point of interest, like inspection points. So you need to encode which position are the measurement instruments, for instance, where you want to take a measurement and inspection. And then you need to test it, etc. If it works, can a robot really walk through that environment, etc. And that already takes it depends on the site, 1 or 2 days, etc. And this is something they feel that it's very painful, right? So how do you program then? How do you tell the robot what to do? Like if it's about taking samples, you need to teach it which valve to turn and what to, where to put the bottle, etc. And there you have really limited time. You cannot spend 20 hours in collecting data. Does that help you?
Can we ask you one more question?
Sure.
Yeah, so you said that the depth maps are not reliable because the staircase in industry environments have holes and you showed us how the stereo camera fails. So what was your solution there?
I mean, you do a lot of heuristic engineering, right, to circumvent some of this. So do you take multiple methods, etc.
Okay, so you don't do anything with your RL, let's say depth-based RL something in simulation. Or maybe you build blind policies or something, I don't know.
Yeah, actually, we train the policies so that they don't rely fully on the perception side. I think that's a very great strength to the robot. If you can hide the sensors, and then the robot basically tries to climb down the stairs blindly, and that works also quite well. When you really want to drive reliability up, so you want to use that data.
Got you. Thank you.
all right, thank you again for the talk. Yeah, I guess now we have to Yeah, so I guess now we have the coffee break and the poster session. And we'll come back with 2 more talks.
3 more.
3 more talks.
So in terms of the products,
I think it's totally open. You can just
to connect to Zoom, and then you can put it into the HDMI. Yeah. Yeah. So the microphone is. Yeah, this you can behind the because one microphone for the audio in this room and that are on YouTube. This one you can yeah, yeah. And this one you can just put syntax. Yeah. The USB and like something.
Should we wait or should we?
So it doesn't know, but I was disappointed in my it does continue.
Yeah. Can you hear me? No. Are you recording or no? Yep. Okay. Because I want to show something. Then since you're recording, then I will.
Okay, so hi everyone, welcome back to our sixth or seventh talk for today. It's my pleasure to introduce Professor Mohsin Kaboli. He leads the AI, Robotics, and Cognitive Vehicle Research Lab at BMW Group since 2018. He's also professor at Eindhoven University of Technology, where he leads the Embodied Interactive Perception and Robot Learning Lab. Mohsin received his PhD focusing on interactive tactile perception and learning in robotics from TUM in 2017. His research interests lie at the intersection of embodied robotics, visual tactile interactive perception, machine learning and control, with applications ranging from mobile robotics to robotic grasping and manipulation and human-robot interaction and collaboration. He has received numerous awards, such as the Best European PhD Thesis Prize in Tactile Robotics. He was also finalist for the George Gerald PhD Award and the ICAR 2023 Outstanding Paper Award in Perception. Looking forward to your talk.
Yeah, thank you very much for the nice introduction and invitation. There was very nice talks basically today, and we are a little bit different because we are not using simulation that much. We are basically working with a real robot, and we have our own basically problems. So for me, when we are talking about let's say the autonomous system or intelligent system from a very, very high level, I'm considering several blocks, means the system needs to have a multimodal sensation and perception, interaction, learning, decision-making, and planning at the same time, you know, as a complete systems. So I've seen many groups basically are working only on the learning part. They are using different methodologies, you know, RL and so on. But for me, it's a bit different because for me, if we will not have a complete systems, so we need to deal with many data, you know, millions and millions of data. And especially when you're working with the robot and different sensing modalities, you will not be able to collect the data. For example, using the hand, using a touch, you know, if you slide your hand on a rough object after 10 times, start bleeding. So you cannot collect that much data, right? Like a vision, because with the vision, you can have millions of data and nothing can happen, right? So this one was my interest to find out how the humans basically intelligence develops. I have been in Japan and we were recording data from the human fetus. So to find out what is the first sense in a humans, we cannot see, we cannot hear it, but the brains will get developed based on the body movements. And the body movements, basically the information comes from cutaneous information and proprioceptive information as well. And based on that, our brain is start getting developed and it gets folded, basically. An interesting thing is here, even there are some syndromes or diseases can be recognized based on this kind of a movement before the birth. So this was our motivation in order to develop a baby robot. This is a Nabi, is a 9-month-old robot. And the robot, this robot can see and can hear also the objects when the object was moving, means sound localization as well. But if you see, the robot cannot really move. You know, it's a kind of a robotic movement because the sense of touch is missing here. So the robot, even here, the baby robot cannot even differentiate the body part from the word. It can be extended, for example, the word can be extended of his body, or can be, for example, something completely different. Let's move on here. So what we basically find out from this study was the sense of touch plays a very important role in our daily life in a human, from grasping an object, manipulation, realizing the object's properties, whole body interaction, and social interaction, and also the self-awareness. If you see, this is you, this is not because of the vision, because of the tactile. This is me. This is basically because I can differentiate my hand, you know, from the desk here. So if you see these days, there are many also the robot in the industry. This is the Amazon, this is BMW, and also there are other robots here. But if you see, still humans are working, right, in different domains. The reason is even our robot is not, can see, for example, here the strawberry, but is not able to pick it because cannot realize the properties and can easily crush it. And what is the motivation for me, you know, when it comes even to grasp and manipulation, it makes sense when the robot and humans, they work together, right? And one of the reasons we would like to bring also the sense of touch is the safety as well, because the vision can fail. Even like a few years ago, someone has been killed in Volkswagen, even when working in one of these cages. Even there were many security cameras and so on. And the other thing, basically, if you see here, this is there is no vision here, and this is the grasp, and the robot can easily crush the object. And the idea why we are working in this basically pure tactile, because we want to realize it, what is the capability of tactile sensing in robotics, you know, because this one has not been investigated before. And these are basically very difficult tasks in robotics because the object is transparent and deformable, and the center of mass of the object is dynamic, right? So here the robot can grasp an object, which we call it, even in human, is called reflex grasp, but is not able to manipulate because cannot basically detect sleep and correct the force regulation here. This is the method basically we have we proposed, and this is the real-time sleep detection without having any prior knowledge, and force regulation. And I think is a correct video. Let's see what will happen then. Yeah, and if you see here, this is very difficult. In a real time, the robot make a sleep estimation, detection, and force regulation, and pure tactile. There is no basically division here. And the second thing basically is if the object is very heavy, you know, if it's easy, light is easy, right, to hold it in a hand without crushing the objects. But when the object is very heavy, there is basically two options: either to crush it press means to apply more force or let it go, right? But the other thing, basically, when it comes to the in-hand manipulation, we are ignoring is the role of our arm, right? Like a human. So how can we get basically hand and arm manipulation at the same time? We are using the human strategy, means when the robot realize, if you see it's shaking, right? Because it's very difficult to grasp the object without crushing the object. Is start moving the hand in order basically to compensate the weight of the objects and the sleep, as well as basically crushing the object by moving the center of mass position here. This is basically the full body robot we had. We have developed, this is the tactile sensing, and we call it electronic sensing here. So if you see, the robot can easily move with the hand or with the feather, right? And if you get close to the robot, will not kill you, definitely. And the idea is how to get the robot's hand and teach the robot how to write, right? Or to do the pick and place. And to have intuitive, basically, the learning here. However, there are many challenges here when it comes to the real-time processing and basically bringing both vision and tactile, which partially I will address here if I will have time. And if you see here, basically, we developed this one in our lab a few years ago. This is a multimodal tactile sensors, which has a proximity, temperature sensors, normal and shear force. We can measure it. And the idea basically for me is when you are developing any methodologies, it should work across any sensing technology, because we have different, here the tactile sensor, they measure like a shear normal force. But if you basically change the sensors, the methodology or algorithm will fail, which basically this is not our interest here. And this one was the baby robot we had with the full body and had 5,000 tactile sensors. And the idea for me, or let's say the goal was to have whole body manipulation and interaction, means when the robot is rolling over the surface, could realize the properties of the object based on the entire body. And of course, there are many challenges here, which we had to answer, basically the address. This has been published in the Science Robotics. And basically the computational part is one of the main problems. And when it comes even to the human, if you want to inspire from the humans, in human, we have two parts. We have CNS and PNS, is peripheral neural basically sensors, and also CNS, which need to be combined together in order to address the entire basically computational complexity here, which at the moment we don't have it in the robotics. So going from pure tactile to vision and tactile, I think you may heard these days about the visio-tactile topics. Basically, this is a bit different than what we are doing, because usually the visio-tactile these days is called, to put it in this way, the tactile sensors at the moment, which now you can see even here, they are using the cameras, they put a layer of the silicon and they call it visio-tactile. For me, this is not a tactile sensor. This is a camera, it's nothing, right? So because with the reason is the tactile is action conditions. You have to have a sensor which you are interacting, you will get an information. And when it comes to the vision and tactile, and the tactile is not the slave of the vision, is not only the contact. And we need to get the tactual properties of the objects here. For example, when we are talking about the vision and tactile, the vision will give kind of a global features, like a global shape. So when it comes, for example, to the tactile, we need to know the inertia. You need to know the center of mass, stiffness, textural properties, which cannot be received via any sensor except tactile with the proper actions here. And the second thing is we do a lot in hand manipulation, but in order to get to know the objects, right, the properties. But if you see the toddlers, even by pushing, a simple push or pull can get a lot information from the object here. which we call it a simple non-prehensile manipulation, right? So we have one of my smart students who is sitting here, French one. Basically, the idea was of him basically to solve part of the manipulation problems, but using non-prehensile actions here. So if you see basically when it comes to the manipulation, we are considering very hard task, which is getting, let's say, manipulating the objects in a clutter. So we divided the task we have at the beginning in 3 parts. The first part basically is active decluttering in order to find the target objects using both vision and tactile, and to use an active perception. So again, collecting the data, you see people are collecting a lot of millions of data, but this doesn't happen in humans because we have an active perceptions, and the collecting the data is based on uncertainty reductions. So our idea is the system, the robot has to decide how much data is enough, not a human, right? So if even with 1 shot, 2 shot is enough, the robot can understand it is enough. We don't need to get more. Otherwise, we had to go, the robot can collect more and more here. And the second part basically is the shape reconstruction using both vision and tactile, especially if the object is partially occluded, right? Because you cannot see, you need to touch, right? And then the third part basically is a robust pose estimation, regardless of the object properties. If the object is transparent, non-transparent, if it's articulated, soft, or so on. This is the framework we propose. The first part basically is decluttering. The second part is object reconstruction, and also the robust pose estimation. I would like basically to put some to make these areas, which we call it the vision and tactile calibration, bold, because when it comes to the simulation, vision and tactile, the calibration between vision and tactile is already given. But when it comes to the real robotics, we don't have that one. And for the human, in a real time, we are learning vision and tactile calibration, hand-eye calibration. This is the reason, even if you are simulating everything, when it comes to the reality, it doesn't work. And this part basically is the robotics experiment we have. Here we have the scene graph, which is extracted from the object in the scene. Here we have 2 robots, where this is the panda and basically you are. We call it the shared perception here. They are working together, collaborating. And this robot can actively see basically the objects, and the other one has a tactile sensor, which is it a contactile? Or yeah, this is a contactile sensor here. This is the decluttering part, and the object, basically the robot will decide either to push, to push the object, or for example, to grasp the object in order to declutter the scene. And later on, we have an active perception. The robot actively looks into the scene to find basically to reconstruct basically the shape of the object here. And this is based on the information gain. And then there will be a part, basically, the robot cannot visually see the object if you see, these areas, which is basically more complex or is it transparent, and then start touching. So then we will have both vision and tactile for object reconstruction. And again, for the tactile here is an active, is not a passive, because the robot knows where to touch, right? And how many touch sample is enough for reconstructing the object here. Okay, and this one basically is 5 minutes less, but I have to go fast. So, and then we have here the object pose estimation, which is a real time. And then the gradual is shuffling. Basically, you will see we are able to, the robot can estimate the pose. These are the, and basically now we are moving also to the articulated objects here. And what we want to do, basically, this is the TRO is submitted, is the visual tactile based tracking and goal-driven manipulation of the unseen novel object here. So I will go a little bit faster this part. And if you remember, I was talking about the non-prehensile manipulation. For example, if the object is very heavy, so how we can manipulate? You cannot basically take it in your hand. And the idea is how we can estimate the properties of the objects. And the objects can be homogeneous, articulated, or heterogeneous objects. And to estimate the properties of the objects here by vision and tactile and simple, basically push here. This is the annual one. I mean, here basically this he proposed the predictive visual tactile interactive perception here. This is the story I already talked about. It is pose estimation and so on. And here the robot will decide either to push or pull the objects in order to estimate the physical properties basically here. This is the methodology we have. This is, we have basically the learning part, we have inference, and then on top there is differential dual filtering, having both prediction and update part. So here the robot will basically reconstruct the shape and decide what is the best action to take. And and when basically which action is the best, for example, the push, and then we'll decide where to push and what is the direction, which direction to push in order to estimate the properties like center of mass and so on. And here basically is the update part, and then what anyone developed here is experimental results. So I don't have time, I will not explain it that much. And this is basically the result, which basically is outperformed the state of the art. And the good thing is here, what we have developed, even we didn't train it, for example, here with, if you see here, the video is not working. Yeah, it's here. Even if there will be the out of distribution, because we didn't train it with this environment, the methodology still it works here. The last part, we are working on a cross-modal perception. So if you see in a human, there is an intersection between somatosensory, visual cortex, and auditory cortex. There was a question like 2-3 hours ago, someone asked, if you want to train, we need a power plant, right? And if there will be off, the vision, how we can navigate with other sensory modality. This is very, very valid question, which we have already answered several years ago. So when it comes to the exploration, we have vision and we have a tactile, and with both vision and tactile at the same time, we are building a representative of the objects. But what other people have done so far is like vision and tactile, and then they try to put them together, which is not basically working. And if one of them is missing, and the other basically will support us to still to work. And this is from the brain, what happens. So this is the methodology we developed here, but this is the main core to bring the both vision and tactile, because they are coming completely from different domains, right? Because as I said, if you see it, people are using the camera-based vision is super easy, right? Because they are treating everything with the vision, but this is not a reality. But in a human, or for example, what we are basically working on to make it more generalized, to generalize it, we will bring them together based on the loss function we have developed, and we have kind of a domain adaptation. Just this is, I will put it here. This is the, yeah, basically, this is the visual distribution, and this is a tactile. And based on the proposed loss function here, we are able to bring them together. And in case one of them is not available, the other can take the action here. Here, the system has been trained with the vision, but now we are turning off completely the camera, and we are asking the robot to use only the touch, in order to recognize the objects or reconstruct the object here. This has been also further developed, means if you look at the objects, we are able to estimate the mass or the weight of the objects like a human, right? And even the further development which is in progress. By getting to know the color or the textures, we are able to estimate the friction via the tactile, or the shape. By looking at the shape, we know the stiffness, right? And the size of the object, we know the inertia. Meaning that, for example, if you want to grasp an object, by looking at the objects, you know how to grasp and how much force you need to apply and how to manipulate it, and vice versa. If you are touching, for example, basically an object, then you can estimate the textural properties, or let's say the shape or the other properties, which we call it a cross-modal perception here. And so we are also moving to another domain, which is called human-like perceptions. So without having any labels, it's completely unsupervised. So this is very basically novel. We are working and we try to use, for example, this is the sensor we have developed together with Etienne in Imperial College. And when we are talking about the textures or considering the human's hands, we are ignoring the embodiment, right? Means the fingertips or the skin will deform. And here what we're gonna do, we are trying basically to find out the role of the embodiment and the skins when it comes to the perception as well. And when we are basically learning about the objects, learning about the properties, we want to make it completely to generalize it. Means if you change the robots, if you change the sensors, right? But the perception will remain the same always. So here is my last slide, and I would like to thank all my colleagues, my students. They have been collaborating basically on different topics. So we have also 3 fully funded PhD position. Especially we are working on also the ONN. We are developing completely new neural networks, which is called ONN. It's different than what you have seen. And it's called oscillatory neural networks, and will be on device. And we have some good results, and based on that, we are getting new students, and also we are working on counterfactual learning as well. So it means if the system make mistakes, how can correct itself based on the counterfactual perception and learning. This is completely new. So thank you very much. If there is a question and I have time, then I'm happy to take it.
So I think we have time for 1 or 2 quick questions. So yeah, if anyone from the audience has a question, please. So I actually have a quick question. So for many of the approaches that you showed, I think you had a very modular approach where you have different components in your framework. And also your loss functions often had, I remember one which had several different terms. So I wanted to ask, so were there many hyperparameters in these modular approaches, and also like with these loss functions, which seemed a bit handcrafted? So was that very sensitive to tuning? Did you have to put a lot of engineering effort into making this work?
Did we do that? No. Basically, this is not the hand tune. Basically, what we are trying to know is based on the distribution of the vision and tactile we have. So if you are asking if we use other sensory modalities, to test it here, if it works, we didn't do it, not because it was a little bit out of interest, because we want to focus on the cross modality. more than, let's say, the robustness, or to generalize it, using different sensors and so on. But no, we have not tested yet, but we didn't have that. We didn't have the hyper. Did we have? What is it?
Okay, thanks.
Yeah, because basically, this is the first, the cross-modal, nobody has been worked. This is the first work in robotics community. Nobody has been working. And I have to give basically the credit to Vincent Hayward, who is not here and who passed away like last year. And he was the god of haptics. And we have been working basically with him, and the idea, it comes from him, and we were working together, and the cross-modal was the first work. And now has been basically developed by extending it to multimodal, cross-modal, multi-cross-modal active perception.
Thanks. Yeah, I guess then we can move on to the next speaker, and yeah, we'll see Mohsen again in the panel.
All right. Our next speaker is Katarina Fragkiadaki. She is an associate professor of computer science in the machine learning department at CMU, where her research focuses on enabling machines to understand and interpret video content. And prior to joining CMU, Katarina was a postdoc at UC Berkeley, working with Jitendra Malik, and at Google Research in Mountain View. And she completed her PhD in computer science at UPenn, at the GRASP Lab, and under the supervision of Jianbo Shi, after studying at the National Technical University of Athens. And we're very pleased to have her after the mic works out.
Right, I got it.
Hopefully.
Don't worry. Something like that, right?
Yes, exactly. Yeah,
All
are you good?
Yeah.
Okay, perfect. Then stage is yours.
Great. Thank you so much for inviting me. I'm very happy to share our recent work with you. The excellent topic of the workshop. Okay, so what we'll discuss is 3D spatial reasoning and simulation with generative models for robot manipulation. There are three main ways to supervise robots, right? One that was not that much in this CoRL, but I'm pretty sure is going to take over. CoRL 25, 26, 27 is visual imitation, watching videos and doing, okay? A big part for learning manipulation in this workshop is learning from demonstrations with actions. Okay, you have observations and the action sequences, and then essentially you do some sort of behavior cloning. And then the last part, which it works already very well for locomotion, mostly for locomotion and some local manipulation. Let's say tasks is learn in simulation, scale up with reinforcement learning and core combination of imitation and reinforcement learning, and then transfer in the real world. So yes, so we have seen a lot of works. In fact, the best paper work in this workshop is also a big foundational model of vision and language trained with lots and lots of kinesthetic demonstrations, essentially sequence of observations and actions. We have a big transformers, end-to-end mapping of image and language to actions through, the action discretization or through diffusion, let's say, the action decoders. And one thing that we tried to explore in a work that actually is part of this workshop, it showed up the first day, is how much can 3D spatial reasoning help in robot manipulation? Can we, essentially learn manipulation skills with less data if we reason directly in 3D? So the method that I wanted to discuss with you first is a 3D diffuser actor. It's a combination of 3D scene representations and diffusion models for robot manipulation. So what you can see here is, and I want to walk you through the architecture, is essentially we can perceive the scene with RGBD cameras, and we build 3D feature clouds, which we use to denoise essentially 3D rotations and translations for the robot's end effector. So the first part is essentially the sensing. You have an RGBD camera. The RGB image can be featurized with a standard image encoder. We use CLIP, but we can use other pre-trained backbones, and we don't fine-tune it in this work. Then the depth map, the sense depth map, along with the camera, essentially extrinsics, is used to lift those features. And every 2D patch has a feature vector, so we lift those features to 3D. So now instead of having a 2D feature map, width by height by number of channels, we have a 3D feature cloud, right? A graph essentially of a little tokens, where every token has an appearance vector of the C channels coming out from our 2D backbone and 3 coordinates X, Y, Z. So once you convert your observation into this feature cloud format, one benefit you have is that integration of different viewpoints is effortless. You don't need learning. Okay, of course, you can pass your different views into a transformer or some other methodology to fuse them, but in this way, they're essentially aggregated in a geometry aware way if your cameras are calibrated. Okay, so the relative rotations and translations. You can have more than one views, or you can just have one view. So you build your 3D feature cloud, and then because we want to use, of course, diffusion models to handle multimodality. Right, in imitation learning, every demonstrator has a very different way of doing the task, and so that's why diffusion models give such an enormous push in imitation learning for robotics. That we have essentially a denoising head that takes the feature cloud and takes also a language input, open the drawer, and takes also a noised trajectory or key pose of the robot's end effector, essentially noisy rotations and translations at every time step, and fuses them to predict back the noise. And the benefit of this 3D architecture is that essentially, given your current idea of where your future and effector trajectory would be, this is essentially rendered in the scene, right? So the trajectory tokens are together with the visual tokens, and they are fused jointly with attentions. And these attentions are relative attentions. Essentially, relative attentions means that the similarity depends, of course, on how much the appearance vectors match, and also on the offsets, the relative offset between two tokens, not on their absolute 3D coordinates. This is very important because the coordinate system of those XYZs is completely arbitrary. Okay, so where you decide to put your XYZ center of your coordinate system, and we don't want the results to change based on the change of this coordinate system. So we have essentially translation equivariance built in this architecture. So what you do now at test time is you sample from the standard normal distribution, random noise, and you iterative denoise this trajectory or key pose for some benchmark, which you will predict trajectories from other benchmarks, will predict a target key pose, and then we use motion planners to go there, and you iterate and get your final trajectory out. So how is this architecture different than 2D diffusion policy? She runs a seminal work, like one of the very first papers that used generative models to handle multimodality for learning policies, robot policies. The only difference is that we build a 3D feature cloud instead of using, one or more views in 2D. Yes, and this makes a big difference once you have a limited number of demonstrations. Now, as demonstration goes to infinity, nothing matters, right? You can just do any template matching would work. Now, interestingly enough, there is another paper that showed up in RSS 24, which is called 3D diffusion policy. So, I mean, we took that paper. I mean, there's no, like, as mostly done in robotics papers, you avoid benchmarks. So the authors did not benchmark their work, but we download the code because they actually wrote something bad about our paper. Otherwise, I wouldn't bother to do that because quite a bit of work. So we download their code and we test it on the Calvin benchmark, and actually it didn't perform well. So then the reason we think this is the case is because the essential part is not 3D and is not diffusion. I mean, diffusion is, without diffusion, nothing works. But it is this joint fusion on that 3D feature space. 3D diffusion policy instead takes a point cloud and condenses it into one D vector, and then there is cross attentions between that single scene vector and the action you want to perform. The problem with this is that it completely kills locality of computation. Locality of computation is a very important principle for generalization. This means, your gripper is here, your scene change is there, no problem, because, it doesn't going to influence the attentions on the part of the scene that you care about. So locality of computation, in fact, there is another great paper in this workshop, again, with locality of computation, not on this workshop, on this conference, with locality of computation in the title. So we visualize here some samples from our model. You sample 60 trajectories, and you see that sometimes you have multiple modes, and this is a better result, a better visualization to see this multimodality. Here our graduate student collected demonstrations for putting grapes in the bowl, and sometimes he picked up the green grape, and sometimes the black, and sometimes the dark red grape. And that's why you see those three modes. So all 60 samples are concentrated around those three modes. And you see that we don't hallucinate any modes and we don't drop modes, right? That's the beauty of diffusion models. And of course, diffusion models are getting better and better, and with flow models and so on. And it's extremely exciting. So this model does well on two benchmarks, Calvin and RL bench. Yes, so which is important because usually works either is going to evaluate on RL bench, which is a very geometry like driven benchmark. All methods on RL bench, RL bench encourages using multiple views, which is difficult for a mobile robot to use multiple views looking towards the scene. You can have multiple cameras looking outwards, but it's hard to have multiple cameras looking inwards and moving around at the same time. You need to have the viewing sphere moving with you. It is difficult. And also RL bench predicts key poses, which means, not a trajectory, but rather a key pose, and then he has motion planner to go there. Calvin doesn't do that. There's no motion planner, so you need to predict the trajectory directly. Another very important and very important detail is that here you can predict your 3D, we do task space control, right? So you predict your key pose on the robot base, at the coordinate system at the robot base. There, this doesn't work. You need to use the end effector coordinate system, which translates and orients with your gripper. And yeah, so we did some ablations to understand what exactly is important in performance. So we went from a 3D diffuser actor to a 2D diffuser actor, and now there are two versions of this 2D diffusion, right? So one is the one that condenses the scene into anti-vector, and one that does not condense the scene, and it just leaves it around as a 2D feature match. And both of them have a lower performance. Now, another thing we did is we went from relative attentions to absolute attentions, and again you lose 10 points. There may be a way to get around this by using insane amount of translation augmentations. Yes. And the important thing about this 3D is not that you need multiple views. In fact, things work really well from a single camera. The important thing is this that I told you, that you render and your gripper essentially during this iterative denoising in your 3D visual tokens, and you contextualize it in this 3D aware way, okay? Now, the question is, here are some results from RL bench. And the question is, are these 3D inductive bias important as the amount of data scales? And to be honest, I'm not sure. We're trying to do exactly that, like to throw really insane amount of data on this 3D vision aware language condition policy, so it becomes a foundational policy. Once you put tons of data, you put the pre-trained language, but going became very foundational. But one problem on scaling the data for those 3D policies is just that we cannot find essentially the calibration is difficult, right? So it's hard to find large, like the bridge data or open embodiment data. The calibration is not there, the robot's calibration. So basically what we need to do is we take those videos and ourselves, much like a human does it, or lift them to some 3D, and that 3D doesn't need to be very metric, and then we hope that we'll be able to use them in this way, okay? Yeah, another thing that I want to mention regarding are 3D inductive bias important or not is the following. You can totally imagine you have little data, then you train a policy with more inductive bias that kind of tries to generalize more. Then in this way, essentially, you get more data, just by bootstrapping, and you can totally distill your extra training data into a policy that doesn't have inductive bias, that is faster to learn and so on, faster to train, faster to do inference, so on. So this is totally a legit way of essentially densifying your data, as opposed to going from, whatever demonstrations humans given me in, a policy that actually, doesn't generalize very well. So this is just an extension of diffuser actor to bimanual tasks. Yeah, so this one is on the PERAC2 benchmark, like without spending any time, as you see, we're at the top of the benchmark. This is a recent benchmark, like July 2024 came out. And right now we're also got a, this mobile aloha robot, because it's very easy to, give kinesthetic demonstrations, and we are applying the same thing in the real world. Yeah. Now, of course, spatial reasoning is not going to, without data, nothing is there. So the question is, how do we really can scale up robot data? Of course, collecting more kinesthetic demonstrations would be great. Figuring out, exploration in the real world is also great. Figuring out visual imitation is for sure the way to go, okay? But this is not what we'll discuss now. What we'll discuss next is what about simulation? How can we scale up data in simulation instead, okay, and take advantage of simulation? We have a method that showed up in ICRA 2023, and we say, can we use generative models of language and vision to, scale up simulation tasks, assets, environments, and so on? So the way it works is it has three parts. I'll really briefly discuss. We generate assets from 2D images to make 3D meshes. We ask language models to give us task specification and reward functions in Python, which we then optimize with reinforcement learning, essentially PPO. 2023 was a particularly exciting year. The year where we were able to do in the wild 2D to 3D lifting. Any 2D image now can be lifted to 3D by essentially taking a differentiable 3D representation, projecting it down, computing the projection error with the actual image that you see, projecting it in other viewpoints, and then put generative priors. Essentially, you want your rendered images to have high likelihood under your pre-trained image generative model. And here we're using a view condition generative model, the very famous 0 to 3D model. And first, you can train an nerf, and then you can also, convert it to a mesh and train also a differentiable tetrahedral section. And that's it. This is your asset. So you can lift all assets to 3D now, right? Any piece, any type of a vegetable that you cut, like piece of vegetable, whole vegetable, etc. We were wanted to build supposedly a simulation for food for a Sony project. We had a gastronomy project, and we couldn't do it up till 2023, where we were able to do this fitting of differentiable 3D models using reprojection error and generative priors from diffusion models, from image diffusion models. And 3D geometry is not enough. You also need physics, and you need size, because 2D images don't have size of the objects. But you ask language models. Also, tell me please the size of the pumpkin. What density shall I put? What type of material is made of? And give me all the numbers that I need to put in my simulator. And they do give extremely plausible results. Now, we don't need to get stuck on those language models. Once we start building our own databases, let's say, of materials, and we have a nice zucchini and a nice pumpkin and a nice knife, etc. Then we can just ask, does it feel more like a knife, or does it feel more like a pumpkin, right? So you can bootstrap yourself. Not that I have found a lot of mistakes on the LLM predictions, but we can totally imagine that, yeah, we can bootstrap. And then now this is not enough. We have assets. Now we need to specify tasks to solve and reward functions, okay? And one way that we hope to do that is again to ask language models. So the prompt is very short, and it fits all in this slide, because there is this black magic on the prompt. So this prompt is actually quite simple. First, you need to tell to the language model what the simulation contains, what assets and what are their parts. Then you need to say what is the API to interact with the simulator to get the locations of different parts and their states. And then you need to say, tell me now, this is my scene. I told you what's my scene. List for me a set. So this is the example that we also give it one example of what's supposed to do. give me a list of meaningful tasks. And here says, oh, you have a microwave, so it makes sense to open the microwave, place a cup in the microwave. And this task has also subtasks. So it also does the temporal decomposition for you, which is extremely important for reinforcement learning. And then once you have the temporal decomposition, the example continues and tells it how to, code up reward functions. For example, approach the microwave door and so on and so forth. And then you also describe now a test environment that is very different, has a sanitizer, and the language model can predict the tasks, subtasks, and reward functions, which now you can optimize with reinforcement learning. And the big lesson from this work is that this task decomposition, the temporal task decomposition, was actually extremely important for RL to work. Okay, you can see here, we have this put the green pepper in the left door of the refrigerator and so on. And you need to open the left door, pick up the green pepper. These are the different tasks with the corresponding reward functions, and optimizing them in sequence one by one is able to achieve the task. While if you have one complex reward, and you just then you cannot, without this temporal decomposition, you will not be able to essentially achieve the task without guiding PPO anymore. Now, I don't think this is the only way to guide PPO. I think you can totally do visual imitation and guide it. And in fact, there are many works in this conference, and we're working on this as well. This one does not use any visual guidance. It's all a language model guidance, okay? But for sure, there is a lot of world knowledge that we can exploit. Having said that, for some tasks, for example, pouring, we were not able to get it with language models. It's much more natural. Just watch a demonstration of pouring, just lift it to 3D, put there some goals and rewards, and try to achieve it. It makes way more sense. So in any case, with this method, we were able to scale up demonstrations and collect all this data completely autonomously. And then we did this again with more and more diverse tasks, also for locomotion, with different robot morphologies, some mobile robots, some just static, some mobile manipulators and so on, better renderers as well. And we think that this is one plausible way to scale up simulation. Of course, it's not just asking language models, is going from video to, and I'm going to show you in a second. One such work. Now, one bottleneck using simulation is simulators. There are fantastic simulators, and they're actually getting better by the day. But one, let's say, downside is the interface. This is how much you need to code to add one Franca model in Isaac Gym. And Isaac Sim is also worse. So this makes it very difficult to build up scenes and really create things in these simulation environments. So Xian Zhu in my lab, along with amazing, incredible collaborators across multiple universities, have been working on trying to put out a new simulator. So he started with a fluid lab, essentially just to using particle simulators to model fluids. And now they are building this simulator, which is supposed to come out in a couple of weeks, Genesis. Genesis can simulate rigid, liquid, gas, deformable objects, thin objects, granular objects, all types of objects. They have, coded up all different physics solvers, and it's written completely. It doesn't use any NVIDIA physics engine and so on. It is written from the ground up in Tai Chi, which is a GPU parallelizable programming language, came out in 2018. They have two beautiful renderers. So the visuals from those renderers were used in the previous work, which you can change only with one line of code. And it is extremely fast. Now, for the particle part, it's only twice fast the previous simulator. But for the piecewise rigid part, it is much faster than, Mujoko, which is the most, of course, there is Drake, which is the most accurate physics simulator, with particularly slow. Mujoko is one many people use for reinforcement learning. Genesis is much faster, okay? And the reason for this is the collision checking algorithm, which has been, parallelized in a better way. And the assets are represented using sign distance fields, and the GJK here has much more much more accelerated, let's say, implementation. And essentially, all this is just extremely incredible engineering and great collaboration between Xian's and the team and Tai Chi developers. And these are some visuals, and we've already trained our first quadrupeds on this simulator, and they're working. And of course, we want to train all other robots there. Now, maybe the last thing I want to say is that yes, we very much believe in this paradigm of real or large-scale simulation. We don't think language models is the way to build simulators, although Xian is extremely excited about it. We also believe a lot in videos and understanding videos, lifting videos to 3D, and then porting those assets in, let's say, in these simulation environments. And these are things that we're working on. And we think the tools are mature. All right, all these generative priors are there and working, and things are mature for this to happen. So the takeaways is the 3D inductive biases help generalization. That generative simulation, this combination of generative models and simulation environments, can generate a lot of training data for manipulation. And Xian and his collaborators are working towards better and faster simulators that I really hope that you find useful and helpful. Thank you very much. Yes.
Is 3D construction also nice with 3D inductive bias? It's like the next big thing to have like dynamic 3D reconstructed scenes or?
Yeah, a very good question. So I think so we are not using we are using the features from the image, which is what every RGB policy uses, and then we take that feature vector and we just shoot it in a 3D space. So we don't try to complete or anything, or we don't try to fine-grain point cloud. It's actually a feature cloud. Do you see? So it's not points, it's features. Now, whether I believe in 3D reconstruction, absolutely, but I mostly believe in making 3D reconstructions in simulation worlds, dumping them in simulation and simulating them and get data from there. I think if you just want to feed an encoder to your policy, it can just totally be such a 3D feature field. And I think there is a confusion because many people talk about like, oh, you need to move your camera all around to capture the whole scene. And totally, absolutely not. The same way 2D policies can work from a single view, and that's totally fine. 3D policies can also work from a single view. The only difference is that, maybe the gripper and the scene are mostly more explicitly, fused in that world 3D space. Yeah, thank you for your question. Yes. The base was moving because it was a mobile. Yes, but so this, yes, I mean, some of them are static manipulators, some are mobile, and so on. Yes. Other questions?
We would have time for one more, I guess.
Yes.
Yeah.
Yeah, exactly. You don't need temporal consistency at every time step, much like a 2D policy at every time step takes an image and then spits out the action. Here, we just, in every time step, we take an image, we take the depth map, we just shoot some features to 3D, which is super approximate, right? Because every patch is pretty fat, so it shoots somewhere in 3D space, and that's it. That's all that happens. It's very similar to 2D policies, but I think because the network doesn't need to figure out how to coordinate 2D and 3D, you just need less training data to learn the mapping. Okay, yeah, yes, this is it. Now, yeah, if you want to learn now world models and how deformables deform and how they move, etc., then of course you need to figure out the 3D point tracking of those, which is much harder problem as opposed to just featurizing and lifting to 3D. Yeah, thank you.
Okay, so maybe one last round of applause.
Yeah, I got it.
Thank you. Thank you.
So it's my pleasure to introduce our final speaker for today. Shorin Song is an assistant professor at Stanford University. Before that, she was a faculty at Columbia University. Shorin received her PhD in computer science at Princeton University. Her research interests lie at the intersection of computer vision and robotics, and her research has been recognized through many awards, including the Best Paper Award at RSS 22 and TRO 20, Best System Paper Awards at CoRL 21, RSS 19, and also finalists at RSS, ICRA, CVPR, and VIRUS. She's also a recipient of the NSF Career Award, Sloan Foundation Fellowship, as well as research awards from many companies like Microsoft, Toyota, Google, Amazon, and JP Morgan. Yeah, I'm looking forward to your talk, Shorin.
Thank you so much. And hello, everyone. Good afternoon. Thank you for staying to the last talk today. Yeah, so hopefully today you have heard enough ideas and thoughts about how to mastering the robot manipulation in a world of abundant data and get excited about that scenario. But I think my talk will be first focused on this first order problem of how to get to the world of abundant data, which I think is like a lot of people would agree that we are not there yet, right? So first, maybe let's start by just quickly discuss why we don't have abundant data for robots. There are many obvious reasons, but there's also like some more subtle and less obvious reasons. Right? So for example, the obvious reason is that if we want to collect robot data, oftentimes it does requires you to have some robots. So robot has cost. But I think more subtle reason is that thinking about data collection for robots actually has much higher operational cost. Right? So if you want to collect robot data in many different environments, that requires to ship your robot around or like just like move them into different environments. And also another cost that oftentimes people don't talk about is the expert cost. You need someone that's trained to kind of learn how to tally up robots and then also be good at it. So if you look at a lot of like very impressive tally option demos, actually I'm always curious about who tally up that data because sometimes it's actually really hard to tally up. So those are some hidden costs. And then what about internet data, videos or texts? I think the biggest problem for those data is that you don't have sufficient information. So obviously you don't have a lot of detailed robot action data. And also I think a subtle reason is that most of those data does not have those multisensory data that you need, like force and tactile, which is very critical for manipulation. At least I believe very critical for manipulation. And then the last part is about the reusability about data, right? Even if the data is so hard to collect, a lot of grad students spend a lot of time to collect their tally of data. Oftentimes the data only can last for one project. And then after that, you need to like switch to a different set of data. So the reason for that, like when we don't reuse data, oftentimes it's because the data we collected are very task and also robot specific, meaning that if you change your robot hardware a little bit, you move your camera a little bit, you cannot reuse the data. So as a result, a lot of those data has a very short shelf life that we just keep recollecting new data. So that is also a problem, like why we don't have large robot data today. But if you think about if we aggregate all the data that we already collected for robots, like with all the grad students across the world, it's actually quite a lot. It's just we don't reuse them. So today, my plan is to talk a little bit about our work and then use them as examples of how we can potentially address some of those challenges about data collection for robots, and then potentially like kind of paint a way of how we can get there for a world of abundant data for robots. So first work I'm going to talk about is this work called UMI, which stands for Universal Manipulation Interface, and the short is UMI. So what is UMI? So as you can see, UMI is a handheld gripper or a handheld device that allows you to do data collection. Like anyone can take this gripper to do data collection for in many environments, almost any environment, you can just take the gripper to that environment and collect data for many different robot manipulation tasks, like including very challenging ones like folding clothes or tossing objects. And then finally transferable to many different robots. So in our paper, we test this policy on 7-degree freedom robots, 6-degree freedom robot, expensive ones or cheap ones. So in order to do that, we have a few like carefully designed hardware and software interface to make sure that the data is transferable and reusable, right? So from the hardware perspective, our goal is really try to make sure that the data collection device is able to capture sufficient information for policy learning, but still at the same time reducing the embodiment gap between the human data collection and the robot execution. So to do that, what we designed is a few important design decisions on this gripper. First is that we use a fisheye lens on our camera to capture very wide field of view image so that we can encode enough visual context for inferring robot actions. And then we also add a little, like 2 small little mirrors on the side. So that is to help the system to kind of get a different perspective to the same view to help them to get a sense of 3D depth information. That's what we call implicit stereo. And then in order to capture sufficient action information for the robot learning, we first add a small code on the finger base so that we can track the continuous gripper width. So that is actually quite important because we don't want to just have binary controls of open and close. We want the policy able to precisely control the timing of opening and also the exact width of opening. So that's why we need to have this code on the finger to track that information. And also we use SLAM visual SLAM to track the camera pose in order to recover the accurate 6-stop robot actions in terms of action trajectories. And then on the finger side, we use soft fingers to give you a little bit passive compliance so that when you collide with the object or collide with the wall of the table, you don't break your finger. And also, when we read the paper, we say that this kind of deformation give you this implicit force information because you observe the deformation and you know how much force you apply. But in reality, what we found is that this information is quite limited because the type of material we use, actually, if it's too soft, it cannot pick up heavy objects. So, and if it's too hard, you actually cannot see much deformation. So later I'll get back to like how we can enhance this force feedback or force information later. But I think, yeah, so far actually with just this, it's a little bit hard to gauge the force information. Okay, so I think most importantly, I think that the thing you need to remember for this design is that we really try very hard to make sure that this interface can be applied for different robots because it only uses wristband camera and only look at the gripper. You can easily adapt it for any kind of robot arms you have. So that's why we call it universal diffusion interface. So in the end of the day, all the data that you collected for the task you care about is just a single MP4 file. And you can easily decode all the information necessary in order to train an effective policy, including, for example, detailed robot actions, multisensory observations, and also you can like include task instructions through narration. And we really hope that this single MP4 file data format is already so standard, so easy to share. We can use it as a shareable and a reusable data format for robot manipulation, so that eventually we can share across labs. Okay, so if you read the paper and look at the website, you can see that UMI is actually quite capable. Like we showed a lot of complex manipulation tasks like tossing objects, folding cloth, or even doing like dishwashing and like cleaning dishes. And then, yeah, there's a few demos on the website you can see. But today I want to kind of focus on a slightly different aspect, which is the portability of the data collection device. And as a result, allows us to collect data in the wild, right? So because the system is so portable, the whole handheld gripper is very light, very small, you can carry it around into any different environment you care about, like your home, your kitchen, and then collect the data that you care about. So for this particular cap rearrangement task, we actually collect over 4,100 demonstrations across 30 different environments. But in total, we actually only take 12 person hours, which is quite like short. If you have multiple people, that's like actually just one afternoon, you can collect all the data. And then in the end, we trained one policy that covers all this training data. So as a result, the learned policy actually can like generalize to new environments that it has never seen before. And it's actually like, I feel it's pretty impressive. For example, we just dragged this robot across Stanford campus, and most of the environment is actually outdoor testing that we never collect data on it. So for example, on this water fountain, we never collect data on a water fountain. We only collect data on actual tables. But the robot is able to work out of the box on those scenarios because of the diverse training data it has seen. So just to quickly recap for this UMI project, what we addressed is kind of like the first bullet point of the challenge, right? So because we don't actually need a robot in the loop to tally up, so the cost of data collection coming from the robot is much lower. And also because it's so portable and then you can easily take this thing, get into different environments, you don't need to worry about the shipping cost. And then because it's just a handheld gripper and very intuitive to use, you can pass it to your friends. And then you actually don't really need to train your robot expert to tally up those data. So that is the first challenge for data collection. How about sufficient information? So I would say that for UMI, actually, it does collect almost sufficient information for learning robot policies because, like I said, we track the grippers, we do the slam, we have the end effector poses. However, I have to say that the data collected by UMI, at least this current form, does not contain rich enough tactile or force information that is actually very necessary for manipulation. So how can we solve this problem? So in the second part of my talk, I will actually kind of mostly focus on a few extensions of UMI that's really thinking about how to add tactile and force feedback to the system. And then I think just give you a quick motivation. One of the reasons why UMI is much easier to do data collection tally operation is that you actually get very natural force feedback and haptic feedback when you're doing data collection. When you're doing tally operations, a lot of times you need to use your vision to gauge whether you're in contact or whether the action is precise. But when you carry a UMI, the force feedback is very natural. So that's why it's kind of intuitive to use. However, the problem is that while you are getting this information, while you're doing the data collection, the robot, when it executes their policy, they don't have that information, right? So when the robot is executing learning its policy, all it has so far is just a visual feedback. So it doesn't have any force or tactile feedback. So how can we address this problem? So today I'm going to actually talk about two of the projects that's actually trying to address this force and sensing feedback problem from slightly different perspective. One is thinking about what kind of sensing device we can add. And the other is thinking about how we can reformulate the diffusion policy or the policy formulation in order to better use those force feedback information. So this first project is called ManyWave. And so in this project, we actually try to give robots a sense of touch or tactile feedback through audio data, like the data that you captured through microphones. Right? So this may be a little bit counterintuitive at first, like why we want to capture tactile information or force contact information through a microphone. But if you think about it, it's also actually quite surprisingly interesting. So the audio feedback that's captured through a contact microphone actually provides very rich information about contact, right? So for example, it can easily tell you that when your robot is in contact with an object, what kind of object you're in contact with, and it even can tell you very detailed surface material information if you're just sliding through the surface, right? So for example, in our project, we actually test on this very interesting test where the robot actually can tell the different surface of a Velcro tape. So if you use a Velcro tape, you know that they have two different sides and the surface material is different. So in this case, the robot actually able to touch the surface and hear the sound feedback that while it's touching the surface and able to distinguish which side of the Velcro tape is touching and select the right one to do the task. So this kind of very detailed surface material information is actually even very hard to capture if you have very high resolution, like for example, gel size sensor. Because this the difference is so subtle and so detailed, unless you have very, very high resolution tactile sensor, you will have trouble capturing it. But a $5 microphone is able to allow you to capture this information. So I think the best part of using a contact microphone as a approximate tactile sensor is that this sensor, you can easily buy it off the shelf today from Amazon, and it's very cheap, $5, $10, you can get this contact microphone. And then even better is that when you get this microphone, it comes in with a very standard interface that you can directly plug in into the GoPro camera that we are already using for UMI data collection. Right? So you actually don't need to think about all this complicated electrical design in order to hook it up with your data collection system. And also it's automatically synchronized with your video data. So you also don't need to worry about the latency problem. And then I think also very nice is that this contact microphone almost never breaks. So if you ever have experience working with tactile sensor, you know that most of the gel set actually worn out if you use it for like prolonged period of time. And also oftentimes you need in-house expert to know how to maintain and fix your tactile sensors. But if you use a contact microphone, you don't need to maintain it. As a result, you don't really need to have an in-house expert. It's just plug in and play, very easy to use. So all this property really make contact microphone such a low cost but high return investment. So I would say that if you're thinking about making a robot to do any contact-rich task, you really should add a contact microphone to your robot. So I don't think you'll regret it. It's just a good deal. And then, however, there is indeed a small challenge or quite obvious challenge when you're thinking about using contact microphones in your robot. And I think that is come from like the background noise that you have. In particular, if you're using like UMI type of device to collect data. So here I'm not playing the sounds, but you can basically imagine that when you're using UMI, like the Handa gripper to collect data, your contact microphone will pick up some background noise or like people talking in the background. And when you're running the robot deployment, like executing the policy, the action, the system will actually pick up a lot of noise from the robot motor. So this is actually really loud, and it's actually vibrating quite a bit. So there is a domain gap, or like kind of like the distribution gap between the demonstration data and the robot data. So how can we bridge this gap, right? So that is actually a pretty practical problem. So during this project, we actually tried out a lot of different signal processing tools and methods. And in the end, what we found actually works the best is actually a surprisingly simple data augmentation method. The idea is that you have your data, original data collected that is relatively clean or has some noise, doesn't matter. We just add a lot of random audio data into this data set, just directly overlay it, and also some robot noise. And then use this augmented signal to train the policy. So what this policy learned is that I should just ignore those irrelevant noise, but focus on the task relevant part of this signal. So with this data augmentation, we can train this policy, basically train a pretty standard diffusion policy with these two sensor modalities, and we can actually execute, like deploy the policy for many different contact-rich tasks. So I guess just a quick summary of some findings in our paper. I think the first thing is that we do find that if you include contact audio, you can actually improve the robustness and the generalization ability of your policy. So here is just a quick visualization for the attention maps that the policy learned with and without audio. So one interesting thing we found is that when you are training the policy with audio, the policy is more likely to focus on the task relevant area. So for this task, it's trying to wipe the marks on the whiteboard. So if you train with audio, it actually focuses on like the shapes on the whiteboard. But if you don't train your policy with audio, if you only train with the vision, the network actually focuses on the room structures, like for example, the table edges or the room boundaries, and instead of focus on the whiteboard. So the reason is that without audio, the robot really have trouble knowing when it's in contact. So it's actually trying to use the room structure or the edge of the table to gauge the depths. So it's kind of overfitting to the wrong places. But with audio, it's very easy to know that when I'm in contact with the whiteboard, therefore focus on the right part of the problem. And another, I think, quite obvious finding is that we found that the noise augmentation is effective, although it's very simple, in bridging the audio domain gap. So if you are using audio, you're thinking about using audio in your robot, I think you should always consider using this noise augmentation. So this is actually not surprising because in vision training, we actually always add data augmentation, right, to make the policy robust. So I think here is the same story, that we add data augmentation in the audio to make the policy more robust. So many wave is good. That is like, it gives us a little bit tactile information than before. However, it also has a few limitations that I have to mention. So first is that while the contact microphone does provide information about the contact event, like when you're in contact, it does not provide you with very precise the force information. It does not tell you that you're pressing the surface with 1 Newton of force. So that information is not there. So as a result, one common type of failure modes that we see is that for the wiping task, sometimes the robot is able to wipe the shapes off, but sometimes it just uses too much force because it doesn't really know how much force I'm applying. I just know that I'm doing the job. So sometimes it actually, like, see, it's always bending the finger because it's squeezing too much. So that's one problem. It doesn't have very precise force information. Another problem is that it's more come from the policy formulation. So we still use diffusion policy that's just predicting the position of the end effectors. So as a result, the system, because it only predicts end effector pose and does not using any compliance, so it's actually not very robust to any unexpected force perturbations. So I think both of those limitations actually lead to the thought that I think we still can benefit from, like, if we can use real, like, precise force feedback, and then also combine it with like proper compliance control, so that it can better leverage the force information. So for example, here is a system that we can, or like what tasks we can do if we actually use accurate force sensors and also training a proper adaptive compliance policy. So you can see that this policy is able to precisely follow the very complicated 3D curvature of this vase. And it's also able to maintain the constant force in order to wipe out the marks from the vase. And it's also very robust to perturbations. Like, the student actually, like, try to knock down both the robot and the object, and it's still able to work. So to be honest, I actually see a lot of diffusion policy deployed in my lab and also across other labs. I kind of believe that this is one of the most, like, graceful and robust policy that I have seen, at least in my lab. And it's not trained with tons of data. It's just by leveraging better using force sensor, right? So if you actually really think about how I can get my policy into next level, that it just works better, smoother, and more robust, more elegant, I think maybe thinking about other sensor modality would be another direction instead of just adding more data. So how we do this? So this is the paper that we just submitted to ECRA. This is led by my postdoc Levine. It's called adaptive compliance policy. So the idea is quite simple. Is that we want to add compliance or like force feedback into diffusion policy. However, the challenge for adding compliance, or the tricky part about adding compliance into your system, is that the compliance profile, or the target or desired compliance profile, is oftentimes task dependent. Like, depends on task you do, that you probably has a different target compliance profile. And also, it is something that will vary or like change temporally and also spatially, depends on the stage of the task. So it is a highly dynamic property that if you just manually tune that compliance profile, it's very hard to get it right if you're changing from task to task or like different stages of the task. So so actually, because of that, if you look at most of the existing systems that's using compliance, they oftentimes actually just use a constant compliance that is uniform in all directions. So as a result, it's very hard to find the right compliance profile for the given task. Right? So for example, if your policy is too compliant, it's actually will lose the ability to track the target very precisely. So as a result, you may lose context at some point. And then on the other hand, if the is too stiff, you easily break your robot or tool or object because it just does not provide you enough compliance. It doesn't mean that you can just keep tuning it and get the right parameter. It's actually really hard because it's not the one single parameter. Your compliance actually will change before contact, after contact, and also depends on the pose that you're actually doing the task. So getting the right compliance is hard by manual tuning. So what we can do, we can learn it from data. Right? So that's basically the idea for this work, that we're trying to basically summarize the desired compliance profile from human demonstrations. And then we'll train a policy that's able to quickly and dynamically adjust the compliance based on the visual and the force feedback. Right? So the policy is the same as diffusion policy, but the input has additional force, and also it has additional output to describe the desired compliance profile for your low-level controllers to execute. So just high-levelly describing the output, that's the policy basically representing the desired compliance by using a virtual pose target and also a target stiffness value. So those are the things that learned through your human demonstration data. And here you can see that the robot actually, through their execution, when the virtual target is aligned with the position target, it means that the robot will be very stiff and actually track the position very precisely. And then when they're deviate, means that you want the robot to be more compliant. And then the directional difference between the reference target and the virtual target give you the compliance direction. So you can actually adjust the compliance direction in SIGSTOF as well. However, as you can imagine, this policy actually works really well and is able to like really gracefully handle this very complex context-rich task. But there is one quite big limitations that I don't really like about the system. That it really rely on a very expensive and also like hard to use force sensors. So we use the ATI force torque sensor in each of the robot end effector in order to get this force feedback. So as you can imagine, if we want to do data collection, now we need to kind of do data collection with these robots with this very expensive force sensor. That is kind of going against with my UMI design, right? I don't like that. So I think one thing that we are actually working on is try to improve this whole system design by making the force torque sensor smaller and more portable. So this is still ongoing work with my new postdoc Hojun, also from Stanford. That basically Hojun's whole PhD thesis is about this coin FT. So this is actually a coin-sized force torque sensor that's very small. Like this is the original ATI sensor, and this is a coin FT sensor. And then you can see the plot of the force feedback from these two sensors. That although it's not maybe as precise as the ATI sensor, but it's highly correlated. That you can actually get a pretty good force feedback or reading just from this small force torque sensor. So with this small sensor, we actually can add it to our original UMI design and then make the whole data collection device portable again. Right? So this is something that I'm pretty excited about, and we are actively working on it. So that is about the last point, is getting sufficient information, in particular force and tactile feedback. How about the last thing is reusability of the data, right? Can we reuse the data for different robots, different projects? So this indeed is the most common questions I get asked, is how to make the UMI system, UMI policy workable for a different robot. So I think for that question, it really depends on the type of robot you have, right? If you have another industrial robot arm that comes with a very precise and accurate IK, then pretty much the policy is directly transferable. You can deploy the same policy on a different robot by just calling the IK solvers provided by the robot. However, if you have a mobile robot or legged robot that does not come with like a precise IK solver, then what you need is actually a whole body controller that learns, like for example, in this case is a legged robot. So what we need to train the whole body controller to do is to learn how to move your body and legs so that you can achieve certain end effector trajectory that's predicted by the manipulation policy. Right? So here you can see all these errors is basically the manipulation trajectory that's predicted by diffusion policy from data collected by UMI. And then the whole body controller is trained to kind of able to track those end effector trajectories. So the good thing about learning this whole body controller is that nowadays you actually can train this whole body controller purely in simulation without recollecting any real world data or simulating any real world tasks, right? Which is actually the most expensive part. Like for training the whole body controller, you just need to load the robot. You don't need to load any robots or any objects or any tasks. So that's actually make it very easy to learn. So when you have the whole body controller, you just need to combine it with the manipulation policy that we trained with the real world UMI data. You can get very expressive real world manipulation skills on those very complex legged robots. So for example, you can do this kind of like a very fancy task of like tossing tennis balls. And then to collect the data for this robot, you just need to actually use the UMI gripper, like a handheld gripper, to collect tossing trajectories. And then the simulation data will learn how to control the robot body. And then I think what's more exciting is that once you have this system, you actually can directly plug in the original UMI policy that we trained for the cup rearrangement task for this legged robot, and it was immediately zero-shot work onto a new different robot embodiment. So that means that we can completely reuse the data that we collected in the earlier project. And for this UMI unlike projects, we actually indeed directly using the policy that we trained on UMI. We didn't do any fine tuning, didn't do any like data collection. And then if any of the things I talked about today interest you, you can check out our project webpage. For all the things I talked about, like apart from the ongoing projects, we always try to open source our code and also give you very detailed tutorials about how to build the UMI gripper. So we really hope that there will be like more UMI grippers around the world so that people can collect data. And then I think it's actually indeed true that a lot of people are already using UMI, printing UMI across the globe and building their own systems to collect data. Here it's just like 2 example works that I feel particularly impressive that people actually build UMI like in Tsinghua, and also here is Shanghai AI Lab. They actually also even improve the UMI to have a better tracking results. So that's also one of the pain points for like the UMI. Sometimes the slant doesn't work. And then I think there's many other works actually using UMI currently. And then I think like it's very encouraging to see like they're using it. And then also in order to, so just to help people or build up this community that people like share different data, we recently launched this data website. It's called UMI Data, UMI-Data. And the goal is that we really try to build a centralized hub or like a place to share different UMI data that's collected across the globe or from different industry or academic labs. And then if you are also using UMI or some related data collection device, you can actually contact us to list your data here as well. I highly recommend you to do that. You can also like start from our own project. We actually already shared all the UMI data that we collected throughout different projects. And then we really believe that there's no data set that's too small. I think one of the reasons that people back then don't really share their robot data is that they may feel like, oh, my data set is so small. It's only a single task, or like 100 data points. But I don't think like that's a problem. Like even you are just having a single task data set with a small number of demonstrations, you should consider this here because it will eventually add up, right? And then also we, yeah, oh, oops, so, okay. Okay, so the last point is that we really believe that UMI is a constantly involved design. That even if you are using, if you're thinking about adding new sensors or tweaking the hardware and make the device different, then you can still contribute to your data, even if it's not directly transferable to our current UMI design. It can still be used for pre-training or other creative usage, right? So regardless, I think you should consider share your data in this website if you are using UMI, or you just directly use the data that's already listed here. And that's the end of my talk. Thank you.
Thank you very much for the great talk. Are there questions from the audience? Okay, we can start here. Most.
Yep. Thank you very much for the talk. Basically, the tactile sensor you mentioned, the audio has been developed by Giorgio Cananta 10 years ago.
Yeah.
So what is the difference?
Yeah, I think the sensor itself has no difference. It's just a microphone. However, I do feel like in terms of how to use it, there's a slight difference. So I think before, the reason why people don't use microphone as a way to like get tactile sensor is because it's very hard to get explicit contact information, right? So if your policy requires like contact position or contact force as an input, then it's actually very hard to explicitly decode that information and then put that into policy. But if you learn it using behavioral cloning, you actually don't really care about explicit state information. You just need the raw input. So that makes it easier to use the microphone type of data.
Then basically, then what you were presenting, for me, there is no autonomy, it's more automated grasp, right? Because when we are talking about the vision and tactile, and we want to make the robot to be autonomous, to grasp the manipulation, the robot has to understand the visual properties and tactile properties. And the tactile property doesn't come with just with a simple contact, because it's action condition, right? Tapping, patting, scratching, sliding will give you completely different information.
Exactly.
So this is a tactile.
Yeah.
And when you are talking about the microphone, and the reason even the Giorgio stopped working on, because it doesn't give you tactile information. Is that a tactile?
Yeah, I don't think I fully understand your question, but I think, for example, indeed, the feedback really related to the action strategy. Like we show that when you touch the surface, you can actually hear the feedback instead of just directly touching it. You need to like sliding on the surface. So but instead of asking the robot to infer the strategy, we just demonstrate that strategy. And then the robot can learn directly from human demonstration. We simplify that process. So hopefully that's like answer your question. Maybe we can have more discussions afterwards. Yeah.
Maybe for the sake of time, we can one or two other questions from the audience. Yes, please.
Your floor set on the top. So just
You mean the deformation, right? Yeah, so I think when we read the paper, we actually make a point that you actually can estimate the deformation from the finger, or estimating the force from the deformation. But it's actually kind of hard because the material that we use is kind of like stiff. It doesn't deform that much. And when we change it to very soft material, it cannot pick up very heavy object because it bends. So that's a problem. Yeah.
Yeah, then maybe one more question from over there. Yes, please. Yeah.
Okay.
Yeah, I think both are very good questions. Let me go back to the first one. I think I didn't say that contact microphone is sufficient. I think that's why we are still trying to add force sensors. So I think contact microphone only give you, for example, a very high frequency information. It does not give you precise force, also does not give you the low frequency like force information. So I think contact microphone is a very convenient way to get a little bit like tactile, but definitely it's not the best way. So if you have money, like better. If you can design your tactile sensor, then go for it. I think that's still valuable. And then for your second question, I kind of forgot. Yes, about whether the force is the action or the, yeah. So I think in our current system, although it's a quasi-static task, actually it's not just taking force as an input and use it as a feedback. The output is actually very important as well. So it also infer, so the virtual target, you can think about that actually telling the robot that what is your expected force that you need to execute in order to do that task. You can imagine that for wiping tasks, you need a certain force. We also in the paper, we test on different type of tasks like rotating, pivoting an object that requires a different type of force. And also the force needs to change when you're like actually moving the object around. So it's already part of the output and it's already part of your action space for the force. That's true. Yeah. So I think for the tasking task, although back then when we do it, we don't have those feedbacks. I think it will benefit from force and tactile feedback. Yeah. Yeah.
Thanks again to our speaker. And now we have the final panel discussion with the 5 speakers from this afternoon.
I'm muted.
I do not because that sounds, but yeah, I know it's a bit good. Take one of them.
Oh, they should be together.
Yeah, they need to be together because one is for live stream and one is for the audio. So maybe we can put them together. Oh, they should be kind of together. So I can maybe start this panel with a question to our panelists. So yeah, maybe let's start with a more general question. So we have seen many LLMs and VLMs in the robot decision-making software stack. What do you think, which sensor modalities are necessary to achieve general purpose manipulation? Maybe, yeah, Ted, you already have the microphone, maybe you can. If you want.
Sure. Yeah, sure. I guess I can give a very easy baseline answer to B, which is I think definitely vision is needed. I think it's already sufficient that we see that pixel to action large scale imitation methods can get surprising amounts of dexterity and generality, perhaps a lot more than any of us would have expected. Maybe based on all of the great limitations of such a limited modality that all of the great speakers showcased today, I would not have expected a year ago that you could do things like shoelace tying, for example, without things like force or tactile feedback. But clearly we can get a lot farther with a lot less than we would have expected. And so the question is, how much further can we go? Or if there are like kind of walls we're going to hit, do we have any, strong signs that the walls are already here or they'll be arriving soon?
Okay, so I think the short answer, I really believe that all the sensor modality is useful. Like actually, I do feel like the more the better. But also, I think there is some practical considerations that's why people are not using all the sensor modalities. I think one is once you add more sensors, you does make your system more fragile and easy to break. If one of the sensor breaks, the whole system kind of like is not function properly. And also, surprisingly, when you have more sensor modality, you are more likely to get out of distribution scenarios. Because if one of the modalities out of distribution, the whole input is out of distribution. So I think that from the first principle perspective, I feel like we should get all the information we can. But I think there also requires like maybe new machine learning method or like careful thought about system design to make them robust to deal with all the different type of sensor modalities. Yeah.
Yeah, and Christian, whenever you want to say something, just feel free to jump in.
So, for me, basically, what in CoRL I have heard about the tactile is not really tactile sensing, neither the gel side nor the microphone. When we are talking about the tactile information, basically is action conditions. And one of the reasons you were using the force torque sensors, because in our body, we have 5 million tactile sensors. We have cutaneous, we have ruthenian, and the others, and they are working in different frequency. And we have different spatial resolution for different tasks, right? So, and for me also is not only in hand manipulation, is also whole body grasp and manipulation. So when you are acting or basically executing any action, you will be able to get different properties. Like sliding, will give you another, for example, if you want to recognize the textural properties, friction, and so on. And when we want to develop anyway, like manipulators, I don't believe that we have to just feed our networks with raw data, right? Because as I mentioned during my presentation, we have to consider at least 4 blocks. Multimodal sensation, interactive perception, and prediction, learning, decision-making, and so on. But what I can see here is basically one part, is learning. This is not really, we cannot really have a robotic system works in a dynamic environment using just a learning part, right? We have to consider everything in a loop, right? And the prediction is matters, for example, you were showing a cup. When you are grasping a cup, consider the cup is made of iron, you know, or a stone, right? The same one, exactly the same the cup made of plastic. So when the robot is grasping, the surprise happens, which is called predictive coding and active inference. It's completely different what basically we heard today, right? So we have to consider many things. It's not only the a block, you know, and we can say, oh, we have to just feed with a lot of data. That's all.
Yeah.
Oh yeah, I just want to quickly like respond to this. I think that yes, we probably don't need to always take in raw data, but I think it's extremely powerful and also like alleviating a lot of burden if we can actually directly use the raw data. And then I agree that if you have more intelligence, maybe you can train a policy that's able to reason about different materials of the object and then choose the action differently. However, that's quite hard. But what we show here is that with a very simple machine learning method, but just feed them different data, they're actually able to learn that strategy automatically. If you say that that's only learning, but maybe the learning also did a little bit of prediction and planning. Although I totally agree that for like a more long horizon tasks, we probably definitely need like more explicit planning and prediction. But for those like kind of reactive tasks or picking out a cup, we probably don't really need that kind of reasoning. Yeah.
Yeah, thanks. And maybe just for the other speakers to also have an opportunity to say that.
Yeah, so I don't have a lot to add. I think what I learned about the sensors in this CoRL is a couple of things. In the dexterity workshop in the morning, there was this hand with 4 fingers that would able to reorient objects without any visual feedback through the proprioception of those 4 fingers. So I feel like the more fingers we have, these more fingers allow even just knowing where the locations are to get a very good, understanding of, how the object reacts to your forces, which I found very interesting. And yes, I think force is very important. Another thing that I found amazing is what Pulkit Agrawal said. He said manipulation is not about vision. The human is doing the next thing that he's about to do as opposed to what he's actually looking at right now. And I think this is quite correct. Yeah, so we definitely need this force feedback that Shuang was talking about, and more than, there are too many vision-based methods, but I'm pretty sure next year is going to be way more force and tactile oriented and so on.
Thanks. Christian, do you want to add something?
Do you hear me? Yeah.
Yeah, maybe.
Do you hear me?
Yes.
All right, good. Well, not much, but if you really want to deploy these robots in the real world, right? Again, it's about, can we build these sensors in a robust way? And I think the tactile sensors are pretty fragile to this date. I think that there needs to be more done here, and I think but I'm still amazed is kind of the combination of using internal measurements like force sensors in joints, and how much you can predict using machine learning black box models, and you can inherently sense the touch. That there's some work I don't remember, but where you can you can touch the arm and it actually can precisely predict where the contact point is and the contact force on the arm just from inherent sensing.
So you want to briefly get to 1 or 2 other questions? Yeah, then maybe you can follow up. So another question, or something we also heard today, is about simulation, that this is also a very powerful source of data. And now I want to ask the panelists, what do you think, what are the best ways to combine this simulation data with actual like real world data to achieve in the wild manipulation capabilities?
For me, we cannot simulate tactile. It's impossible to simulate a tactile. Basically, it's a long time. It's 15 years I'm working on a tactile with Yasu Kuniyoshi. Basically, we were trying to find out even how many fingers do we need for the dexterous manipulation. It was like 15 years ago. And we don't need 3, we don't need 4, we need just 2 if we will have sensorized, 2 fingers. I think what is missing here, I can see people are not how can I say, they don't know the state of the art, what have been done before many years ago. You know, I think we have to little bit go back to see what has been done before. And the other thing is we cannot treat the tactile with the vision. So with the vision, you can collect a lot of data, millions of millions, you know, even you have a camera, nothing can happen. If you have your finger, if you slide the finger on rough objects after 5 times, start bleeding, right? So of course you have to use different methodologies, right? And what comes to the humans, we are using uncertainty-based learning, right? So we are not feeding with millions of data the people, the system. Robot has to know how much data is enough, you know, in order to learn something. So, and this is basically, it's called active perception and prediction based on uncertainty reductions. This is the thing basically, is from my side.
Thanks.
You don't want to. Okay, go back to the original question about sim and real. I do feel like both of them are very powerful, but they do come with very different limitations. I think for manipulation, like all the context-rich tasks, I think it's actually really hard to simulate them properly. And especially if you think about the diversity of the object you need to interact with, I think that kind of feels very daunting to think about simulating all of this. But for locomotion or learning the robot control is actually pretty doable in simulation. So that's why, like the Wumi Unlike thing, we have this combination of using real world data collection for manipulation and then learning the whole body controller in simulation. Yeah.
I think the reason I'm hesitant to say too strong opinions is that I think our team in the last few years has not invested too much in you know, sim to real, especially for additional modalities beyond vision. I think my intuition here is just that I think with a lot of the scaling approaches we're looking at, we are really betting huge on the diversity and scale of, you know, internet data. And I think when you go from internet scale data to robot action data, that's already one distribution shift. You add other special modalities, depth, touch, 3D priors, that's another distribution shift. Then you add sim to real gap, you're building a house of cards. And so I think what we found is that when the one thing we want to keep is and measure and improve on is the generalization, that you know, we want to kind of take as little risk that may have the chance of hurting generalization as possible. It's definitely true that I think, you know, we may be missing out on, you know, very high performance in some specific settings, but I hope that our lessons for scaling and maintaining generalization can compose with the great works that are being done on pushing the limits of these modalities later on.
Thanks. The other two panelists, Katarina, Christian, do you want to add something?
Yeah, so one way, so some beautiful ways to combine sim and real is you can go to your real environment and, you know, 3D perception works and you can reconstruct it and port things in simulation, and object detection works and tracking works. And also you can use essentially rewards simply from motion inference and appearance inference and instead of doing reward engineering. So that's one way. You can also, you know, have demonstrations in the real world and use them with reinforcement learning and simulation to robustify your policies. I mean, for me, the most impressive robots right now, beyond, of course, Tesla car and Waymo, are, you know, those locomotion robots and those leg robots. And these really show that they can generalize, and they use 1 billion interactions just to walk around, right? So manipulation hasn't showed anything impressive yet or something that works. In that respect, trying to combine sim and real sounds like a very good direction. And also simulators are also getting better and better and faster because there's also this trade-off, like, you know, you can be more accurate on the contact representation, but then you are much slower. So people are pushing in this way. Now, at the limit, after 10 years, I don't think we may be using simulators. I think we're going to all be using neural simulators. We'll be figure out how to learn world models from data in sim and real, and we'll use our mental models to, you know, augment them any way we want, and you know, scaling up mental data. But maybe not next year. I'm not sure.
Thanks. Great point. Christian, do you want to add something briefly to that?
Yeah, I think one trick that people do nowadays, right, is to separate. So you basically learn a representation of the environment. So you have a visual model with some sort of representation, and then you plug it in and you train the motion with other methods, right? So you decouple vision and motion control, kind of. That's kind of powerful, and you can also kind of test the different modalities. But I think people didn't understand yet, right? What's the right connection? I mean, 20 years along, people distinguish, made the interface between motion and vision by a 60 breast pose, right? And that didn't work well. So there's now there's some latent space that goes on and so on. But that's one way where you can make things work nowadays. But apparently, yeah, the world model idea is I think the path really going and these bigger models, right? But I think at the moment this is kind of one of the approaches to deal with this variability in the perception data.
Thanks. So I think for the sake of time, we can maybe take one more question from the audience. So yeah, I think this was the first hand to go up. Yeah, please.
Yeah, so a question how to utilize probably only like several percent of them have those data, and there's still a lot of gap. So what's your take on that?
So just very brief for Christian. So the question was about how we can leverage internet scale video data, because there was the embodiment gap. Many of those videos don't have useful manipulation capabilities. Yeah, so yeah, Katarina.
Yes. So the first thing that was tried is let's use video data or image data to learn features, right? Like this R3M, I think is the paper called. I mean, that's one way, feature learning. Another thing that people do is they predict videos and they think that it's a good pre-training task for downstream policy. So this also has shown to work. Another thing is you learn video models and you use them as your simulators. Are going to be quite slow because you need to be generating pixels. One thing that I find particularly possible and easy to do in the next years is instead of just looking at videos as for feature learning, is you just really see it as essentially a simulation. You can see exactly where the hand is going and how the object is moving, and which part. Now we can estimate perfect camera motion with learning-based methods in the wild. And I really very much believe that we'll be able to do video to 3D to 4D and essentially use this for manipulation. Now, of course, this is for videos that show manipulation. If you have videos that with cats jumping, I mean, they're not very related for robot manipulation, but there are a lot of videos of humans manipulating things that we're not using right now, like in Ego 4D and so on. I do believe that as perception is getting better and better, we will be able to use these priors.
Thanks.
Yeah, big plus one, I think, to using videos as a pre-training target and auxiliary task. I think it was Ilya Sutskever who once said, well, he believed that once superhuman video modeling is solved, robotics will be solved 6 months later. I don't know if that's quite as true. I think actions have a lot to add, but in general, whether video generation models are used as a pre-training task, as a world model for search, even at inference time, definitely good ideas. One question, sorry to hijack, is maybe to the other panelists especially, is how do we think about combining internet scale data with non-video modalities for all of these very unique and important sensors, such as whether it's force or audio or tactile or whatever it is, where there isn't great coverage of internet scale data for these modalities? Like, how can we hope to generalize, right? Do we need to wait for maybe the next foundation models, which do have these modalities as a first-class citizen? Like next year, maybe there will be audio and video native foundation models for both input and output. Do we need to wait for one for a tactile foundation model, or how should we think about it?
Yeah, Sharon was shaking her head, so yeah, looking forward to that.
I think that's actually a very good question. And okay, so first of all, I feel video data that's like it feels silly that not use it, right? It's there, and it has like all this dynamic information. We should definitely use that for training policy. And then, but I feel maybe what we are really lacking is a very nice network architecture that maybe we already have it. Transformer probably can do that. That's able to kind of take in like different type of modalities very like organically. So I think right now, what we are thinking is that maybe we'll pre-train the visual encoder with video, and then we'll fine-tune it with action data. But it's possible that from the beginning, the transformer or whatever the foundation model already have all this input and outputs, but it just you can fit in different type of data to train different part of the network. So if you design it from the beginning, then problem is that later if we have tactile data, we can just train the same model, but with additional data inputs, and then it can just keep adding to the current model, and it can incrementally improve with more and more data instead of designing or training the network from scratch. So I hope that could potentially be one solution.
Thanks. So Mohsen and Christian, do you want to add anything?
Basically, as I said, this is a very computer vision approach, treating the robots. You know, for me, it's completely different. So for me, embodiment matters, right? Why there are many robots are failing, even they have a perfect vision, you know, because there is no embodiment involved during the training, during the learning. This is my hand. This is the reason I can hold this one, because I learned with this finger. This, even if you change the properties of your skin, you know, it gets a little bit basically oily. You cannot grasp anything because you learned with this hand. So everything is not computer vision based approach, because we want to solve basically everything with the methodology algorithm we have in a computer vision, because it's easy. But if you want to treat other modalities, we have to go to another types of basically the methods. And I like transformers, but when it comes to the robotics, it doesn't work, because we have to do, how can we do the counterfactual learning if the system making mistakes? How the system can learn from failures, right? This is the thing, even we have it in our human's brain, you know, when it comes from the walking, you can check your CPG, you know, then we learned walking from the failures, right? So how the system can learn, but transformers is good, great for basically language modeling. But when it comes to the physical system, like a robotic system, no, forget about it.
Yeah, then Christian, maybe one last take.
It would be super awesome, right? If you would just give a GoPro camera or even the Humi hand to our customers, human operators, and then they do their task, and then we get the data, and then robot let's train once and it's done. I think that would be really great if that works like that, and we don't have to send the robot and then teach it, you know, how to do things. Yeah.
Thanks. Yeah, and with this, I'd like to conclude the workshop, or at least this panel. And we have few more things to say, but very briefly. Yeah, so thanks again to our panelists. Yeah, and now just very briefly want to wrap up this workshop.
So I thank everybody who attended the workshop, and especially the speakers who contributed to the workshop. Thank you so much for your fantastic talks. I think you tailored the talks to the workshop. Thank you so much. I think it was really interesting for everyone. We see this, I mean, 6 p.m. on a Saturday in the room. Still, you know, we have a really good attendance. I think what we saw today was that we have a range of data, from robot-specific data to large-scale internet data, different sources of getting the data, simulation, teleoperation or demonstration, just the internet, real-world robotics data, getting the data through RL or self-play. I think there's still many open questions around just thinking about where the data comes from. And then we also saw that, I think a general trend that additional sensor modalities improve performance if you combine them. And we also saw that language is a possible bridge, but I think just a general trend to look at different sensor modalities, which is very interesting. We also heard, including from the speakers from industry, that, success rates are not yet there in many cases. And mitigating failures is something that we as researchers often don't look at. We just say, in 20% of the cases it failed. That's not enough. And of course, I think in robotics, especially if you look at manufacturing, we are used to superhuman performance, right? I mean, what manufacturing robots do is something that no human can do in terms of accuracy and speed. And also that is something I think will be interesting to see where we get this from. Behavior cloning alone will not achieve this. So I think there's still a lot of open questions, and I think we saw many interesting ideas today, and I hope you take something out of this workshop and continue interacting with our speakers and organizers. So thanks everyone, and thanks again, a big thank you really to all the speakers for their fantastic contributions to the workshop. Thank you so much.
Home or?
Yeah, if you are leaving and traveling back home.